I hope everyone has their coffee, some sort of beverage. But yeah, I guess we'll get kick-started. Kick-started? We'll get kick-started. Yeah, there's a phrase there somewhere that I'm trying to say. All right, first things first is we do need to talk about the atom. Sounds like, I'm pretty sure there was a movie called We Need to Talk About Kevin. Or was that a TV show or a TV series? One of those things. Now, quick crash course revision very, very quickly. Let me bring the whiteboard up. It's good. So that there's not too much reflection. Water is a beverage. I mean, it's definitely a liquid you drink. What is classed as a beverage is a good question. Okay, so let's look at atoms. Not to be confused with atom. Let me know if my mic cuts out, by the way. I'm increasing the gain. I am going to have my back turned to you a bit. Times. So let's quickly look at an atom, right? An atom is made of protons and neutrons. It kind of looks like a ball of grapes. And some of them have positive charges, and some of them have neutral charges. And the things that swing around are the electrons. And this is what we're interested in today. We'll talk about protons a little bit later again when I talk about semiconductors. But that's going to be in a few hours' time. Now, what we will be doing is talking about these electrons that are on the most outermost surface. And the reason is because when we talk about conductivity, right, conduction, anything, when we talk about a material that allows flow of electrons, i.e. these bad boys to move, we usually talk about metals. And we talk about metals because they have something called a metallic bond, which allows them to be good conductors. Hi Naz, hi Tetsu, welcome in, welcome in. This is the thing that makes them good conductors. Because they make this metallic bond, and again, I'll go over this again later in more detail. We usually use copper wires for a lot of the things. Most of your electronics, if you're looking at your PC, if you're looking at any plugs, cabling, chances are, if you're a gambling person, they're going to be copper. Copper is very cheap, very good conductor. Hi Riso, welcome in, welcome in. They're going to be very, very good conductors. All right. This is the principle of it. And this is kind of the definition of one of the things that we're going to talk about, which is current. Current is quite literally the flow of electrons. And you might ask yourself, well, why do electrons flow? Well, you need to create something called a potential difference. There's a few words we use for this. I'm going to list them. Potential difference. Could be just potential, by the way. Potential difference. There's another word that we like to use. Does anyone know which one I'm referring to? Hi, welcome in, senior. Big welcome in, welcome in. I'll be at my lunch break shortly. Nice. Voltage, exactly. Put on a Russian accent for that. But you're absolutely right, voltage. Now, some textbooks will tell you EMF, by the way. Electromagnetic. Yeah, no, that's right. I was confused with the magnetic one. I have to read it out. But you're absolutely right. Voltage is the one that I tend to use as well. Now, I don't like to use EMF only because I'm being pedantic, being a bit rude about it. Hi, Blank. Welcome in. Welcome in. Hope your stream went well. And does anyone know why I don't like using EMF usually? Anyone have a sus? Hi, Smirky. Welcome in, Raiders. Hello. How's your stream, Blank? How's your stream, Smirky? I hear you were celebrating 9 years of partner? It attracts ghosts. That's a pretty good reason, to be honest, if that were the reason. Because only weird people would not say voltage. Do you know what? I kind of like that idea. Smirky Raid, welcome in, welcome in. A co-working stream, nice. I love to learn about science. Well, you're more than welcome here. We are learning about science today. Today, we are doing Crash Course Electricity 101. So we're just starting with the concept of electron flow, which is your current. And now we're talking about something called potential difference. Electromotive force is, there we go. That's one of the things. I almost got it confused there. But the reason I don't use electromotive force usually when we talk about these things is because it usually refers to the supply. Now, this might seem weird, but I'm kind of jumping ahead. Usually, the force, the electromotive force in our system is going to be a battery, right? But there's going to be voltage drops, a term that I'm going to say. There's going to be potential differences randomly in your circuit, and they're not necessarily EMFs technically. They're just drops of voltage or potential differences randomly around your circuit. Well, it's not very random, but you know what I mean. That is why I'm going to be pedantic, and you have to be careful when using the word EMF. Again, you don't have to be. It's just being a bit, snobby and pretentious if you see anyone being snobby about it. That's where the snobbiness comes from. I hope your stream went really, really well, Smarky and Blanc de Nuit. I hope I got it right. Thank you so much for the raids. You guys are more than welcome here. Electromagnetic means both magnetic and electric. That is true. Oh, did I pronounce it perfectly? On paper, I know a bit of French. Doesn't mean I do know French, though. That being said, we did finish Clair Obscur recently. Amazing game. Chef's kiss. A French chef's kiss to the game. Okay, so current flow or electron flow is referred to as current. Not really, okay? I just spent so much time explaining that the flow of electrons due to a potential difference is called current. But here's a little bit of a story. Not actually. Because back in the good old days, before people knew what the atom was, what the electron was, and they discovered electricity, I believe we blame Benjamin Franklin for this particular incident. They didn't know about positive charges and negative charges and things like that. And so when initially what happened was Benjamin Franklin was able to describe how a capacitor works, how a Leyden jar works with a storage of positive charge on one side and negative charge on the other. And he used terminologies such as credit and debit. Very American, I would say. Now, the problem is he had to gamble. He had to gamble which side would be positive and which side would be negative. There was a 50-50 chance to get it right. And he didn't gamble on the correct one. So what we thought was the flow of positive charge back in the day turns out to be the flow of electrons, the flow of negative charge. And so that is why to this day, when we talk about something called current flow, it's actually in the opposite direction of electron flow. What's really, really, really interesting is that when you look at textbooks, electrical engineering, electronic textbooks, anything like that, I have one right here somewhere, but it says something like electronic and devices, electron flow edition. And it'll say something, and another book will say, I don't know, DC-AC fundamentals, current flow edition. There are literally textbooks that will write equations, derivations, mathematics, all of that based on which interpretation of current flow you take. The argument that I always use, if you're doing basic electricity, if you're doing electrical engineering and robotics, all of that, you're going to take the old school way, the current flow way, this way. Okay? If you are studying electronic devices, specifically semiconductors, anything kind of like physicsy aspect of it, you'll be studying electron flow. You kind of have to, because if you're using any physics explanation of anything, you're going to have to talk about the electron. We have to talk about the electron in that case. Live long and prosper. Welcome in, welcome in. Not really, Grim. There is an intricate reason as to why we name it negative and positive. It's a little bit more towards the realm of quantum, but there is logic to the madness as to why we call it positive. It all warps in with the whole electromagnetic discussion eventually in the end. Yes, as every sci-fi movie ever existed, quantum is the answer to everything. If I don't know the answer to anything, I'll just say, it's quantum reasons. Okay, so we have covered current. The symbol for current, by the way, is a capital I. The unit for current, an SI unit, is amps. Now, usually when we're working with anything that I'll be building, we absolutely will not be using amps. We'll be using milliamps because let me think about it. Personally, in my whole life, I've only used up to 2 amps in a lot of the stuff that I work with. And again, I worked with battery and battery cells. So you can imagine that, me working with 2 amps is quite extremely high. But most of the time, in any of the electronics, in the building stuff that we work with, we'll be using milliamps. But the unit for it is amp. I'm just playing Witcher 3 background music from Velen. 1 ampere does carry a lot of electrons. Yes, it does. Yes, it does. Now, the symbol for voltage is, this is interesting. So some people in some nations of the world will use the letter capital U, but I use V. This is controversial. This is where humans split in half. This is where wars are being fought. Well, lightsabers. I use the symbol V. And the unit is voltage. The unit is volts, apologies. And the symbol for it is V. And the reason why people argue with me about this, the reason why there's so many arguments about this is because people are like, but tofu, now I'm going to get confused. Are you talking about V the units or V the equation, the symbol that it represents? And my argument to that is, if you're getting confused at that part in your equation that you don't know if we're talking about number 1 units or number 1 the symbols in the equation, I think we have worse problems than getting confused between the symbols. It should be clear what you're working with, whether it be units you're working with, whatever it is that you're deriving, or the equation. That's my personal argument. Exactly. We have bigger
it's the only way to be sure.
Bigger problems. I didn't spend too much time on the electron, Grim. Yes, so I'm just going to skip away. Amps is coulomb per second, but. We're going to skip ahead for now. But what about volume? Hi, Bog. Welcome in, everyone. We're just doing Crash Course Electricity 101 today. That's the buzz that we're working. Velocity is always lowercase v. Volume is uppercase, but velocity is always lowercase. And then there's the drunk v as well, which is frequency. I forget what that symbol is called in Greek again. Okay, we're almost done. The last thing that we want to talk about is the resistor, so that we can talk about Ohm's law. We will, Lunar. Resistance. Vive la résistance! Let me see which way is better so that you can see the board. I'll just move my boxes of gadgets and gizmos. Rewiring my house, nice! I wish you best of luck with that. Stay safe, make sure everything is grounded correctly. Oh, sorry, I hit the mic. Resistance is another very important thing. I'll tell you, so resistance is, the unit is ohms. And the symbol is a weird looking horseshoe. Greek letter. Resistance is futile indeed. It is. Now, what resistance is quite literally. Physicists are not trying to mess with your brain here. It is quite literally in the name. It is the resistance of flow of current. Okay? If you look at it from the perspective of electrons, it's the traffic jam. When you have a system, you have a voltage, a current, a resistor, it defines by how much the current is allowed to flow. And between all these 3 things is a very, very important equation or relationship that was hinted. Now, before I get to that, actually, I'll kind of explain all of this using fluid dynamics. Okay, before any fluid dynamic engineers, get traumatized really, really quickly. It's okay. You don't need to run away. We're not going to do anything crazy. But there is an example that people like to use when talking about voltage, current. We talk about water flow and pipes. No, let's not talk about Navier-Stokes. Let's shh. We're not trying to scare viewers away here. So let's imagine what voltage is. Okay, so I said a voltage is a thing that makes the electrons go. But why do the electrons go? Well, in reality, especially when we draw it in a circuit, when we draw the symbol, it's a battery. It's a thing that supplies power. And what you have is a positive terminal and a negative terminal. So when you have something that is 9 volts, you have a positive side voltage of 9 volts and a potential voltage side of 0 volts. And electrons are going to flow, okay. So electrons are going to flow to the positive side, but remember, current goes the other way. So the current is going to go from the positive to the negative, okay? And you're trying to envision it, it was like, well, why? Why are the electrons moving? There is more quantum mechanics actually to explain this, but when you use the water pipe analogy, it might be a little bit nice. Let me explain. Do you guys know about potential energy in classical mechanics? Okay. Remember the gravitational potential, M. This means that if I'm standing right here on the ledge, I have 0 potential energy if I were to jump to the right now. I had 0 potential energy because my height difference was 0. Now, imagine if I climbed up on a stool. Might be a health and safety issue with it. So I'm not going to climb up on the stool. I'm going to climb up on the stool and there is a small height difference. Let's say about 30 centimeters, about a ruler. Suddenly, I do have potential. mgh. M is my mass, how much I weigh. G is the gravitational force of the acceleration due to gravity. And h is the height difference, that 30 centimeters. I have the potential to do a lot of energy. Yes, these are words that we can use to talk about, about the potential that you guys have in life, of what you guys can achieve, especially if we tap into our unlimited potential. Sorry, my mic must have cut out there. Unlimited potential. What is the practical application of MGH? You can use it to determine your kinetic energy really easily. So the interchangeability between MGH and the kinetic energy, half mv squared, you can calculate your body's velocity at a certain point of the trajectory. Basically, let's say I was jumping off a cliff. Okay, that's a bit extreme. Let's say I was jumping off a ledge and there was a certain height to it. You can actually calculate theoretically at what velocity you are going to impact the ground and calculated your chance of probability. For health and safety reasons, please don't do that. Do it theoretically. Don't actually do it. I was regaining brain cells. Well, welcome in. If anyone wants to regain some brain cells, you guys are more than welcome to come in. Now, that is classical mechanics, and I'm going to associate potential with the same reason. You can imagine that the flow of water, i.e. the potential of our current, let's say, again, let's remove the word current now, and we have water and pipes. We basically have a huge height difference now of water here. And our pipes are going to be the wires, the current that's going to be carrying. If we have a lot of water right from the top, we're going to create lots of pressure and the current is going to go out really, really fast. If we remove half the water, let's say it's not 9 volts anymore, it's 5 volts now, apply 5 volts instead, there's less pressure to push out the water. That's the kind of equivalent to potential and of electric circuits with mechanical water systems. Now, what is current? It's quite literally your flow of water. Your molecules of water are now the electrons in this case. So that's the other example. So we have voltage and current, and then your resistance is basically how thick your pipes are. If you make your pipes really, really thin, you're increasing the resistance. if you make your pipes really thick, you are decreasing the resistance. And so these analogies are usually used to explain current, voltage, and resistance, especially in an introductory level. Personally, I'm not a big fan. I like to think about the electron. But again, I'm not an electrical engineer or, computer scientist, which is where usually kind of analogy is used. I do like thinking about the electron usually. But in case that is a bit confusing, especially since I only did a fluffy version of the atom, if this analogy helps, absolutely take it on board. Because even though it's not real, let's say, because it's still only an analogy, the concepts and the physics of where things move and why remains the same. Does that make sense? Maybe I confused everyone even worse. I apologize about that. Where's my spray bottle? Here it is. Sorry, I'm missing a lot of chat. It is moving a bit quickly. I apologize for that. Yeah, the duster kind of spreads my marker a little bit too much. So that's why I don't use a duster. Not very good for some. Okay. I just have a little notepad here to make sure. Are you a teacher, IRL? I'm a lecturer. I'm a physics lecturer. But I am also technically a qualified teacher. Let me see, what did I have in my lesson? Talk about the atom. I'm skipping the proton, neutron, electron, and Bohr model because I'll talk about that later. Valence electrons, conductors. Okay, almost one more thing left. I'll introduce the idea. There is a test, yes.
Ray, when someone asks you if you're a god, you say
yes! Welcome, Diaz. There will be a test at the end of the stream. We can combine all of these guys together. The I, the V, and the R with a very, very classical equation that you cover almost first thing ever you do in electricity. V is equal to IR. This is referred to as Ohm's law. Exactly. That's voltage is equal to your current times your resistance. We'll put the symbols up here, just so we don't forget. Voltage, current, now, this is almost true, almost 100% of the time, but not always. There are a few exceptions to the rule. First of all, this is only true for conductors, things that conduct electricity quite well. So I said earlier, copper is really good. There's certain metals there, combinations of different metals that are very good. Examples of things that are not good conductors are things like a piece of wood. It isn't very stable, and this stuff doesn't obey it. Another thing that doesn't obey this perfectly is something called semiconductors, which I plan to do a session on in a couple of hours after we do some introductory level physics. Semiconductors only obey Ohm's law over a certain range. And another thing that affects this equation is temperature. Resistance does get affected by temperature. And this is a bit more at a quantum level, not even at a quantum level, but more so imaginary as to why this happens. Solids expand when they get heated, there's an increased traffic jam, and it's this exponential growth. It's not even a linear growth, it's an exponential growth, and it's very, very hard to work around with. But generally speaking, unless you're working with huge currents, you're safe. The heat shouldn't be an issue. In fact, none of the demonstrations I'll be doing today are going to be unsafe in any way in that way. Everything I will be doing is safe. It is being taught at a secondary school level education. Maybe not the semiconductors. The theory won't be. It'll be at a bit of a higher level, but the experiments are going to be at a secondary school level. So we are doing safe things generally speaking. Obviously, don't be silly. Stuff. Okay, what are capacitors? Capacitors are, I'm just sitting down for a second because I'm tired. Capacitors are, what are they? They are metallic plates that can store electric charge because electrons aren't allowed to pass through unless you obviously break the capacitor, apply way too much voltage, and they will be able to jump. Barrels for water to fill up. Will I cover that? Yeah, so basically what I have planned for my first experiment today live on Twitch is that we're actually going to prove Ohm's law. Before I get to it, let me think about what I should cover to make sure that we know things. Measuring voltage and measuring current. I think that might be very, very important. Yes. I'll talk about this. And I'll show you some symbols actually even. Let's talk about symbols. Not secret society symbols, although maybe sometimes people feel like physics is a secret society. No, I don't study it or teach it, Garth. Not much. Not much other than the fluffy stuff we all studied. Potential wonder. Definitely on semiconductors. I'll talk about diodes and stuff like that. But not... I don't think I'll do capacitors or inductors because I'm avoiding anything with AC today. Today, we're mostly going to do DC. So let's build a circuit that I will be building later. This is going to be the circuit that I will be building later on today. The big line here and the small line like this is a symbol for our voltage source. This is basically the feed, the pressure that we are going to put into our system. Let's pretend I'm going to put 5 volts through. Okay? This symbol is the symbol for a resistor. A resistor is the thing that's going to slow down the current. And it's usually a little piece of metal. I'll show it to you in a few seconds. And let's say we place it at 500 ohms. And we're going to have current. If our loop is closed, if our circuit is closed, we are going to have current flow. We'll have flow of electrons away. But our flow of current is going to be this. We can calculate the current thanks to law. So this is a universal symbol for a resistor in a circuit. And this is the universal system for a voltage source. Another one that you might see sometimes in your textbooks or in diagrams is a double one, like this. Same thing. But remember that this positive part here, the big line here represents the positive side of the voltage source. And this represents the negative side. So when we're showing current flow, it always goes from positive to negative. And again, this is why I tell you to dissociate from physics. Because if you are a physicist or you studied intro to physics, you will think, but the electrons should be going to the positive port. That doesn't make sense. Again, this has got to do with the classical confusion that was made over 200 years ago. Not confusion, but a gamble. So over 200 years ago, people gambled as to which one was the positive and negative. We got the gamble wrong. We built all the foundations of electronics based on this, and only backwards went back, after a long time, went back and said, oh, by the way, we made a mistake, but listen, so what? Let's keep going with it. So that is where that comes from. And you're absolutely right. Sometimes the resistor symbol is different. In fact, more often than not, you will see a resistor like this. It's just a rectangle. Sometimes it's that symbol as well. It's not so much that it's changed. It's got to do with, I would say, cultures. Different countries and different cultures will use different symbols of resistors. Most of the time, I will be using apparently what's called the American Standard, which I know is controversial because we use SI units and all of that. But I think what I use is called the American Standard. So every nation, every region will have their own kind of practice. Familiar with that, of course. Hi guys, welcome in, welcome in. And we use both interchangeably. Yeah, for me, personally, I see both of these all the time. I've never seen a lecturer or a scientist or anything where they're like, oh, you have to use it this way. Both are interchangeable. The reason originally why oh sorry, my head is blocking it. The reason why the resistor is a squiggly line is quite literally that was actually what the first resistors were. They would get a wire. Lots of gizmos and gadgets around. They would get a free wire like this and quite literally bend it back and forth like this. Bend it over and over and over again to build up resistance. To build up a resistance. That's where that symbol kind of notoriously came from originally. Now, if you look at modern resistors, they're quite literally rectangles. So that's why the symbol for it is rectangular. In a university cover. Yes, I do know about the elephant toothpaste. That's a chemistry demonstration. Does the bending affect the resistance? It would at a very fundamental level because you're cracking and breaking the copper wire, but I think it would be very small, Hitch. I think it'd be very, very small. Yeah, I'll show you what a real resistor looks like. Grab you some here. I have a big box of secrets. Preparing ahead of time. I want to do Ohm's law as well, so I might as well get a resistor. So here is what a resistor looks like. I'll try and get the camera to focus it on for you guys. There we go. This is a 1 kilo ohm resistor. And these lines are actually very important that are on the resistor. There is a cheat sheet that you can use to actually identify what the resistance is. There's even, the last line is usually a notation of what the error is in the resistor. But I never trust those things. I never trust my color coding expertise in this. I always just measure the resistor because, you know, very, very, not disheartening, but you know, in the moment, you don't trust yourself. I don't know about you, but I'll never trust myself in reading those. Hey, Tapcat, welcome in, welcome in. What is happening in the box to change the resistance? Oh, it's the material, the density of the material in it. There's a whole section on that. Unfortunately, I won't be covering that today. Apologies about that. But I plan not to cover it. In the background, you'll see a bunch of electronics, things like that. And you'll also might see a bunny running around. Don't be alarmed. There is a bunny running free in the house. It's all normal. Nothing to be scared. Turn off the fan for a bit. A bit hot in Ireland today. We're going to do Ohm's law in a second now. I'm just taking a quick break because imagine giving a lecture or teaching can be a bit tiresome. Why do you stream? Because I believe in the idea of giving education for free. I do a lot of social media outreach. If you guys are into Instagram or Blue Sky or YouTube or TikTok, whatever social media you have, I do short form content, and I try to upload like physics education in shorter than a minute. So something you can learn very, very quickly and revise over it. So yeah, and I do it on Twitch as well. So that's my kind of... All electronics component contain blue smoke. It is a wild day, King's Crypt. Okay. Let's set up something here to actually test Ohm's law. So it's one thing for you guys to trust me, but it's another thing for you guys to actually see the experiment for yourself. So what I'm going to do, we're going to actually, I'm putting away my markers because they're all over the place. We're actually going to build the circuit. Oh, I forgot. I knew I forgot something. I wanted to talk to you about how to measure stuff. Here we go. Now, I feel like this stuff is glossed over, and I almost glossed over. So it's understandable that other people might do the same thing. So a quick thing I want to explain is how do we measure things? How do we measure voltage? How do we measure resistance? And how do we measure current? Sorry, my beautiful Witcher 3 music in the background is a little bit on the louder side in my own ear. I don't know what it's like for you guys. I'll just turn it down ever so slightly. So, the way we do that is by using this bad boy. I'll introduce to you that I don't have a name for this guy. I got him in Lidl. He's amazing. But this is a multimeter. A multimeter is amazing. It can do everything. It can't solve your life problems, but it can solve some of your problems. So a multimeter can be used to measure resistance. It can be used to measure voltage, and it can be used to measure current. You do need to do a few mechanical switch arounds, but the design and the premise of a multimeter, especially a voltmeter, is actually very, very, very simple. It's very, very cool, and you can build one at home. Highly recommend that as a first-time project. If you guys are just starting into analog electronics, I think Googling how to build a voltmeter is a great introduction to it. And in fact, if you watched all of this stream today, I know it's very, very tedious, especially when I get to diodes and I explain LEDs. I think like you really will cover today the basis to build a lot of cool little nifty things. Now, sorry, my rant. There are three things that we can measure. We can measure voltage, we can measure current, and we can measure the resistance. Obviously, according to the plugs and according to certain ranges, because basically this guy is a giant resistor, and we have to plug in mechanically which resistor we want to put in so that we can measure things. Now, when we're measuring the voltage, we are going to measure it in parallel. What does that mean? This word is going to be very, very important later. What have you built? What have I not built is the question, Tommy. I'm an applied physicist, which means it's my whole life is just building things. Just depends what. So if I were to measure the circuit, and I wanted to measure the voltage source specifically, let's say the voltage source, I would literally grab these two needles. They're little metallic things at the end so that we can actually, get conduction, we can get flow. I would measure it across the voltage source. Or if I wanted to measure the voltage across the resistor, I would measure it across here. What's really important, and kind of, I hope that this kind of gets into your brain, especially when I did the introduction to the voltage, is that when you're measuring voltage, it is across something, not through something. I swear, this is if I ever hear my students ever say, I measured the voltage through this. You can't measure through it. It's across. It's a potential difference. It's like, imagine that we didn't... remember when I used MGH, right? As the potential to Earth. It's like saying, well, my height is 20... I'm at a height of 27 centimeters. Now, obviously, we can always assume what they meant is from the ground up to 27 centimeters. But let's say we were beings that didn't exist on ground. We just floated. Where is your reference point? What does 27 centimeter mean? 27 centimeter from where? So in voltage measurement, that's the exact same reason why we measure across in parallel. We're measuring it from one point to another reference point. It's across something. We assume sea level, but let's say we were floating, Yes, I'll speak about voltage drop in a little while, hopefully, especially when I get to the potential divider. Yes, I'm going to be teaching you about potential dividers, chat. It is going to be a long class. So when we measure voltage, Grim, thank you so much for gifting 5 community gift subs. Really appreciate it. Thank you.
I don't know half of you half as well as I should like, and I like less than half of you half as well as you deserve.
You're very, very, very kind. Thank you, Grim. Is it like using a galvanizer?
71
Night
years
talk.
is far too short a time to live among such excellent and admirable.
You had me learning. I'm glad, Father Farron. Welcome in.
I don't know half of you half as well as I should like.
Thank you, Bog. Thank you, Grim.
As well as you deserve.
If any of you guys got the gift subs, please enjoy them to your heart's content. We have a lot of physics kind of ones and lab rats. So if you guys don't know, my name is Tofu, Tiny Talk Like Tofu, and my whole kind of setup stream is called Tofu's Laboratory. And so anyone who has become a subscriber has now, against their will, become a Tofu lab rat. And I promise we only do minor experimentations to newcomers. Welcome in, everyone. And thank you so much for the gift subs. Really, really appreciate it. Thank you so much. Now, before I get too distracted, when we measure voltage, like I said, measure across something. But current, let's think about what current is, guys. Current is the flow of electrons. You're measuring current through something. And so if we wanted to measure current using this guy, we would switch a few things around. But we would actually quite literally place it into our circuit in the middle of the circle. So what I would do is I'd redraw all of this. In fact, I'll show you. I would measure voltage like this. That's the symbol usually for it, a little circle and a V. And if I were to put a current meter, something called an ammeter technically, it's just a circle with A. Again, I think this is American standard notation. I'm not sure. But like I said, every nation has their own little twist and version to it. And that's okay. Be familiar with whatever your degree or your nation uses. And that is how we'd measure it. Again, so try and remember, voltage is measured in parallel, current is measured in series. And try to think logically why that is the case.
And they call it a mine. A mine!
Jimmy, thank you so much for gifting a gift sub to Electric Tofu TV. That's a really good username. Thank you so much. You're very, very kind, lab rats, for the support. Really appreciate it. You're very, very kind. So I've told you how to measure voltage and how to measure current. What's the last thing I need to know how to measure? Well, since Flukes is Fluke is very expensive. I don't personally use anything too expensive. Sharon, thank you so much for the resub. Welcome in. Really appreciate it. Resistance, exactly. Okay, people are getting a bit crazy. Guys, do you realize that there is tons of questions coming in? Tons of chat, and I'm trying to read all of them. Let's be civil people, please. Resistance is futile. You're absolutely right about that, Elation. Now, we can measure resistance, and we measure resistance very similar to voltage. In parallel, we measure it across a resistor. We need to measure it from the start and the end of a resistor. Kind of makes sense. But a very, very big safety point. Well, maybe not safety. Just like you'll break your stuff if you do this accidentally. Very, very important safety issue. You don't measure it when your current is in operation, when your circuit is in operation. So when you're measuring the voltage across a resistor, you can't measure the voltage across the resistor unless there's voltage going through it. So obviously your circuit has to be turned on. If you're measuring current needs to be flowing. So you do need your circuit to be turned on. However, you cannot measure a resistor when it's in operation. You need to extract it or turn off your system and then measure across it. In fact, pull it out completely. And the reason I say that, it's good practice, especially when your electronics gets a little bit more complicated, because sometimes, especially if your circuit is closed, you could be measuring the resistance from here to here, or there's another possibility. You end up measuring the resistance from here all the way to here, wherever those 2 points are being measured. So there's two possibilities. Be careful of that. Plug out your resistor so that there is no other choice. Didn't we do that a while ago? We did, Bog. I made the mistake when I was building Bob, I think. Was it Bob? I'll show you guys Bob, since we have a lot of new people here. You guys are going to meet Bob. Bob was our first crew robotics project. This is Bob. I did put eyes on him. Say hi, Bob. Don't be shy. Bob is a self-balancing robot. He's a little rough around the edges. New people, you mean forever people. Well, hopefully, if you guys are interested in these kind of streams, more than welcome. I don't usually do hardcore 8 hours of electric physics non-stop. I usually do a couple of hours of physics and then a couple of hours of gaming. I do love video games, and I like video games that have physics elements in them. At the moment, I'm playing through the altars, which is really, really cool. Good physics in there. Maybe we'll play it later today. But we'll see, because I have a lot of physics lessons planned today. I have a lot to get through, chat. Welcome in, guys. Welcome in. I love Bob. Yay for STEM. Welcome in. Hey! I recognize some of those science emotes. Star coming in with the 350 stream streak. Nice. Nice. All right.
And they call it a mine.
Mine. Thank you, Herder, for 5 community gift subs. You're very, very kind. Thank you.
71 years is far too short a time to live among such excellent and admirable hobbits. I don't know half of you half as well as I should like, and I like less than half of you half as well as you deserve.
Thank you so much, Labrats. Really appreciate the support. You're very, very kind. I can learn and watch gaming? Yes, theoretically. I say theoretically because I make mistakes all the time, of course. So, thank you again for the hype train. Really, really appreciate it. I'm trying not to stay too distracted, but you guys are really, really kind with the supports. What we're going to do now is we're actually going to prove Ohm's law. And how we're going to do it is I'm going to build a circuit, this exact circuit, maybe not with 500 ohms because I don't have 500 ohms. I only have so many resistors. So I pulled out a 1 kilo ohm resistor, 1K, 1000. And where's my train of thought here? Yes, and I have a power supply. Look at this. This is how cool I am. I have my own power supply at home. What's really interesting about this and what's really good about these kind of things is to make sure that the power supply has a current limiter for safety. Sharon, thank you so much for another 5. Really, really appreciate it. So many gift subs. Holy smokes on a cracker. Thank you. Really, really appreciate you guys giving so much to the community. It is a big battery. That's exactly what a power supply is. You plug it into your wall and it's a customizable battery. This is what a power supply really is. We have a current limiter. Sorry, I can read. There's the A. I couldn't find it. I don't have my glasses on. Wait, I do. This is going to be the current limiter, and this guy is going to be the voltage supply. The current limiter, I'm going to set it up something like 200 milliamps, even less. Reason being is, let's say I accidentally screw up my circuit, right? It's a safety feature that if the current goes to 200 milliamps, this whole bad boy shuts down. And so your circuitry is protected, you're protected, all of that kind of stuff. It's a nice, simple power supply system. Can you start from scratch? I'm sorry. I will upload all of these videos, but I can't start from scratch, unfortunately. But just a crash course revision. Current is a flow of electrons. We take it in the opposite direction because we didn't know which way current was flowing. Benjamin Franklin got the 50-50 gamble wrong. Voltage is the thing that pushes electrons. The higher the voltage, the more electrons can be pushed. And resistance is futile. It is a thing that's in your circuit that slows the flow of electrons. How's that for crash course? All right, let's design or let's build our circuit. But actually, before we build it, let me move the camera here, guys. I'm going to show you my setup over here. Oh, this is my PC. This is my everything. I'll probably zoom in a little bit. Yeah, nice. So this is going to be the power supply. It's already plugged in. This is the multimeter. So the first thing I'm going to do is I'm actually going to measure the resistance. I'm going to take note of it. If you guys have notebooks, that's perfect. Do I have a notebook is the question. Let me get my pen and paper. My notebook is full. I write a lot of notes, it seems. You'd think I wouldn't. Sometimes my brain lags. Wait a second, let me grab a notebook. Come on, where are my notebooks? I have so many usually. I think I decided to clean up for the stream so that my room didn't look so messy. And of course, let's start a camera fund. I only recently got this camera. This camera is amazing. Like, I can show you a resistor and you can actually look at the lines if you wanted to. So if anyone really wanted to... Okay, now it's not zoom. Come on, focus me. There you go. So if anyone wanted to Google a resistor spreadsheet, you guys could definitely test this yourselves to make sure that's correct. This camera is absolutely amazing, but it would be ideal to have two. Okay, so I have a notebook and we're going to take down some results. First things first, we are going to measure what the resistor is. And the reason why we're measuring the resistor is we're going to prove our theory. I said that Ohm's law is V is equal to I R, and I want to see if that's true. So, once I do my experiment, I need to be able to prove it, you know? So, as you guys can see, it reads 0.99 kilo ohms. That's almost 1,000 ohms. There is a bit of error associated with any resistor. No resistor is ever perfect. But there's also small error associated with a multimeter as well. So if you are very, very pedantic about your percentage errors, you can keep track of it very easily. Now this is a voltage power supply. Let me look around with this. I haven't used this guy in a while. So on. So first things first. I know how to okay. So I'm going to set the voltage to, let's think about it. I'll start at 1 volt. Now, if you are going to do these experiments or demonstrations at home, it's best to do a mini experiment or mini mathematical thing to make sure that you're not passing too much current. Again, remember I said 1 amp is huge. Don't go above too much. A couple of milliamps. By a couple, I mean, let me think about it. A diode dies at around 25 milliamps, maybe. But again, nothing ever really goes above 50 milliamps in electronic circuits that I mess around with. So that's a good safe bet. 50 milliamps. Low. Okay. This power supply is called Verti. It's not too expensive, but it isn't an amazing power supply. It's very good in its range, but I wouldn't say it's like as good as the ones I've worked with in the lab. The ones I have in my experiments lab are. Okay, so we have about 1 volt, which is great. And then a current limiter. This isn't the way you usually do it, by the way, guys. Usually your voltage supply has a normal way of doing it. But specifically for this power supply, the way I set a current limiter is I short it. Called shorting your circuit. Then I set the current limit. So at the moment, the current is set to 800 milliamps, which is really, really high. There's no way in hell we should be reaching anywhere that high. So we're going to decrease it way. So I have it at 95 milliamps. That's way more than enough. I think, if I did my mental maths right. Obviously, I could make a mistake up to 1 decimal place, and that could be an issue. But generally speaking, there we go. And I think, I'm going to test this theory out. We might have to redo all of this again if this happens. But I think an interesting thing that can happen is if I turn it off, it should save everything. It does! Woohoo! All right. So we turn it off. We finish messing around. So our goal now is to measure the voltage across the resistor, and measure the current through our circuit. Those two things. Now, unfortunately, that means we need two multimeters. And if I were to do this with two multimeters, or with one multimeter, it would be annoying. I have to turn off the circuit, turn it on, turn it off the circuit, turn it on, plug it in correctly. Because remember, you can only measure the voltage in in parallel and the current in series. So you'd have to reconstruct it. So what I've done instead, ta-da! I've pulled out another multimeter. Before anyone says, "Oh, Jofo, you're cheating. This is hocus pocus. You're messing with the results." Don't worry. I'm not. I cannot stand the accusation. What we're doing is we're just using two ways of measuring this whole system. So let's do that now. Welcome in, everyone. All hail King Julian is a really great username. Let me just unplug these guys. So these guys use normal power jacks. Let me just get up a second and I'll get my power jacks. Not called power jacks. What are they called again? Cables. Power cables? Or what everyone else calls them. Okay, so this bad boy is going current. Positive out. Positive. Red is usually positive. Black is usually ground. I should have actually talked a little bit about ground. So remember I said that, yeah, let me actually mention it really quickly before. Sorry, chat. I know we're excited to get to the experiment, but it is important to cover ground. Now, where does the term ground come from? In this case, we don't actually technically have a proper ground, but we usually refer to the negative side of our power supply as the ground. It's our reference point. Remember I said when we were measuring the potential energy of a human being, jumping from a stool to the ground is quite literally, in this case, the ground, right? In electronics, we sometimes call it the reference point as well, the reference ground. But there is an important thing to not confuse it with. Some people have jumped in here, which is don't confuse it with something called earth ground. Technically, they're different things. Ground is just a reference point in our circuit, but earth ground is ever so slightly different. And this comes from, well, quite literally what it was before in the past. When you have a lot of flow of current, when you have a lot of potential, and any basic circuitry in your house to be, safe, the way things were connected to ensure that the flow of current would go somewhere safe was quite literally connecting it to earth deep in the ground. And the way they used to do it was a big giant metal rod stuck into the ground. That's where it came. That's where the name came from. Earth ground. There's no trick to the name. That is the idea behind it. And usually you'll notice all your cabling in all safety systems, they will have a reference ground or a ground circuit in place, a little cable somewhere to connect to everything. In electronics, we try to keep everything to one side as well. We try to keep everything to one ground so that things don't get confused and mixed up, which I have done in the past before. I have made that mistake. So it is something that you kind of learn. You learn it in intro to physics. You learn it to intro to electronics and electricity. Then you're like, nah, that's easy. I'll never forget that. And then when you actually build your robots that you're going to take over the world with, you make a mistake and then things get shorted, unfortunately. And current goes where you don't want it to go. Earth and ground is the same word in Swedish. Oh, really? Is it? Ground. Do you have a doctorate? I do. I have a master's and a doctorate in physics. If you guys are interested, there's loads of stuff about me in the About Me page, or there's a few commands. Thank you, Jay. There's a couple commands. But yeah, my stuff is electric grid, batteries, wind turbines, thermodynamics. That's really what I usually talk about as well. Oh, Arhelius, I accidentally I think with the ground issue, didn't I burn my power supply? That little 5-volt power supply? I think we cooked it. So yeah. I'm very good at that. There's something about me in games and in electronics. I don't tend to, you know, test things out properly and things break. Or I don't think it through properly. Very interesting how games and electronics show true personalities. Anyways, that was a bit of a rant about electronics, or about ground, because I did forget to mention it. Let me zoom in the cameras ever so slightly so you guys can see stuff. I know my desk is messy, but that's because I have loads of electronics stuff. So I apologize for that. All right, here we go. Shorting stuff, yes. Speaking about smelly, if you start smelling copper, shut everything down. I know that you guys can't smell everything through Twitch, but safety first, all that good stuff. If you start smelling metal, shut things down. Yes, exactly. Get the sniffers. Okay, so here we go. I'm going to plug. This is going to be my current. I'm going to plug it into COM. Oh wait, this positive port, it goes in milliamp, then the COM. Will go into the resistor. Let me get my crocodile clips or my alligator clip. We had this discussion before. Sorry, I have just a big box of magic tricks here that that I have on the side. I'm going to show you two bad boys here. Twitch stream. All right, check these out. So there's two kind of clips. I don't know what they're called. Oh, so you call Cayman clips, is it? So the way I was taught was this guy. Look at his teeth. This guy. Oh, sorry, the camera's a bit weird for me. I don't know where to point it. This guy's called a crocodile clip. Okay, it won't hurt if I put my finger in there. Well, it does hurt actually, but it doesn't pierce my skin. This guy is called an alligator clip to me. As you can see, his teeth kind of go over and he's a little bit extra sharp. I will not be sticking my finger there. That will hurt for sure. So those are the ones. Electronic devices are running on smoke. If the smoke gets out, the device stops working. So yeah, so that's the way I learned them. These are crocodile and these are alligator clips. That's the way I've learned to use them. Of course, every country, it's not even a country actually, every lab group will call them differently. So it just depends on your lecturer and your teacher. See you later, alligator. The alligator clip has overbite. Yes, but I think that's actually opposite, right? Does anyone know anything about alligators and crocodiles? Can anyone confirm or deny who the overbite, what the overbite is for all of them? Oh, I forgot to write down my resistor value. It was 990 something ohms. Don't have the decimal place for it. Okay, and then we close the circuit with the next. Nice. Okay, so what I'm going to do is I'm just going to turn this on and I'm going to test that the current works. I'm going to angle it towards you guys. This is the ammeter. What I've done is positive into the positive port, from the negative into the resistor, from the resistor back to the circuit. What I have done is basically what we had on the whiteboard, which showed that the voltage source was connected to the ammeter and then to resistor. It actually doesn't matter the order, whether the ammeter is before the resistor or after the resistor, because the current that's flowing is going to be the same before the resistor and after the resistor. There can't be more or less current. You're not splitting the circuit anywhere. There's nowhere else for the current to go. You're defying the laws of physics if it changes. All right, let's turn on the power supply. Okay. Good readings. I'm just going to get the right range though. So that's 0.99 milliamps when I supply 1 volt. Let's do a bit of mathematics really quickly. So V is equal to I, or V, 1 volt, divided by 1000 should be 0.001 amp, which is 1 milliamp. Ta-da! Very, very crude mathematics, very, very quickly, just to make sure. Is that Kirchhoff's laws? We're not getting to Kirchhoff yet. We will cover Kirchhoff. That's for potential dividers. But this is just Ohm's law we're doing. Oh, you meant the order of the stuff. Is that what you're referring to? I would still say that's just kind of electricity 101, even before Kirchhoff. Okay, so that works, which is great. And the last thing we'll do is we'll also measure the voltage. So I'm going to switch out one of these ports here. Because it's a multimeter, there's too much going on in the multimeter. It has an ability to measure milliamps, ohms. It has a potential to measure volts, and something as high as 10 amps. Now, I never use it, but just in case, let's turn on our circuit again. Whoop! Sorry, I just want chat to see the measurement that I take. It's going to be voltage. Something around the area. Just note, by the way, sometimes your readings will have V squiggly line or V straight line. And we're definitely looking at V straight line. If you're confused about this, let me just remind you that straight line is something called DC current, direct current. This is all that we're going to do today in today's session on the front page. But there's another type of current called alternating current, AC. That is where the band name AC/DC comes from. I had to think about it there. It comes. I'm assuming that's where they came from. They came with up the name. There's two types of currents, DC and AC. For today's stream, we will only be doing DC stuff. So make sure when you're doing all your measurements, it's the straight line or dash line sometimes. Okay? Voila! Would you look at that? Our current is 85 milliamps and our voltage is 0.85 volts. Okay, let's write that down. We have a result. So we have 85 milliamps and 0.85 volts. Okay, next thing we're going to do. I'm going to increase this voltage ever so slightly. So 1.336. Look at that. Our current has changed. It is 1.34 milliamps. And our voltage, let me get these probes across the resistor, is 1.34. 1.34 volts. You might be suspicious and you might be like, Asa, thank you so much for the sub. Really appreciate it. Thank you so much for the PP contribution as well. You might be very, very suspicious and you're like, hold your horses. 1.36, 1.34, really damn close, aren't they, chat? Why is that? Does anyone have an idea? Why is the voltage source going across almost all of the resistor, number one? And number two, is all of it going across the resistor? Are we losing some stuff? I say it in such a voice that obviously, you know, there's a hint already. Electrons go burr. That's a good answer for everything, honestly. That's basically quantum mechanics explained for everything. Yeah, there's resistance in the wires. There's resistance in the power supply. In fact, we usually, no power supply is ideal. There's all of these little things. But mostly, almost all of the voltage has to be dropped across all the resistors in our circuits. And in this case, the only thing in our circuit is the resistor. So all of it has to be dropped across it. This is kind of Kirchhoff's laws coming up again. I know sometimes people pronounce it Kirchhoff, but I will refer to it as Kirchhoff because I've been corrected on it by some German-speaking people. So I'm trying my best. I'm trying my best to be appropriate in saying the correct name. We're close enough to the correct name. Let's increase our voltage again. And we are going to measure that the current is 2.13 milliamps. And the voltage, let's measure our voltage across the resistor. Oh, it shot above. That's okay. That's because my range was at 2 volts. Now I'm going to increase the range to bit higher, 2.13 volts. Wow, I can't actually believe how good it is. The results are shockingly very good. Badumts. Usually there's a bit of source of error, but actually the results are brilliant. Very suspicious. Very suspicious of them. Increase the voltage a little bit. We're going to increase this to 3.09 milliamps. And this guy is going to be... Now, my ultimate goal here is to draw a graph. So chat, how many points do you need to draw a straight line graph? A trick question. 309 volts. 2, exactly. You only need 2. As a person who went through their PhD defense, don't do that. Yeah. Obviously, the more points, the better. In my lab, when I teach my students, 10 is really, really good. 6 is bare minimum for something decent. That's my personal rule of thumb. There is no correct answer to this. Everyone is different. 3.9 volts. Okay, we got slightly different answers this time.
Meat's back on the menu, boys.
3.9 volts and 3.91 milliamps. Thank you, Herder, for the 100 bits. People are usually shocked when they find out I'm not a very good electrician. Fair statement. Fair statement. Thank you, Herder, for the 100 bits. Thank you, everyone, for the subs and for the gift subs. I really, really appreciate it. It's very, very kind of you to support the stream this way. All your monies go towards electronics and towards my bunny. Speaking of the devil. I have to supervise her. She's allowed in the room when I'm not doing soldering. I've left the door open, so if she wants to come in, she's allowed to. When I solder, I don't let her in, even though my room is ventilated. It's a very small bunny. I don't want her breathing any of the stuff in, just in case. Just in case. 4.52 milliamps. And the last voltage reading, I have 6 points. We're going to be lazy on Twitch. Voltage, it is 4.51 volts. Nice. All right. Well done, chat. Now, you might say, Tofu, how can I do this experiment at home? You can't. Not without a voltage source. You do need to invest in something like this, which isn't fair. But what you could do is you could grab a couple of batteries to measure across resistors. But again, you need resistors as well. And you definitely want something high. I used 1 kilo ohm just to be safe because I didn't want high current. So from a perspective, even though this experiment is super, super easy, it's actually very hard to perform without good equipment in your house. So I should have done it again for today's stream, but the ideal experiment to do at home instead is the potato battery, which I do actually have a full YouTube video about. If you guys want to build your own potato battery, I have a full educational tool about it. Maybe not necessarily how to construct it and everything like that, but I teach the educational aspects of the potato battery if you're Professor Proton. Yeah, Bog, I saw a bunny in the pet store as well with normal ears. I was there with Nate and we were like, that bunny has freakishly long ears. That bunny's not okay. And then we realized we're just warped because we're so used to Bambi's ears. Stash an AA battery in a potato. That's pretty sound, yeah. So the next step that we're going to do is I have a bunch of results. Here, I took down the voltage and the current and we're going to plot it. We're going to plot it to prove whether or not Ohm is correct. Was George Simon Ohm correct? I think that was his name. Or was it Simon George? Forget which one it is. When you say normal ears, I picture a bunny with humans. Maybe she'll come down. I do have a treat jar down here. I'll shake the treat jar and see if she comes over. What I might do is get myself an iced coffee really quick and go for a pee break. Omega lol, that's right, that's Omega. I was always wondering if I should do the physics of memes or whatever it's called. You know, explain what the physics symbol means for kappa, for omega, for alpha. beta. What other symbols are there that we use? Giga Chad, Giga. Wait, do we use gamma in slang? Mu, nu. I've never heard any of those used in slang. Gamma is equal to game. Does it? Sigma, I've heard, yeah. I've never heard of Charlie or Gamma or Tau, any of those being used in human slang. All right, I'm going to go to the bathroom really quickly, grab myself a nice coffee. When we're back, we are going to plot this and see if it works. Let's see if we can prove Ohm's law. I'll be right back in a couple of moments, chat. Everybody who's been here from the beginning of the lesson, make sure to stretch, do a few jumping jacks, grab yourself some water, pet your bunnies. If you have bunnies, pet your bunnies. Back in a couple of moments. My rabbit and I have decided to leave planet. Hello, I'm back. Emilio Horseman, welcome in. Harold, hi guys. Welcome in, welcome in. Sorry, chat is moving a bit quickly, so sometimes I do miss messages. I apologize for that. I checked up on Bambi. She is doing her Shawshank Redemption cosplay at the moment. She's very, very busy at the moment. How do I zoom? Bit of light mode going on here. Prepare for flashbang. I'm going to change screens soon. Just prepare for flashbang, okay? I take no responsibility for this. Whoosh! She's digging a tunnel behind the poster. She's digging a tunnel in her tunnel. She has a project that she's trying. I don't know why she's so convinced that this is the tunnel she needs to dig. I've given her dirt. I put her outside. I give her things to bite and dig into. No, there's this one area of the carpet that she must dig into. I don't know what's going on with her and that carpet, but whatever it is, you know what? I'm not judging. Every girl needs a hobby. Every girl needs a hobby. Just saying. Just saying. My camera over here, because I think I'll be blocking most of the stuff that I'll be showing you now. Let's look at this bad boy here. Nice. Julio. So what I'm going to be doing is I'm going to be basically plotting in Excel. My ass! I know. Be prepared for flashbang. There was a warning. I did warn chat there was going to be a flashbang. I want that there, and the slope to be there, then the x has to be current. X is always plotted first. Okay. So, this is capital I in brackets milliamps. And this is capital V brackets capital V. Spreadsheets! Yes! What if the hobby's mass murder? We don't do that around here. Hi, Sol. Welcome in. So, let me turn it off, actually, my power sources. Spend too much time on this. Sorry, we don't feed too much power out of this. Eek, Excel hide. I will not stand for Excel bullying. Excel is amazing, and if you bully Excel, you just don't know how to use it. I said it. I said it. Anyways, before anyone comes and haunts me, let's put down all our results. First of all, I'm going to put down the list of current results. 0.085, 1.34 milliamps, 2.13, 3.09, 3.91, and 4.52. Oh yeah, huge amounts of data, yeah. I used to do everything in Excel, and then I started working with the Irish Electric Grid and frequency generation, and there was like a bunch of data for every second that's ever happened in Ireland for over a year. And so my Excel just crashed trying to open the data. Obviously my PC wasn't the greatest when I was a PhD student, but my PC quite literally crashed and the file couldn't be opened. So ever since then, I that's how my whole Python career happened, actually. Why Python was the language I used. I know people give me shit for Python as well, but I had to be able to extract the data somehow. Okay. So this is all the data that I collected during the stream. You guys were there. You have evidence that I did not make up these results. We measured them. We measured the current in series in our circuit, and we measured the voltage in parallel. We measured it across, not through something. Remember, chat, you measure voltage across something, not through. If I ever hear you say you measured the voltage through something. Now, let's plot it. Here we go. Oh, I must have mistyped something. Yeah, I mistook this one. Here we go. Oh my goodness. Look at that. We'll do some axis titles, trend lines. Anyways, before we get to that, there's a mistake here. An ever so small mistake. I'm going to add a trend line. And we're going to display equation on chart. And looking at that equation, eyeballing it right now, I can see that we have a wrong answer. Does anyone know what the mistake is? I mean, it's a small mistake to fix. It's very easy to fix, but... Recommend warning. Is there anyone with beautifully functioning working eyes and can spot this? What the mistake is in our graph? No, not rounding, no. Rounding is okay. It's okay to have rounding. Look at our slope. Our slope is 0.997 ohms. Do you remember what we measured the resistance to be? No, not labels, not chart. I'm skipping ahead. What was the resistance meant to be, chat? Do you guys remember? Do you remember what we measured the resistance to be? 1,000 ohm, 1 kilo ohm, exactly. We're off by a factor of 1,000 because we actually took down the units in milliamps. If we wanted to really make the graph proper, if we want to be pedantic about Ohm's law, there's other conversions. We need to change current into amps. So all we have to do is divide it by 1,000. So we take this result, divide it by 1,000. Drag it down. That's what we plot then. Plot current against voltage. Again, you don't have to replot it. You can just convert your results if you've been keeping track of your units. But I'm being tedious. The equation on draft. Excellent. All right. So let's do a little bit of cleaning up on this graph. Of course, we're scientists. This experiment will be titled Ohm's Law by the amazing Tofu. I don't know who that is, but I think that sounds right. On the y-axis is voltage. Voltage in units V. Usually in brackets we put the units that we're in. And this is current in usual units amps. Now you could have kept it in milliamps. It's completely fine. You would have just needed to convert the resistor as well. But again, it's fine. So there we go. Now look at this equation. This is really interesting. I'm going to write that on the board and we're going to do some maths on this. Y is equal to M. Ready, kind of spoil the plot there. 997 plus 0.0. Okay. So I'm gonna teach you a little bit about linear algebra. Who's excited about that? And suddenly loads of people leave the stream. I'm going for a break. Bring up the. No, no, Dasbig, that is very dangerous. Please don't do it. Welcome in, welcome in. So let's look at this then. I'll move on to the next part of the whiteboard. Let me get a marker. We've plotted the graph. Had voltage here, current here. Now, an equation of a line is a very classical algebra, but also it is used in any science. Honestly, I can't think of a science that doesn't exist. Things like obviously physics, chemistry, biology, anything statistical. So all the social sciences, we use this as well. I'm trying to think of other stuff, mathematics, business. Oh, business models. This stuff is in everything. There's absolutely no way that this isn't useful information, okay? And a straight line equation is y is equal to mx plus. Now, what do these symbols mean? Y is the data on the y-axis. In our case, that's our voltage. X is the data on the x-axis, which is current in our case. Now, C and M are two things that the Excel sheet gave to us, which were numbers. Now, M stands for, and again, I think maybe depending on which country you're from or what school you went to and things like that, your symbols could be a bit different. You make that constant a bit, okay, there we go. So Grim is saying that for him it was a B. Zarda says it was A. For me, it was always M and C. For me, all my life in physics, in different lectures, it was always M and C. So it's different for everyone. It just depends on whatever education curriculum that you went through. M stands for slope. Slope is how steep your line is. For example, this line isn't steep at all, while this line is very, very steep. That is what that M represents. It's how quickly the X and Y ratio change. C is a constant value. It's the intercept value. It is just a number on the axis, if I'm not mistaken, on the y-axis, where your line intercepts. In most physics equations, the line usually goes through zero, but for the love of God and everything that is holy, I don't know why I went religious there, do not force it to go through zero. Do not make it go through zero. That is, you are forcing your data into a position which you didn't find the results to. This is good practice in, I'm going to say physics, but also I'm going to assume in any field of science. Do not force your line to go through zero. Yes, they should go through zero. That's what we're trying to usually prove. But by forcing it to go through zero, you are altering your data. So do be careful. I highly recommend you don't do it, okay? Rise over run, exactly. That's another way of putting it through. Now, in our case, that should be zero or as close to zero. But again, just don't force it. Usually, you have to do a few extra clicks in Excel to force it. This means that when we plot all our Y data and we plot all our X data, we can extract a straight line equation, which is what we got in Excel. It's told us Y is equal to, sorry, let me actually rewrite it here. Excel told us Y is equal to 997x plus, what the number is, 0.00. This is what Excel told us. Very, very simply. Like with like. This is our slope. Oh shit, I shouldn't be using yellow. Sorry. Yes. Blue. This is our slope. M and this is our intercept. It's really, really close to 0. It means we have a really, really good result. While this guy here, our slope, is our answer. It's our resistance. Why? Let's look at the equation again. V is equal to IR. Let's sub in what the equation of the line is over it. Y is equal to XM. I just switched the order, it doesn't matter. Plus C. V is equal to Y. I is equal to X. The slope must be equal to the resistance. What is C equal to in our equation? What is C equal to? C is the constant, yes. But what in V is equal to IR, what is it equal to? Coffee. Good. That's a good answer. No, not resistance. No. Resistance is M, our slope. So we have this matched up. We have this matched up. This matched up. Where is this guy's matchup? Fudge. Errors. It's meant to be 0. We got it pretty damn close. Very, very close. 0.0046. But it's meant to be 0. Okay, it's our intercept point and it should be 0, but we're not forcing it to 0. So there we go. So this means that our resistance via our experiment is 997. When I measured the resistance, there was an error in the measurement because I could only show so much decimal place. This is a resistance experiment. Resistance measured was 9. Now, the reason I write 0 here is because I didn't actually have another decimal place in my voltmeter reading, in my multimeter reading. So there is a source of error here, which my point I'm trying to make here is that we could have actually been super, super accurate. It's unfortunate that my multimeter wasn't able to give me another decimal place to be a little bit more accurate. The point is, though, we were able to prove Ohm's law. Ultimately, all of this is over-explaining. I did over-explain. I did try to kind of give a more understanding explanation of it. In fact, any equation in physics can be, well, okay, this is an exaggeration. Any linear equation can be extracted and be experimented with. Let's look at Newton's law. Second law, F is equal to ma. That's Y is equal to mx plus c. If we plot force on the y-axis, if we plot mass on the x-axis, our slope will be a acceleration due to gravity. We could calculate the acceleration due to gravity with a setup of force and mass. We could, I'm trying to think of other equations that have linear relationship. You can grab any equation in physics and do really, really interesting things. You can plot and graph. And if you can plot it, 2 seconds, the door knock. Sorry, was I muted? Apologies. We could have proved Ohm's law with just one measurement. We could have done a calculation very simply. We could have measured the voltage, we could have measured the current once, and then calculated the resistance, and we would have gotten a value. So what? You only measured it once. There's so much error associated with. Well, we do it again. We change the voltage, we change the current, we get the same value for the resistance. Again. But by plotting a graph, we actually reduce error. If we plot an increasing voltage and if we plot the increasing current, we get the slope of that relationship, we get a very good answer with minimal error, number one. And number two, a consistent proof as well to show the direct relationship. Because then it shows that it's not just true for one value, it's not just true for two value, it's actually true for 3, 4, 5, 6, how many values you take. It's really, really important to be able to do that in almost all fields of science. If you can show your experiment with just more than one demonstration, more than one mathematical measurement, it shows that your law is, well, proven. We say it's proven. Well, laws are a bit weird. The reason is, how should I say this? Laws are weird. You've noticed that there's laws in physics and there's theories in physics, and what's the difference between them and things like that. Laws usually don't have a good enough explanation. It's just known to be true and never disproven. Ohm's law holds to be true. Another law is the law of refraction, the law of reflection, all of these things. We might not have the best explanation, especially at the time that it was developed, by the way, but no one can disprove it. No matter what you do, it's still true and it holds to be true. There are exceptions to the rule when you tweak the conditions, but again, the conditions are put in place for those laws to be upheld. So, you know, just to be wary of that. I don't know. I think it's kind of the opposite, I would say, bogus. I think Loss thought, yeah, because we have better explanations a lot more now, and we have theories. Most of the time, now things are explained. But back in the day, when we were just discovering the world or trying to understand the world, a lot more laws were done. Yes. So, for example, Newton's stuff was laws of gravity, while Einstein's explanation theories. Again, there's a lot of dispute about this. Bear in mind that what I say is an opinion, by the way. A lot of people seem to dispute a lot of this, and there's a lot of contradiction in information. So what you believe perhaps could be a little bit more accurate. You're more than welcome to go. I think it's slightly the other way around, bogus, but I'm not sure. Again, so many people argue about this. The reason I bring it up is that physicists argue among themselves. So you know, it's hard to really know for sure what's going on. Also, I have my desktop audio. Apologies, I had nice Witcher music background. I'm just checking what my package is because someone knocked on the door. Oh, cool! It did arrive after all. So reduce, reuse, recycle. I bought a textbook for like £5. Really old textbook, but like £5. An old edition of Electronic Devices by Floyd. Floyd is like the father of electronic devices textbooks. It is very outdated. I think this is 1990 something. I'm so sorry, by the way, if any of you guys were born in 1990 something and I'm calling you outdated. Let me see when this was published. But generally, the fundamental physics has not changed since, so it's okay. This is published. Can't find where it was published. Anyways, it's secondhand. It's pretty good quality. A bit rough around the edges, but I really like it. Textbooks are quite expensive. Drop my little break from Ohm's Law for a little. But we did finish Ohm's Law. We have one more thing to cover in a very hardcore, which is power. We'll talk about power in a second. Yes, I am Lunar. Gen Zs are outdated. Tofu 2020. That's not what I said, lads. That book had potential. Then you put it on the ground. I know, I did put it on the ground. I don't have any more space. I have so many boxes of gadgets and gizmos for today's stream. So, yeah, I'm running out of space. I need more tables. Yeah. I apologize. You are welcome to send me the sailboat. No. The sailboat is background here. Sorry. One of my projects. We're trying to develop an autopilot system. We stopped it for a while, actually. I got distracted by Bob, my robot. Where's Bob? So, again, I'm showing off Bob. Robert, otherwise known as Bob. Other known as, with the ultrasonic sensors, as home budget Wally. Got distracted by him for a while. But yes, we were working on some step motors and servo motors to see what was the best input. But I need a sensory input for the autopilot system. I need not a gyroscope. I need an implanted compass. Walby. Does it have Arduino? Yes. That is so unfortunate, Bill. Yeah, like when I was in first year, I bought a few physics textbooks, never used them again. Do you know what? Do you know when I use textbooks now? As a lecturer, to make notes and to come up with problems. And like, yeah. After all my years in physics, I never used a textbook as a student. I only used textbook as a lecturer. So that's why I bought the electronic devices, is just to have a textbook as reference. Because I know that you can get access online and you can pay like decent money for it. It's cheap to buy an ebook in comparison to a physical copy. But I don't know. I struggle to study via ebooks. I don't know. Maybe I'm being very weird about this, but I can't seem to learn as well as I used to. Can't you repurpose large books as a doorstop? Oh, don't worry. For me, I give it to Bambi. Bambi eats all my books. She has a big thing for Feynman lately. She's eaten Feynman's textbooks. I have the same weirdness. Excellent. I'm not the only one, so. Where you can actually flip the pages. Yeah, I don't know. Aren't all PhDs scientists? I think so. Well, you can get a PhD in history and languages and stuff like that. I don't know if they're considered, that could be considered being a scientist. Obviously, they have a doctorate and they're very, and they did original research as well. But I guess technically it's not a science. Feynman is just too flavorful. Yeah, she has a thing for Feynman. He is a fine man. So if the adage, you are what you eat, holds, Bambi has a thing for physics for sure. Right, geek, right? She's busy digging. All right. Indiana Jones has a PhD, not a scientist. Was he a historian or an archaeologist? Because if he's an archaeologist, I think that's a science, no? Correct me if I'm wrong, but I'm pretty sure they have a scientific method and everything. It's like a little bit of chemistry, a little bit of geology, a little bit of Monica on the side. Yeah, I agree, Dr. Prince. I was thinking about that. There are different, like, for example, even me talking about archaeology there's definitely a stem there or a footing in science for sure. I suppose it just depends what you want to take it in. It's a lot of these things are not as black and white as they seem, you know. You can't just paint, well, maybe you can, but a lot of fields, especially nowadays, it's very difficult to just paint a paintbrush your one thing over the other. You know, there's so much interdisciplinary things going on. And usually, you know, trying to think of examples. A physicist, let's say you have all your degrees in physics, but you end up developing some biomechanics aspects in creatures, and you spend a lot of your time working in biology and physics. Are you classed as a biologist or are you classed as a physicist? Well, they'll say, well, we'll put up a new class for you. We'll call you a biophysicist. You know, there's so many divisions now and things like that. Ultimately, I'm going to be very pretentious here and say we're all physicists at heart. I've said it before and I'll say it again. Somewhere, somehow, your degree stems from physics, I'll boldly say. So to me, all of you chat are physicists. Fellow companions, fellow comrades. Oh no, there's a lot more, Pudge. That's only a tiny, tiny little field. It was my only first project and I didn't understand a lot of it. I am not a robotics person. As in I don't teach robotics. So on stream I teach physics, but sometimes I end up teaching myself things, or chat teaches me. Does that make sense? So sometimes I take up on projects like the robotics, like the boat thing, and I don't know anything about it. I don't know anything about programming. So what I do is I just teach myself how to do it via stream. That's sometimes what my stream is about, if you guys are into that. We do have rules about the backseating though, because sometimes it can get a bit overwhelming and aggressive. The problem is the aggressiveness that sometimes comes out of it. Yeah, I was going to say, Turin, sometimes as chat as a collective, do you know what my electronic streams remind me of? Do you guys remember Chat Plays Pokemon? It reminds me of that. It reminds me of like the chaos that is created, the good and the evil, where stuff doesn't get done because of contradiction that happens in chat. Yeah, sometimes that happens. Obviously, most people don't have, negative aspects in their bones, but as a collective, exactly. Chat is a very confused hive mind. So sometimes it can get a bit messy. We call that entropy. Oh, I love talking about entropy. All right. Let's talk a little bit to finish this section off. Because I realize I've been streaming for almost 2 hours and in my mind, I should have been done this by 2 hours. I'm still good on time. The last thing I want to talk to you, chat, about. Oh no, I didn't do parallel. Oh my god, I'm so behind. Oh wow. Okay. That's fine. That's fine. More electrical content. What I want to talk to you about is power. Okay? Power, obviously, is an English word that we tend to use. In an English sentence, you would use it as a concept of explaining dominance over one person or one thing over another, right? Now, power is how we define things in physics when it comes to, well, powering your systems. For example, you have power ratings on everything you use. Chat, I think most of you are using your computers or something like that to watch me. Hi, live on Twitch. Front page. I'm teaching people about power. I think you guys are using something to watch me with that uses power to do so. And power is defined as energy over time. It is the amount of energy that gets to you or your system, unit of power, a unit of energy, over a unit of time. Let me explain that really quickly. And I don't know if Naz is here, but my mod came up with a really, really good analogy. It uses alcohol and Irishness, which is great. And I'm going to use this for my students from here on in. And the way I explain power is that you can have a giant, giant battery that has loads and loads of energy, and you could store loads of energy, but it can be meaningless to your system if you can only put out a small amount of energy at a time. And the example that Naz uses, which is really good, is about drinking alcohol, about drinking pints. For example, if anyone here has celebrated St. Patrick's Day, if you're drinking beer out for St. Paddy's Day, and you know that you have to drink 8 pints today, not trying to promote alcoholism, this is just expressing an example here, and you know you have to drink 8 pints because your mates are the way they are. This is something that they do. It is more difficult to drink 8 pints, let's say going out at 9 p.m. and finishing at 2 a.m., than it is starting at 3 p.m. when you're out in the parade for St. Paddy's Parade, then going to the bars and then going out night clubbing. It's a lot easier to drink those 8 pints during the total of the day than it is towards the end of the day in that shorter amount of time. So, power and energy, this whole discussion between them and what the difference between them is that it's the amount of energy that you can compact per unit of a time. So quite literally, the unit for power is joules, the energy, per second. That's the SI unit usually we use for it. There is another unit for power. What is the unit for power, chat? We could actually do the calculation on that, Bogus. It'd be interesting to see how many hamsters we need to power things. Watts, exactly, watts. Now, in electrical circuits, we can actually use a very simple expression. The aspects of power is the voltage and the current. That's E is equal to V. That is another equation for it. Power of our circuit is equal to the voltage times the current. We can extract 2 more equations from this because we're smart, chat. We are the smartest people ever. We can substitute some things. First thing that we can do is I can substitute that V with IR. V is equal to IR times I, sorry. Multiply it out together. That's I squared times R. We have another equation for power. Another thing that we can do is we can sub in for current. V over R is equal to I. Let's sub that in here. E is equal to V times V over R. Clean that up. That's V squared over R. This means that pretty much no matter what your circuit situation is, as long as you've got 2 pieces of information, voltage, resistance, or current, we can determine the power of things. The current power. Very, very useful. And you might be wondering, well, what kind of stuff would we want to know about power in our circuit? One of the examples that I usually teach in first year physics, hi, welcome in, is light bulbs. What is a light bulb? I forget what the symbol is. Arrow sticking out, I forget which one it is. It's basically a resistor that emits light and heat. Don't let the blue smoke out. Yes, we don't let the blue smoke out. But that's what we usually refer to light bulbs as. And when we are given a light bulb, we are given, let me think about this. We are given the power rating of a light bulb and we can work backwards. That means if we know what our voltage source is and we know what the power is, we can determine what the current is. If we know the power and we know the voltage, we can determine what the resistance is. There's a lot of things we can do with that. Why not defining the impedance instead of... Because we're working with DC. There is no impedance in this case. Don't inhale blue smoke. No. We can determine these things. It's a very, very useful thing. And you can do some maths on this if you wish. There's tungsten as well. Another really interesting element that's used. I don't think it's used in light bulbs specifically, but in a lot of resistivity measures called constantine. Constantine is really, really good because that's where it gets its name. It actually remains constant no matter what the temperature range is. It's not. But it can still do a lot of things under a lot of stress. And we use constantine quite often in physics experiments or in electricity experiments. Even in thermodynamics, One of the things that we like to use Constantine for, which is really interesting, is to create thermocouples. You would wrap a copper wire and Constantine together, and then you would wrap another copper wire and Constantine together. So you have basically 3 wires. Make a crude system of this. And you would immerse one couple in a cold icy water, something that you know is a temperature, a constant temperature, i.e. cold icy water should be at 0 degrees Celsius. And then you have the other thing in hot water, in measuring a human body temperature, in something else, you know, whatever it is the thing that you're measuring. And it uses something called the Seebeck effect so that you can actually get a voltage potential difference. You can use this to power things. So temperature changes can be used for electrical power. I've spoken to this before about this on my Twitch stream, but I'll kind of re-mention it again. This is the principle of the thermonuclear devices that are used in thermogenerating nuclear devices that are used in Voyager. So Voyager 1 and Voyager 2 that are in outer space, they use a radioactive material. It's super hot, and outer space is super cold. And so there's a huge temperature difference between those two. And because of this huge temperature difference, you can get a lot of current, a lot of voltage out of the system. And that's how it uses to power all the electronics in its system. The other part about it, though, however, to kind of mention, is that it has a half-life. So all radioactive material have half-lives. And so that is why maybe you've heard on the news that a lot of the electronics on Voyager have slowly been shutting down, that they're... that certain instruments cannot take measurements anymore. And the reason because of that is because the half-life of the radioactive material has been reached. A lot of materials just don't have enough power anymore to function. Bye-bye, Voyager. Eventually we have to say goodbye. The camera is almost down. Was there even a camera on Voyager? I didn't realize there was a visual camera. Nice coffee. Good iced coffee. Bon voyage. Exactly. I think those kind of things are still being used to this day for a lot of Oh, sorry, that's a photo. It doesn't have a video though, right? It doesn't have video feed. So I'm just checking what my lesson plan was for today. Mine. Thank you so much for gifting Voyager a gift sub. Not to be confused with Star Trek Voyager, although a very good Star Trek TV series. Okay, so Ohm's law experiment, do it in the Excel sheet, resistor change current. And the next plan I have is resistors in series, parallel, and combination. Ooh. Hopefully you'll discuss this soon. Oh. I see. No, unfortunately, Tech, we won't be doing that. The RTG on Voyager was 470 watts. That's a lot. When were you taught about this first? The Voyager stuff that we're ranting about, or this? The Voyager stuff, I was never taught that. I just learned it, or like I read about it myself. The electricity stuff. So I did science for my junior cert and then physics for my leaving cert. So I would have done this in junior cert level. That is high school? Middle school? I think that's middle school in American terminology. Basically 12 years old. 12 years old, I think, is roughly is what I'm thinking in my head. That's preschool in America. I think, okay, that was a joke, was it? I'm not even going to just ban that, by the way. I'm just going... Sorry, remove that comment. I'm just going to ban that completely. We don't want that kind of talk around here. Sounds about 8th grade. 7th, I think, if we're looking at 11th class system. So in Russia, it's 11 classes, from 1st class to 11th class, if I remember correctly. Am I right in thinking that? I think I am. I'm happy to be corrected on that. If we're looking at grade systems, then this would be 7th class. Yeah, a master's and a PhD, Vic. You're back home, Harry? Okay, so I've talked to you about V is equal to IR. I've talked to you about power, all that good stuff. The next step is to talk about things in series and parallel. That's the next thing we have to talk about. So, circuits exist in both series and parallel, or systems exist in series and parallel. And I've kind of talked to you about series and parallel already when I talked about measuring things. So let me, bring up the camera a bit more. Let me clean up the board a bit. Now we have room to work with. Really, I need just a giant wall of blackboard. That would be really cool. Actually, that would be a cool thing for me to invest. A whole wall, just be a blackboard. That would be class. Quality streaming, quality content creation. Okay. Second to dry really quickly. So now what we want to talk about is something called, what's the word? About things about series and parallel. Okay, so what does that mean? Series is quite literally kind of hidden in the word. It's something put in one after the other. When we have one resistor, then in the train track another resistor, and the train track another. So let's say this is our voltage source. We have two resistors. Our voltage source is 5 volts. And let's say this guy is 200 ohms and 300 ohms. Now we have a bit of a complicated circuit. We have two resistors, we have a voltage source, and we kind of like, oh damn, what's going to happen here? What is going on here? I'm Mord, welcome in. So when we have resistors in series, the way we deal with this is that we add them up quite literally. If we want to know what the whole system is, right? The total resistance is resistor 1 plus resistor 2. Hopefully your maths is really good. 200 ohms plus 300 ohms, 500. We know our resistance is 500 ohms. We know that our voltage is 5 volts. We can use V is equal to IR, rearrange the equation, V over R is equal to I. Our voltage is 5 volts. Our resistance is 500 ohms. We can now calculate that our current in our whole system is 10 milliamps. Resistor 1 plus resistor 2 obviously equals resistor 2. Clearly. Another thing is true. Or another thing that can happen in our circuit that can get a bit confusing. We have resistor here and another resistor here. Dun, 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 dun! Oh boy. In Germany, it's U is equal to IR. Why in America? I don't know why it's in America, but here we use V because it stands for voltage. We mentioned earlier that it can be U for other people. And that's okay. It's okay to be different. I'll take the path of least resistance. It does though. So let's say this is 200 ohms and the other one is 300 ohms. 200 ohms and this is 300 ohms. Okay. Well, then I guess you got your answer there. U does kind of look like V, especially if you write it fast. That's true as well. So there's not too much confusion. So we have 200 ohms and 300 ohms. Now we can't add them up. Now think about this logically as well. Remember what I said current is when we were talking about pretending current is water flow. If current is water flow, we have water flowing from here at 5 volts. And suddenly it comes here. And it actually has two paths to flow through. It can flow through the 200 ohm resistor and it can flow through the 300 ohm resistor. And you might be thinking and sitting there, it's like, well, where does the current go? The analogy that I tend to use is if anyone goes shopping, grocery store shopping. If you go grocery store shopping, there are lines, grocery stores, and there's, what are they called? The belts where you put your grocery store. And there's two options. There's one where there is a very slow old couple trying to get their groceries out. And then in another aisle, there is a couple of people there, but they're, putting things quickly and they have a lot less items to put on. Which path do you choose? You can choose both. And in fact, you need to kind of do a bit of mental maths. You're like, one old couple or three really, really fast people? Which one do I take? You need to kind of gamble. It's not just an easy choice that, you obviously go down the fast lane. Sometimes you need to go through the slower lane just because of the position that you'll be taking. But sometimes you want to go through the fast lane because it will get through a lot quicker. And obviously, we've all been in this boat when you accidentally mess up and some disaster happens where someone, as it goes through the checkout, something was lost, the tag was lost, and they have to wait at the line, and your gamble didn't pay off. Anyways, that's a bit of a side rant. The point is that current is actually going to go flow through both of them. And people say current flows through the path of least resistance. Although true, it's a ratio answer. Current is going to flow through the 200 ohm and 300 ohm, but ever so slightly more to the 200 ohm. How much? It's basically a ratio of it. Now, we'll get to that later because I'll be talking about potential dividers and current dividers. We'll be talking about Kirchhoff's laws a little bit. But just to kind of remind you on this, or express it, if we wanted to calculate what this total resistance is, let's say this is confusing. I'm like, stop. What is the total resistance of this? Let me redraw this circuit with one resistor. Tofu, can you tell me, what does this circuit, what do we need to do to this circuit to make just one resistor out of it? That's okay. I'll tell you how. We calculate the inverse of the resistor. 1 over RT is 1 over R1 plus 1 over R2. If you do a little bit of cheeky algebra, that's the same thing as R total is equal to R1 multiplied by R2 all over R1 plus R. You can trust me on this, or you can do the little bit of algebra if you wish as a little mental practice. Let's sub in all our numbers. RT is equal to 200 multiplied by 300 all over 200 plus. Does anyone have an answer for that? Anyone have a calculator ready to go? Self-serve for the win. 120 ohms. I know roughly that that's correct because it's less than 200. I don't know what that means. Okay, so if we were to redraw this circuit equivalent, we have 120. V is equal to IR. We can calculate what the current is again. V or R is equal to our voltage is 5 volts. And our resistance is 100. If anyone can do their mental maths or remember it, 5 divided by 120, we should get a current answer, and we can calculate what the current is again. To circuits in university. Hopefully not too I speak sometimes. Hopefully not too traumatizing then. Whiskey Jack, welcome in everyone. Sorry, I'm blocking actually the board where I'm talking about this. 5 volts divided by 120. I should do this in my head, but I can't because I'm too tired. Calculators. 5 volts divided by 120. Where is my calculator? 41.67 milliamps. That sounds about right. You're in the right trajectory. Perfect. So as you can see, something interesting happened, chat. Hold your horses. Hold your horses. Earlier, we had, let's say, one resistor here. That was 500 ohms, right? We added 2 resistors together. There were 500 ohms. That's a lot of resistance, right? When we put 2 resistors in parallel, our resistance was even less, our RT was even less than 200 ohms. By putting resistors in parallel, we increase the current in our total circuit. Isn't that kind of interesting if you think about it? Putting resistors in parallel increases our current. By giving current more options of where to flow, by giving current more choice, it has less resistance in total. Which kind of makes sense if you're thinking about pipes and rivers and things like that. Very, very important. Witchcraft. Burn tofu at the stake. Take them out and you increase it. Oh, take resistors out completely. True, true. It would be a very bad thing to take out resistance. By the way, again, a highlight. If you ever are messing around with electronics, if you are messing around with any electronics, with bits and bobs, make sure to always put a resistor in series just in case. Don't do what I did and make things explode accidentally. Thank you, Thunderpaws, for your pride. Really appreciate the support. Thank you. Why did I get bumped? I'm more interested in the voltage dividers personally. We'll get there, Wombat Hole. That is plan of my lecture today. Take care not to let the magic smoke compound. Listen, if you... Okay, no, I'll take that back. I was going to say, you're very talented if you burn a resistor, and I remembered a student. No, never mind. You can definitely blow up a resistor. Do be careful. Don't do silly things. Alright, my coffee's finished. Have some water. Gotta stay hydrated. I'm very tempted. I'm so scared to do it, Boom Thinking, but there is a thing physics lecturers do, which is to demonstrate the voltage limit for capacitors, or like putting in reverse and what can happen. And you blow up the capacitor. Don't do it. But I know that a lot of physics lecturers do this as a demonstration for their students. And I love to blow things up in the lab to make things exciting and interesting. But I'm worried about that. I don't know. For me, I'm too worried. Yeah, no, you're not wrong, Dacris. You're not wrong. It makes the room stink. That copper smell, that smell of burning copper terrifies me. If you buy any pieces of electronics and you open the packet, the fresh smell of electronics just smells like copper. but I literally, like, my heart races when I smell it. I'm like, oh, something's burning in the house. Electric burn. So yeah, the magic smoke, exactly. So the next thing I want to talk about is combination. Combination is the next step. Where's my cloth? Bambi, take it. Does she run in here? Not lately. Coming into the room and just taking things. Oh, it's here. All right. The next step we're going to do is a combination. Now, combination, quite literally hidden in the name. We're going to put those two things together. We're going to put series and parallel. So let's do a bit of stuff here. So let's do a voltage source. Again, same thing, 5 volts. I'm going to put resistor and then 2 resistors in parallel. Dun, 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 dun. Dun, 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 dun. Not sure why I'm adding a musical aspect to this, but I am. We'll say, what will we say this is? We'll say this is 250 ohms. This is 200 ohms. And this is 3. So I kind of already did it, but I probably should have highlighted in words what I was doing. Use a soldering sponge. Yeah, no, I don't think that's going to work. The thing that I didn't mention before is that what we're doing is we're drawing equivalent resistors. It's not like physically when we're building these circuits, we physically have 2 resistors or 3 resistors and stuff like that. What we're doing is we're applying some classical Ohm's laws, classical mathematics here, to determine what the resistance is in our circuit to make our calculations easier and to know what the total story is in our to know what the total current is in our story. So what we're going to do here is we're going to work with parallel. Usually speaking, we work with everything in parallel. If you have a really complicated circuit like series, parallel, and then a triple parallel, and then another mess over there, if there's all these things happening, it can get very, very confusing. What I will say is deal with the stuff in parallel first. So let's deal with this. Let's make an equivalent resistor. RT is equal to R1 multiplied by R2 all over R1, 2. Sub in our numbers. 200 ohms. Marker's dying. 300 all over 200 plus 300. I'm going to be a cheat because we actually did this earlier. 120. You can repeat this into the calculator. See if I'm not spouting nonsense. So the equivalent resistor here between these two guys is 120. So basically what we have is we have one resistor in series with another resistor. Remember what the series is? You just add them together. So instead of RT, I should write REQ, equivalent resistance. So our total resistance is R1 plus this guy plus this equivalent. That is 370. We can now calculate what the total current is in our circuit. V is equal to I. Markers are best. Have I ordered some? I think I ordered some. That's just dead. La-di-da-di-da. V is equal to IR. We rearrange the equation. V over R is equal to I. Our voltage is 5 volts. Our resistance is 70. Sub in, we can do a bit of maths. If anyone has a calculator handy, shout at me, chat, what the answer is. $13.5 milliamps. Just trying to do a rough estimate in my head if that's correct. Yeah, that's kind of okay. Yeah, that's in a rough dimension. Welcome in, Gray. There's actually a lot of science communicators on Twitch. One of the things I do is something called Tofu Tech Talk, where I invite Twitch streamers with science backgrounds. If you guys want to scroll, I think you might need to, if you're watching me from the front page, you need to click into my profile. But if you look at the About Me, I have a whole Tofu Tech Talk list with all the links of different people. I've had astrophysicists, I've had people who've worked at NASA, I have biologists, microbiologists, chemists, mathematicians, historians, Egyptologists, musicians. We've had a variety of guests on Tofu Tech Talk. So if you guys are interested in kind of like exploring and finding more science communicators, I definitely recommend. I'm still exploring to find new people. When will your next stream be? Tomorrow. So tomorrow I was going to do passive filters, which is a little bit more advanced than what I'm doing today. But let me think about it. Will I do passive filters tomorrow? I haven't really taken up robotics again. But yeah. Yeah, I'm doing a stream tomorrow. I'm not sure at all. No worries, no worries. If it's wrong, it's only a mathematical mistake. We're pretty close to the end. Didn't we do passive filters? So what I did, Grim, was I just explained the concept of filters. I just taught you the wibbly wobbly aspect of it. What I wanted to teach about passive filters is the mathematics, but it's quite hard when... Have I taught AC circuits on stream? I know I did a whole bunch of stuff on YouTube, and Instagram, TikTok, but I don't know if I've taught it on Twitch before. You can use fractions if you want. I prefer decimal place. I'm a decimal place fan. I'm pro decimal places. Unless it's pi. If pi is involved, I'm okay with it not being in decimal place. Okay. Now I've shown you all of this. I've shown you combinations and series, and kind of what I want to show you is a little bit of an idea or a concept with something in series and parallel called voltage drops. But I do need to take a little break. I've been standing for a little while. My legs are really sore. Yes, Twitch streamers do have feet, by the way. I know there's a misconception out there that we don't. But, ooh. Rest me feet. We might make a cup of tea as well. Good cup of tea. Oof. But the next step that I want to do is I want to show you something about resistors in series and parallel and where the voltage. There's a bit of drama with resistors are in series versus when they're in parallel. I'm going to open a cafe and call it the Decimal Place. That's a really cool cafe name. Are you a tea or a coffee lover? Both. I love coffee and I love tea. But I like my coffees bitter. And I like my teas bitter too. I like both. How long is a short? No, you're joking, mechanic. There is no way you had that exam in your question. I wouldn't know how to answer that. I'm guessing that's a joke. Your lecturer put that in as a joke. Hey, Irish Rover, welcome in. Usually black tea, standard Irish breakfast or Irish teas. In Ireland, we have something called Barry's and Lions. Very, very good teas here. I don't drink it with milk. I just drink black tea straight with no sugar. And coffee I drink with a bit of milk. I'd answer with yes. Probably me too. Hope the lecture's gone. It's really, really, really well. What did we do? We did a lot today. Let me revise everything we did today. Okay, for anyone coming into the Twitch stream, welcome in. If you guys were here in 15 minutes or less, let me do a quick crash course revision of what we've covered. I have a little lesson plan here. Can't say I'm not a teacher without this kind of... So I covered what an atom was very briefly, and the reason I only covered what an atom is briefly is because I'm going to teach you about semiconductors later, and we're going to talk about holes and electrons and electron hole pairs and the depletion region. We're actually going to talk about like pretty, not advanced, it's not crazy advanced, I don't want to scare anyone, but it's definitely not intro level. This is definitely already jumping a little bit. So we are going to do some really cool solid state physics stuff. Still introductory level to solid state physics, but it's still solid state, which is cool. I talked about the proton, neutron, and the electron. Specifically, electron flow is got to do with the electrons flowing atoms. Specifically, metals tend to be very good conductors because they form this thing called a metallic bond. And this metallic bond is really, really cool because the electron isn't associated with one atom. They're a collective. They're a hive mind. Okay, there's a bit of Star Trek stuff going on. The Borg here. But the idea behind it is they are so ready to jump ship that the tiniest bit of voltage allows current to flow very, very easily. Now, a voltage difference is basically creating a pressure wave. You're creating pressure for electrons to flow. The higher your voltage, the higher your pressure, the more electrons will flow. Now, a little bit of a misnomer. Current flow and electron flow are two different things because initially when current was discovered, people didn't know about the atom, they didn't know about positive charge, and they didn't know about negative charge. And so there was a 50-50 gamble of determining what was positive and what negative. And it turns out we made a bad guess and negative was in the other direction. That being said, we still work with the same problem. We continue to pretend that current is positive flow. All it is that electrons flow the opposite way to current. Don't worry about it. And finally, resistance are things that block current flow. They slow it down. Well, slow it down is a misnomer as well. They reduce the amount of current that is flowing, and there is a direct proportionality between all of them, which is called Ohm's law. Voltage is equal to current times resistance. And we proved it earlier today. We did a whole experiment. We had a whole Excel sheet. We got what the resistance was with the slope of the line. We compared it to experimental versus theory, and we got a very, very accurate result. And yeah, we basically proved Ohm's law. Now, Ohm's law isn't true to everything. It's not true to semiconductors. It's not true to non-conducting material. It is not true to things that get hot. There's all these little exceptions. But generally speaking, in most electronic systems, it's true. It's even true in AC circuits. And I didn't talk about that too much, but I did a whole series on Instagram and YouTube. If you guys are really interested in AC circuits, I have done a lot of this on YouTube. You're interested in that, and Instagram and TikTok. So whatever your platform is, whatever you prefer, make sure to follow me there. I do a lot of social media and outreach there. So that's where we are. We did series, now we did resistors in series and parallel in combination. And the next step I want to do is I want to prove it to you. And I want to show something really cool that happens to voltage in series and parallel. There we go. Hopefully that was a good crash course summary of everything. Did you teach 5-5? No, nothing about 5-5-5 timers at all. In fact, I've only encountered it recently because I started messing around with electronics, Brian, and building stuff. Trek is better than wars. Yes, Cowboy, you are not getting banned. What are your tips for science communication, content creation? You'd have to be a little bit more specific on your question if that's okay. If that makes sense. Like what tips are you kind of looking for? As in being consistent or inspiration or, you know, sorry, I can't help much more. All these fun things. Well, I don't know if that's that true though, Sundry. So the exceptions are the fun things. Does that make sense? So when I said that it isn't true to semiconductors, it's really, really, really cool why it's not fully true to semiconductors. And I'll explain it hopefully in a couple of hours time. I do need to get, let me see what I have in the lesson plan. My last thing, I really hope to cover it, which is magnetism and motors. I want to explain how a DC motor works. I have a whole DC motor kit here. Really, really cool. Kirchhoff's laws, potential dividers, potential. Yeah, I won't do current dividers. I don't have time to do current dividers. Welcome back, Jimmy. Growing up in school, maths and science were my weakest subjects. That's kind of why I do what I do with my social media and Twitch is I'm not aiming this for kids. And it's okay if you are in high school, if you're learning physics and you're just interested in stuff, that's completely okay. But my thought process behind a lot of my science communication is a lot of us did do physics and science in school. I didn't particularly love it. It wasn't fun or interesting to me. And I don't think I got an intuitive understanding. So most of the science communication I do is kind of teaching basic physics again, but with a little bit of a, interesting trick or interesting analogy or just sharing how my brain works and how I interpret things. So most of the stuff that I teach is for adults who did do a little bit of physics, weren't too crazy about it, but now maybe you guys are interested in science. There's a lot of cool stuff in the news about physics, about rocket launches, about superconductors. I'm trying to find some buzzwords that are in the news lately. But, you know, there's a lot of stuff in the news lately. And I'm just trying to give you more context and more base to be able to interpret a lot of the language that is... Hopefully I'm doing a good job, but we'll see. I want to buy one, Has. I wanted an oscilloscope. My birthday is coming up. I was thinking about, yeah, I do want an oscilloscope, my own oscilloscope here. I have one in the lab, but I don't have one here at home. I want an oscilloscope and a frequency generator. I want those two things. Those are my to-do list or to purchase list. But good ones are really expensive, you know, it's really hard. I trust class has been well behaved, very well behaved. I think we only had to ban like 2 people. Actually did not include a time. Now, I think I will make a cup of tea if that's okay with you, chat. Anyone want a cup of tea? Before we continue. So when we come back, we're going to do some voltage drops across resistors. Me? Yes. All right, I'm going to make a pot. I'll be back in 3 minutes. Irish coffee. Not today. Not today. Maybe another day, but not today. All right, chat. I will see you guys in a few minutes. I'm going to put on... Oh, if you guys are... So one of the things I do is I play video games and I teach physics using video games. So to give you a little taste, I'll put on a video of me teaching the physics of boulders. Let me show you a little bit about that while I'm off. My rabbit. Sorry, it took a while. Obviously, I have to boil the kettle and things like that. Back, everyone. We also have been blessed minorly by Bambi. Background, that's my bunny. Is the inspiration for all the chaos that happens on stream. For a PhD or a job, as both of them are hard to get. Emperor, it depends what you're looking for. Okay. Are you looking for... I would lean to... yeah, no, I can't give advice because your life is very different to mine and I don't know what your story is. So I really can't give advice. Advice for myself, I would do... Like, I'm very lucky the way things turned out. Oh, she's going to the robotics box. The advice I would give myself is to get a job first from me. But... Bambi, you're on the front page. Ah, that's my box of magic tricks. Gotta be careful with that. All right, I got myself a chocolate croissant. So like I said, Bambi is allowed in the streaming room when we're not building stuff. So because we're not soldering anything, it's okay. We do have to keep an eye on her to make sure she doesn't eat any of my wires here because this room is not bomb-proofed. So most other rooms in the house are cable-proofed. This room is not, so we have to supervise her here. So chat, if you see her being bold, scream at me, okay? If you see her eating wires, you have to yell. Woo. setting up stuff here for the next experiment. So I'll get a bunch of resistors as well.
And they call it a mine.
Cowboy, thank you so much for the sub. Really appreciate the PP contribution. I'll bonk if she eats the wires. Thank you, chat. Thank you. Want to come and say hello to chat? No? Chat can be weird sometimes. I get it, Bambi. We don't want Bunny to become a resistor. Exactly. Oh, the chocolate filling is really good in these chocolate croissants because it's little. Little is good. Listen, I know it's a mass food chain or whatever those are called, but Little Bakery, chef's kiss. Okay, so I grabbed a bunch of resistors. So this is my little tray. I have a label maker and all. In case you're wondering, I have a bunch of resistors here and they're labeled accordingly. I spent some time organizing some of my stuff. 100 ohm, 220 ohms, and 330 ohms. So that's what we'll work with today. We'll obviously measure them as well, just to make sure. But yeah, make sure if you see her do anything silly, scream. So the first things we're going to do is I'm just going to put two resistors in series. One 220 ohms and the other one 330. Hi, Cora. Welcome in. Classic resistor numbers. That's right. So I have 220 and 300. I will
And they call it
switch the camera around. Grim, thank you so much for getting Lunar gifts up. Appreciate that. Thank you. We have another lab rat to join us. I might switch the camera around so you guys can see Bambi. Maybe we can build a second. I have this overlay. Oh yeah, you can do a bit of bunny cam. If I can move. Maybe I can do a mini bunny cam for you, chat. No. See if my camera can stretch over here. Sorry, chat. I'm moving you around. I'm shaking you all about. Just want to set you a bit of a bunny cam here. The very, very crude bunny cam. Ooh. But ta-da! Bunny cam nonetheless. There we go. Very crude bunny cam. So chat, it's your job to keep an eye on Bambi. Make sure she doesn't eat any wires. Let me know if she does. Thanks again, Cowboy and Grim. Really appreciate it. Okay, so let's build some resistors here. Sorry, I have a fan working here, so let me turn. It's a bit hot here. It's getting hot in here. Do not take off all your clothes. Now, we could build a breadboard thing very, very crudely, but I'm just replicating a simple circuit in series. So I have a power source, ammeter. From the ammeter to the resistor, I'm going to grab another wire and connect that with the other one. Whoop. Sorry. I'm in my box of magic tricks here. Red. Okay, I know my desk looks messy, but I swear, for the front page, I spent like half an hour cleaning this room. Can you tell? Can you tell how clean my room is? Chat. Please compliment me. Sure. And then guy needs to. Okay, I know this looks very, very confusing.
Call it a mine.
Cora, thank you so much for a gift sub. Really appreciate that. Thank you. Clean for a physicist. You know what? I'll take it. I'll take it. Thank you so much, Cora, for the gift sub.
And they call it a mine.
A mine. Thank you, Cynical Sorcerers. Appreciate that. We have a Bambi on the loose, actually, at the moment. Big stretch. My favorite part of electronics is when there's a fire. That doesn't sound good, Duffy. That doesn't sound good. So don't be distracted by Bambi chat. Focus over here, this camera. So power supply, positive port, follow the train, goes into the ammeter. This is going to measure our current. From the ammeter, from the negative port, the common, it's also called the common sometimes, goes to our first resistor. Our second resistor then is connected to, our first resistor is connected to the second resistor and back to close. It's basically the circuit that we built earlier. Well, we didn't build it, but we showed earlier in our whiteboard. Bambi's on the loose. She's still there. She's hiding behind the thingy-mabobby for now. For now. Use a large number of resistors. Are there special instructions for fighting electric fires? So we do have a special instruction in the house. There's different fire hydrants, not fire hydrants, fire extinguishers to use. So we have two. We have a electrical fire here as well. I am very cautious. One would argue that I'm overcautious, but I do have a fire blanket and I have a fire hydrant in case. But again, I'm working with such small things that this should not be an issue. Should. Don't jinx it, chat. Thank you so much, Cynical Sorceress, by the way, for the gift sub. But if there is a fire, we're grabbing Bambi and we're running out the door. Good to be prepared. Exactly. It's overkill, but you know what? It's okay. So, what we're going to do is I'm going to measure or supply some voltage here. Ta-da! So I'm going to increase 5 volts just to make a pretty number. I want a pretty number, so I'm going to increase this to 5 volts. Look at this number, chat. This is the voltage, okay? Volts. Mwah, beautiful. Chef's kiss. Turn on this bad boy. So we have our current reading here, 891 milliamps. You can do the maths, by the way. One of them should be 220 ohms and the other one should be 330. So yes, you don't use water. An electrical fire does not use water. It's this kind of foam thing, right? So that's why it's different to a normal fire hydrant that you might find in your kitchen. Never water, exactly. If you can safely do it, so a bit of health and safety, if you have an electrical thing going on, before there's a fire, hopefully, as soon as you smell carbon, shut down the power supplies if it is safe to do so, and evacuate the room. Be safe. Grab your bunny on the way. My case, my bunny's over there. Hiding behind the thingy-mabobby. No, not distilled water, not pee. No, 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 chat. No, no, no. Okay, so we have current going through. And like I said, this is a very safe circuit. We only have 8.91 milliamp. This is minor, right? If I cause anything with this setup, that would be talented. Shouldn't jinx. I have done some incredible things in my life. I think one of the first things I did as a master's student, when I was free in the lab for the first time, I did blow up a resistor, and my advisor was very surprised. Happened. Anyways, we have 5 volts going through our system at the moment. So what we can do here is we can measure the voltage across these 2 resistors. Let's do that. Let's find something very, very interesting here. Or maybe it's not interesting. That was a bit of a spoiler. Anyways, let's take down... I don't have a pen and paper, so chat, I'm going to rely on you writing this down. Let's measure the voltage across the first resistor. I forget. There we go. Minus 2.94 volts. Could someone write that down? Minus 0.294. Let me write it on the board. Okay, why was there a minus sign, by the way? That was weird, wasn't it? What in the heck? Why is there minus signs? Across the other resistance. 1.956. We'll say 1.96. 1.96 volts. Polarity, exactly. I actually, what happened was you can change the negative and the positive by just switching these bad boys around. Basically what I did was I switched the reference points. I made one of them 0 when it was supposed to be the positive port versus the other one. So when you measure it, it's basically, okay, I kind of went on a rant. It's a directionality issue. That's all it is. It's one direction over the other. Minus sign shows that the voltage is actually meant to be going the other way of what I'm actually measuring it. So if you ever see a minus sign, don't panic. All is good. It's just a directionality issue. That's usually a general comment on physics, by the way. If your lecturer says anytime, chat. Oh, okay, sorry, your lecturer wouldn't say that, except for me. Class, why is there a negative sign here? Your answer, more than likely, has got to do with the fact that things are going the opposite direction of what was conventional. Okay. So we've measured the voltage and we measured the current. And we've measured the current, 8.91 minutes. Let me write that down as well. Very interesting things we just found. Our supply is 5 volts. We couldn't measure what the true supply of the voltage is, but it doesn't matter for now. I've shut everything down. Good practice as well from health and safety perspective is to make sure that you shut everything down when you can. You're not using things. And when you're messing around with the circuit, but also very, very important. Now, let me pick you up, chat. Upsies. You can see both Tofu and Bambi. Stand here so that you can see Bambi as well. So, I took down the results here. Something interesting has happened, chat. Very, very interesting. We supplied 5 voltage to our circuit. And remember before when we were doing Ohm's law, we were measuring the voltage across the resistor and it was pretty much matching what our voltage source is. Now something interesting happened. We measured 2.94 volts across one resistor and we measured 1.96 volts across the other. It means that we drop a proportional amount of voltage across each resistor. Very interesting indeed. Hi, Goodest Bean, welcome in. If you're a Goodest Bean, is that a coffee bean? We must know. Hi there, hello, Oil Painter, welcome in. But it is 4.95 difference? Sorry. Oh, are you saying that we're missing about 0.1 volt of something? That's okay. That's okay. We've lost some stuff. We've lost some voltage. It's okay, though. We talked about imperfectional. Maybe I'll talk about it properly again. Why voltage sources are not perfect. Nothing in this universe is perfect, chat. Well, I was going to say except for me, but we also have this over there. Half perfection incarnate.
And they call it a mine. A mine!
Cash will wait. Bye. Sorry, I chased Bambi away. Wanted to eat her treat. Beady Bambi, exactly. As soon as she got her treat, she was like, bye! I'm out of here. I don't need you no more. So let me just finish my croissant, and then we will do a bit of a calculation really, really quickly. But what I'm trying to get to is that energy cannot be created or destroyed. Do you remember that figure of speech in physics? Does anyone remember it?
In this house, we obey the laws of thermodynamics.
Thank you, Naz, for that. Exactly. That's okay if you never took physics. Perhaps you heard it as a figure of speech before. Did a lot of earth science. That's just physics with extra steps. Listen, I'll say that about a lot of fields of science. Anytime anyone says, I didn't take physics, I took this. I don't have a degree in physics, I took this. I will just say, listen, it's just a fancy word for another physicist. To Easter Island for a visit. So, it is true. Energy cannot be created or destroyed, but can only transform from one form to another. And ultimately, what's happening is that the total voltage that we've supplied to our circuit, which was 5 volts, cannot be lost. All the drops of voltage have to be accounted for. And you can do some mental maths already, and someone pointed out, I think it was Zier, that we're missing about 0.1 volt somewhere. But honestly, it's okay. It's okay. That's normal. I'll show you where the mysterious 0.1 volts has gone. There is usually a mystery as to where the 0.1 volt has gone. But I'm sure some of you guys already... I say physics is just Matt was said. Well, I will be pretentious and snobby, Brune, and say that maths is only a language that is used for physics. It isn't the thing that is used to do physics. I'll be pretentious and snobby about it. Welcome in, welcome in. I'm almost done my croissant. Let me just eat this really quick. Okay, it's really chocolatey. I can't eat it really quick. Never. I need chocolate and tea. Be able to teach, you know. Even IRL, you know, when I teach physics lectures, if I have a lot of classes back to back, I still have like at least 10 minutes between lectures usually. So even if it's a rough day with a lot of lectures, I do get a break in between teaching. So I do need to eat a little bit. Skateboarding has really cool physics applications. You can... Last year, a crazy stunt was done by a skateboarderist, I think. Was it a skateboard? It was. So it was a bunch of ramps being... tricks being done on a skateboard on a bunch of ramps on a moving train. Do not do that at home, chat. But it was a really interesting concept and educational aspect for inertia, if anyone has seen that video. Hi, Prof. Hi, George. Welcome in. Sounds like a... No. No. Let's not do this at home, chat. You kind of sound like the professors. Do I? I'm almost done, chat. One more bite left. Done. All right. Let's do some physics again. Sorry for the break. Like I said, I've been lecturing for about 3 hours now, so I do need to eat occasionally. Where's my spray? Oh, there it is. Let's clean up the board. Right. Now, let's do some physics. So what happened earlier? Oh, sugar plum on a cracker. I took it down. But that's okay. I think 1 plus 2.9. No, 4. So I'm just going to redraw the circuit of what the experiment we did earlier. We had our voltage source. That was our power supply. I had an ammeter. It's a circle with an A, measuring current. Remember, you measure current through something, not across something. Never measure current through something. Never measure current across something. And we had 2 resistors. We had 1 resistor and 2 resistors. So one of them was 200 ohms. No, 220 ohms. And the other one was 330 ohms. So you know mathematically that the total resistance in the circuit is 550 ohms. Because they're in series, we can add them together. There is no other way for the current to flow in the circuit. It only has one path. Think of it as a train track. Choo-choo, all aboard the scam train. There is no way for the current to go anywhere else. All the total current is the same at any given point. It has to meet this resistor and this resistor. So we can add the resistors quite literally together to make one equivalent resistor of 550 ohms. Apologies. Now, we did something really, really interesting. Applied 5 volts to our circuit. But another thing that we did was we measured the voltage across both of these guys. We measured 1.96 volts here, and we measured 2.94 volts. Very interesting. Very, very interesting. So a couple of things. Energy cannot be created or destroyed, but can only transfer. But anyways, the point is energy cannot be created or destroyed. That 5 volts has to go somewhere. We have to lose the 5 volts. We lost it across this guy, and we lost it across this guy. And remember the analogy of water and potential energy that I used. Imagine this kind of like a 3D circuit. And imagine the 5 volts is like 5 meters up a hill. Okay? So we have a hill, we're starting at 5 meters. And we meet our first resistor. Our first resistor is a drop. Then we meet our next resistor, it's another drop. And then it continues on and on. 5 meters here to 0 meters. We dropped 1.96 meters here. Have about 3 meters left to go. We dropped 2.94 meters here. And we dropped all the way to 0. Now, there is a little bit of leftover voltage. If you add these guys up together, you know that it doesn't add up to 5 volts. We're missing about 0.1. And let me explain where that has gone. Again, physics, we can't create or lose energy. That just defies all laws of physics. That voltage went somewhere. Over here. Every single power source that exists, voltage, battery, has an associated internal resistance within it. Okay? This is kind of like a sci-fi superhero story happening, that anyone who has great power has great internal resistance a little bit. Welcome in, guys. Welcome in. Hello, science for physics. Yes, science has a really, really cool username because science is a science communicator and has a background specifically in biology with ants, with leafcutter ants. I don't want to put words in your mouth, science. So that is the interesting username from science there. If you guys are interested in biology, make sure to check him out. Remember I said my Tofu Tech Talk? Science was one of my guests as well on it. If you guys want to check out that Tofu Tech Talk, it's in my About Me page if you want to scroll down. Now, so we have total resistance. We have 220, 330, 550 ohms. Oh yeah, and we lost 0.1 volts. Sorry, I got distracted. There is internal resistance with any single power, with any battery, with anything. And this is something that in electrochemistry people don't talk enough about. Number one, true efficiency, and number two, internal resistance. And usually what we secretly do is to make this a little bit easier is sometimes we put in a resistor in series with the voltage source and say that we drop some voltage across this, about 0.1. That is where we lose a lot of the voltage. Because ultimately a power supply is basically a battery, okay? This is why potato batteries are amazing. Oh my God, chat. Potato batteries are so good for this educational specifically. Because if you build a potato battery, you will know that you lose current or you lose voltage if your plates are too far apart. When you put two metallic plates into your potato, and there's current going through your potato, it uses the juices of the potato to travel through. If they're too far apart, your flow is blocked by more potato mulch. And so you have more resistance. If you put the potatoes closer together, or the plates closer together in the potato, and less potato distance, you have less resistance. This is kind of the concept of internal resistance of any power supply. Again, every battery has this. Every power supply has this. Anything in the world, in any electric circuit, has an internal resistance associated with it, unless of course it is a resistor itself, which then it is a resistor that, no, but then that resistance is associated with the internal resistance. Anyways, a little bit of a side rant. So just to explain, we did not defy the laws of physics. We did not lose 0.1 volts somewhere. Probably, more than likely, lost across there. Another part where it could be losses like the ammeter, the voltmeter, little things like that, but most of it, chances are coming itself. This is why, by the way, even though my power supply, remember earlier when we were doing this experiment, it was giving us a number here, 5 volts. In reality, we don't actually use the number that the power supply gives us, because it's kind of lying to us. You use a voltmeter and literally stick it in to the positive and negative port and measure the actual voltage coming out of it. That way it'll be a lot more accurate. Your measurement, the thing that's reading, isn't probably perfectly accurate. And your voltmeter also has a percentage error associated with it, but generally speaking, compared to the power supply, it is a good bit smaller. Zinc plus lead and acid is a battery. That is right. Now, we do drop voltage across these bad boys, and we're going to cover something called potential dividers. Now, ideally, I should have covered Kirchhoff's laws and Kirchhoff's current law. And honestly, it's a very, very simple subject, and the reason I say simple, and I don't want to degrade anyone who's struggling with it, is I've actually mentioned why I find this too simple. I think if you were taught electricity as a physicist, this concept is very, very intuitive. If you were taught this as an engineer with no physics first, it almost feels like you're first forced to learn off something, and then you're kind of like, you don't have an intuitive feeling for a lot of these things. So this is why sometimes I do think a little quick physics lesson is very, very important as to, electrons flowing, what's happening, where does the current go, where does the voltage go. And the little thing I want to mention that's a little bit different is, so Kirchhoff's voltage law basically says that when you have a voltage source, something like 5 volts here, the sum of all the voltage drops has to equal to 5 volts. I kind of already mentioned that with a lot more words and a lot more demonstration. We kind of know this. The current is the same at any point in the circuit that is not in parallel or closed. I forget what the specific wording of the current one is. That's basically it. We've already said all of these things, but in an intuitive electron way already. You already know this. So yes, maybe your lecturer or your teacher is making you, forcing you to learn off something word for word. I hate this. I hate that you're first to learn definitions instead of understanding them conceptually. But if they are forcing you to learn off these definitions, that's the words, but the explanation you already know. I kind of covered it today over the last few hours of doing a lot of these things. Welcome in, everyone. Welcome in. I didn't expect to learn about electricity, but I'm here for it. Welcome in, Rust. We will be jumping in between lessons. So at the moment, we are doing potential divider lesson, which might be a bit out of depth until, unless you have covered earlier the stuff that we covered. But with every lesson, you can go jump in. So the next lesson I believe I'll be doing will be semiconductors. We were talking about solid state physics and atoms. So I'll definitely start again from the beginning. You can jump in very, very easily if anyone wants to stay around for that. Exactly, bloatware. It all comes down to thermodynamics. Sorry. I know there's a lot of new people here, but if you know anything about me, is I will always tell you everything comes down to thermodynamics. Everything comes down to entropy. Everything comes down to statistical physics. Even everything I'm teaching you here right now is all just a fluffy version of statistical statistics. That is my spiel, but of course I'm very, very biased. Hi, cool channel. Hello, welcome in. Welcome in. So, where was I with this rant? Anyways, that is Kirchhoff's laws. But let's do a bit of a calculation here. How do I know how much voltage is going to drop across each resistor? Well, you kind of already can figure it out maybe just by eyeballing it. See that it's almost 2 volts here, and you see that it's almost 3 volts here. 120 ohms? 330 ohms. This sounds like there's a proportionality. You're absolutely right. Let's say I didn't know what this number was. I wanted to know what is the voltage drop across this resistor. Our total, so let's say we're looking for a voltage drop across 1. Say this is 1 and this. It is equal to whatever our resistor value is, 220. This is the proportionality value. All over the total sum of all the resistors. So that is 220 ohms plus 300. All multiplied by our ratio of voltage. Okay, so what did I just do there? What the heck total? There's no ghost in space, Preserve! Jesus Christ, Preserve. Welcome in, welcome in. What did I just do? Out of focus. Vicious. We want to know energy cannot be created or destroyed. So we know that there is a ton of voltage being dropped across here and here. These are the only 2 things, even though there is technically a resistor up here, but we're ignoring it because we're dealing with an ideal situation. We know that all the voltage drop has to drop across here, and it's directly proportional. If your resistance is really, really low, i.e. if your steepness of your hill is very, very small, only a small amount of the voltage will be dropped. If your resistance is really, really big, you will drop a lot of voltage. Your steepness is really, really big. Is my mic cutting out? Apologies. Thanks for letting me know. Your resistance is really, really big. That is why what we want to do is we want to know, we want to extract a fraction of this 5 volts based on this resistance value. 220 ohms is the resistance value over our total one, right? We're basically getting a percentage answer of 5 volts. That's why it's 220 divided by the total sum of the resistors, multiply by 5 volts. This number is just a decimal place. It's just a decimal number, multiplied by 5. You can do it in your calculators. Do I have a calculator, by the way? I should. I swear, I lose my calculators like I lose my glasses. Oh, and I attach this to my glasses because I'll keep losing my glasses. And now I can't. I need to do the same with my calculator. Wait a second, chat. I'm coming back. Have a calculator. phone. Exactly. I just need to wear a calculator necklace, you know, just put it in a case and wear it around my neck. I'm going to start using that as my phone. 220 divided by, in brackets, 220 plus 330, which is 550. Sugar plum and a cracker. Okay. That's 2/5. I should have known that. Multiply by 5. Okay, that was a lot easier than I thought. I didn't know why I calculator there. All right. Listen, I know that we know what 2 plus 2 is, but lads, if you're in the exam, you better be putting it in the calculator just in case. 2 volts. We can do the exact same thing again. Voltage 2 is 303
They call it a
30
mine.
ohms over
A
220
mine.
plus 330. 5 by 5 volts. We get 3. So the voltage drop should be 2 and should be 3. Got 1.96. We didn't get an exact answer. Curling Master, thank you so much for the resub. 9 months. That's a Twitch Baba. That's a Twitch Baba, all right. Thank you so much for the support. Appreciate it. Sorry, I hear tappy taps. Bambi's running around outside the hallway. So we've dropped 2 volts across the first resistor and we dropped 3 volts across the second resistor. And we got really, really close experimentally, those answers. And the reason why they're not perfect is, again, there is probably a resistor in series that we need to consider. There's also, just generally speaking, potential percentage error associated with any measurement we take. And this is, it sucks. And I know that it can be really, really boring sometimes, and I apologize. But in physics, percentage error needs to be taken into consideration. Actually, not just physics, experimental science. Any science where you take data of any sorts has a percentage error associated with it. It has any error association with it. And knowing and measuring that is very, very important. What you drinking? Tea? Do you teach chemistry as well? No, actually, Brokebat. I teach maybe some minor electrochemistry. Not even. It's been, yeah, I don't know. I never really taught, even though I have a degree in chemistry, I never taught it before. I'm not sure why. I kind of, I teach a lot of chemistry concepts with like physics outlooks, if that makes sense. For sure. But yeah, I don't know why I don't teach chemistry. I know a few stuff. Usually what I teach is things that I'm interested in, to be fair, and very knowledgeable in. So I do tend to have doubt in myself when yeah. But yeah, my bachelor's degree is actually in physics and chemistry teaching before I went on to do my master's and my PhD. Fusion, I do have a thing called Tofu Tech Talk where I invite guests for a podcast. If you want to look at the About Me page, you might have to, if you're watching me from the front page, you do need to click into my profile. But not a collaborative teaching. I'd love to do that, actually. I'm still looking for physicists to teach with. It would be a cool project. Any optics teaching? I do teach very basic optics. So, you know, like first year physics. So what is it called? Geometrical optics. I teach lenses, mirrors, but not waveform optics, if that makes sense. I do it, but I don't teach it to myself much. Sorry, I got a bunch of messages on Discord, and if anyone knows me, if you message me on Discord, if you message me anywhere, I always make sure, test that you're safe and alive. Okay, everyone is safe and alive. If you send me a message, I will check it, if it's life or death, and then if it's not life or death, sorry, if it's not death, wait, which one is the correct interpretation there? Anyways, I'll respond to it later, and then I forget, and then I never respond. Thank you, Travis. Thanks, Jimmy. Can we go over Lenz's law? I'm doing crash course electricity today, Master. So we're not doing electromagnetism today. I'm going to do very basic magnetism later, but only to teach about the DC motor. That's my plan. No, I've never done the fusion. I've never given homework to chat. That's a good idea, though. Chat, do you think you want to get homework? Chat, do you want me to assign homework every day for you at the end of Twitch stream? You can be like me and have ripped up pieces of paper and show proof to me in Discord. My rabbit ate my homework. Everyone getting flashbacks, exactly. I don't think we really got homework in university. You obviously had assignments, but those were like part of your grade, but not homework. Hi, 53 New Wave. Hello. As long as it's not Fourier transform. I hate to admit this, but I'm starting to like Fourier transform. Fourier transform saves lives. Fourier transform saves lives. Hate to admit it, but it's true. I used to hate it when I was younger, but I have an appreciation for it now. All right, let me check my teaching schedule. Where are we now? So we did potential dividers. I'm not going to bother with current dividers. Should I bother? No, I will bother. Maybe not for current dividers, but I want to show you something really, really cool. We're going to build another circuit, chat. Almost the exact same circuit. Oh, Tarek, thank you so much for gifting a gift sub. Oh, mine! Have we covered potentiometer? No, I don't think I will bother. Just because we're not going to use it, you know. Today, we're going through a little bit more basic things. Okay, so what I'm going to do is 35 stream streak. We finished bogus. We mentioned earlier. Now, let me rebuild this circuit. Let me remove the marker so it's not too crazy here. I'm actually going to get a breadboard out. And I don't want anyone to be alarmed. The reason I'm using a breadboard is just because it's going to be way easier to measure. So this is a breadboard. Don't panic. All it does is that it's basically easier to wedge wires in. Actually, is this going to be easier or harder? Might be harder. Never mind. I'm not going to use breadboard. Now, we have current going through. We're using the same resistors as last time, but this time we have... Basically, what I've done is I've put only one resistor in series. We have the power supply, we have an ammeter, we have a resistor, back to power supply. Choo-choo! Just a straight line train. Ah, I'm glad. I'm glad I inspired you to get a go. It's so handy to have a power supply, you know, when you're testing things, and I don't know. Again, to each their own, but for me specifically, I think a power supply absolutely does make sense to own one. So my birthday's coming up. I'm not asking for chat right now, but I'm very tempted to set up a throne to get a budget going for an oscilloscope and a frequency generator. I'm very tempted. Very, very tempted. Now. Oh, sugar plum on a cracker. Oh, that's okay. I can do it crudely. I'm going to show you a trick here. So, these banana plugs, I think they're called banana, well, I call banana plugs. It's next month, Blower. It's a bit away. I can plug it in here. Let me zoom in the camera a little bit more. I can plug this banana plug in here and then put this clip across here. What have I done? Oh, what have I done? Let me get this clip here. Crocodile clip. Then get another cable. Alligator clips, that's right. How much? I need to do some research, EK. I actually don't know. There is like amazing oscilloscopes for like 9 grand, and you will absolutely catch me dead before I will buy an oscilloscope for 9 grand. Because what the heck? I don't know how cheap they can be. There's definitely cheaper options. Okay. So what have I done? I've basically plugged in this resistor in parallel with this other resistor. I'll show it into the circuit diagram. It is very confusing. Here's the thing. Circuit diagrams are easy. They're very easy to visually see how you build it. But the experience of working with wires is really, really strange and unusual for the first time. So here's the thing. A lot of people, when a student in university level or maybe even high school level gets to play around with these wires for the first time, and you build a circuit, some people tend to be a bit mean when people don't know how to plug in here, let's say, or how to crocodile clip things together. And honestly, knowledge and hindsight and all of that is really, really important. Unless you're familiar with wires and banana plugs and crocodile clips, you'll never know how to set these things up, and it's not fair to make fun of people. So this is my little side rant. I've worked with wires and cables all my life, well, not all my life, but all my adult life. I know how to use this. First time seeing this, a lot of people wouldn't know how to use it as well. So if you don't see how this is in parallel, it is completely okay. That is hard. This is difficult, especially for the first time. Anyways, that's my rant. I'm Lakshard. Thanks for my yap emote. Yes, you can, if anyone got amazing gift subs there, you have a Tiny Tofu yapping emote, which is called rant. You also have a soldering emote. We have loads of cool physics emotes, actually, now that I think about it. We have soldering, yapping, scheming. Scheming is a very good one here. I agree, Illidan. A lot of people are really mean and negative, especially online, about things that they'll call common knowledge or common sense. And I think a lot of people don't realize that these things are not common sense. My personal and professional opinion. No Arduino. So I know my robot has an Arduino here, but we're not actually messing around with the robot today. Today we're just doing very basic resistors. So what I'm going to do is I'm going to turn on the current. Remember what the current was last time, chat? Do you guys remember? Anyone remember what the value was when we had the 2 resistors in series, roughly? No, not 69, Jimmy. 42. That's not bad for a pointed-eared elvish princeling. I think it was like 13 milliamps, was it? Let's do some quick maths here. 5 volts divided by 550, about 500? About 10. It must have been about 10 or something.
Final count.
42.
42. Oh, that's not bad for a pointy-eared elvish princeling.
Final count. 42.
42.
Ah.
Oh, that's not bad for a pointy-eared elvish princeling.
Final count. 42.
Chat, do I have to turn off the sound alerts?
That's not bad for a pointy-eared elvish princeling.
Final count, 42. Thank you so much for the bits. So I actually had to increase the range of the current. It was 37.3 milliamps. Holy smokes on a cracker. We had something like 10 milliamps earlier, and now it's increased drastically. It is the answer to life, the universe, and everything. You're absolutely right about that. Thank you, Herder. I will kindly ask for you guys to hold off the sound alerts, or I have to turn them off. I should, to be honest, I was warned I should have turned off all sound alerts on the front page, but a little bit of banter is always good. So we have 37.3 milliamps in this circuit. That's a lot. It's almost tripled in size. Now let's measure the voltage across the resistors. This is going to be the drama. Are we ready? This is the drama. What voltage are you expecting, chat? Dun, dun, dun. Okay, so let's measure the first one. 4.93 volts across resistor 1. And across resistor 2. 4.93 volts. Dun, 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 dun! What the heck just happened? Okay, I'm gonna pick you up, chat, again. Chat, are you ready for your upsies? Upsies we go. Back to the whiteboard. It would be handy to have 2 cameras, to be honest. I do have a second camera, but as you guys know, it's really poor quality. Right, so that was really interesting. When we had 2 resistors in parallel, our voltage... I love that emotion. Our voltage was the same. Quite dramatic. Let me explain why. And I have a new analogy in my head, and I only discovered it a few months ago, and I love this analogy. I'm a genius. Not really, but sometimes I have my moments. Oop, 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 oop. All my resistors are falling. Let's turn ammeters. Let's work on this side of the board. Let's clean it up. Alrighty then. Wax on, wax off. Oh, I'll actually just put my plate away. Okay. Now, let's redraw the circuit again that we had earlier. So our earlier circuit was, sorry, it's a bit not dry yet. Have 1 resistor and we have 2 resistors. So we had 5 volts again, we had the 220 ohms again, and we had a 330 ohms. Something stuck in my eye. And what did we measure again, was it? We measured 4.93 volts, is that correctly? I don't remember what it was. Hello from France, bonjour! Welcome in, welcome in. It was 4.9, perfect. Okay, so let me explain what's happening here. There is a rule. When I teach my lectures in circuits, so I teach 2 subjects in electronics and electricity. Actually 3 if you count general physics, not think about it. I teach a lot of electricity. I have like a set of rules in my lab. There's about 5 rules coming into my lab. Number 1, we don't talk about the electron when we build circuits. The electron does not exist anymore. We only talk about current flow. Number 2, when you're measuring voltage, always measure in parallel. If you're measuring current, you always measure it through something. You measure it in series. Number 3 is that current is always the same in a series circuit, or number 4, sorry. And number 5 is that voltage is always the same in parallel. Those are my 5 biblical rules in the lab. And that rule number 5 is when you have resistors in parallel, their potential is exactly the same. So when you had a combination circuit, there was 1 resistor in series and then 2 resistors in parallel. The 2 resistors have have different resistor values. They have different current values. But remember what voltage is. Voltage is equal to current times resistance. So if you increase the resistance, your current decreases, but you get the same number. Or you decrease the resistor and you increase the current, but you still get the same number. That proportionality of Ohm's law stays true no matter what. And in terms of analogy, where did the 0 point? That's usually a resistor. There's a little resistor in series here inside the battery, inside the power supply, where we're dropping a lot of the voltage. Or there's an inaccuracy in measurement as well of our system. Even though our power supply says it's 5 volts, it's probably not exactly 5 volts. That's where the other 0.7 volts is. When we were talking about water, or when we were talking about potential energy in mechanical systems, right? Have really, really big height, 5 volts. And we want to get to 0 volts. We only have 2 resistors. We have 2 separate paths. Your resistors are basically just 2 paths down the hill. Let's look at this from a 3D perspective. You can go, let's say you're walking down a hill. You need to get to here. Or you can do this path here. That's basically our 2 paths splitting. But remember our classical mechanics example, mgh. The mass of the object, gravity is the same. Our height difference is the same. Whether or not you started your journey from here and took this path, or you started your journey from here and took this path, your height difference is exactly the same. From a perspective of the reference, your journey was exactly the same. There's some philosophical moral of the story here. Lizzie, thank you so much for your Prime for 50 months. You're so good supporting the stream for long. Through Heroes of the Storm, through League of Legends, and now through variety streaming and science education. Thank you, Lizzie. Assume a spherical cow. Listen, I'm not that deranged today. Yet. So this is using the analogy of the classical mechanics physics that we are usually talking about. This is the explanation. I've never seen anyone explain it this way. This was my revelation in my own head after so many years. But in case you want a classical physics explanation to this, that is the way I would explain it. And like I said, I've never seen anyone explain it this way. This is my little moment of ingenious. You take the high road, you take the road, and we all both end up in Dublin. Yes, so this is kind of like the discussion of displacement. In classical mechanics, we have something called distance, but we also have something displacement, right? Which is a distance with direction. And the idea behind it is there's funny situations that can happen in physics. For example, chat, are you guys into weightlifting? I'm here into weightlifting. So let's say you start with the deadlift, right? You pick up a lift and up and do 10 reps. 2, 3. Sorry, I'm imitating you, chat, but that's the way I imitate you. And you put your weight down. And then you flex and you're like, oh yeah, look at these bad boys, huh? See how much work I did? And then a pretentious physicist comes up to you and is like, actually, you didn't do any work. Your weight started at ground, you lifted it up 10 times and you put it back to ground. Your net work, when you consider the displacement of the object, is 0. So, yeah. in case you want to bully someone, it's 0 exactly. The displacement is 0. Displacement multiplied by 0, or sorry, your force multiplied by displacement, you did no. Witcher 3 music. Yes, I usually have Witcher 3 or Skyrim music in the background while we study physics. Or any music that's really, really good. So yes, this is kind of the same idea. It doesn't matter which path you take, your potential is different. Now, your flow of current is different though. So imagine this is a hill, a mountain, and there's 2 paths that can be taken. You can have a really nice, smooth river, or you can have it like a jaggedy, crazy, rifty river going down your hill. Ultimately, their potential, their height difference is the same, so their potential in parallel is the same, but their current is different. The current through the lesser resistor is going to be higher, and the current through the higher resistor is going to be lower. It's the opposite of a potential divider equation. we can extract a current divider equation out of this now. Gotta play Outer Wilds. I know everyone always tells me that I should play Outer Wilds, but I'm so scared. I saw Coraline who play it. So if you guys don't know, I have lovely friends who stream on Twitch. They're part of CC Anomaly, and Coraline is one of them. She finished Outer Wilds, and I saw so much of her gameplay. I don't think I ever want to play it again or see it ever again. It looks so stressful, the whole floating through space. It's so scary. True horror game. Now, we can extract a voltage divider equation. Oh, sorry. What we can do now here with this, by the way, is... where was my brain going? We know that it's 5 volts across both of them. Let's say we wanted to know how much current is going through each path. By the way, before we do that, we actually need to calculate what the total current is. First steps first. RT is equal to R1 multiplied by R2 all over R1 plus R. RT, our total current, is 220 ohms multiplied by 330 ohms divided by 200 plus. Do some maths. I don't think it's 100. Hey Joseph, welcome in. $132, close enough. 132 ohms. Bad music. Oh, it's on. Back to Vela. Back to Vela. You did this in 10th grade, I did it in 8th. My goodness. Okay, so RT is 132 ohms. Now what we can do is we can make an equivalent circuit out of this. Uh, 130. That's the equivalent circuit now we have with this. So we can calculate the total current. E is equal to RR. V over R is equal to I. Do this. It's a lot of ohms. It's not even that much though, is it? Because what's really interesting about it is that what's really interesting about it is that the smallest resistor in parallel is 220 ohms, and it's even less than that. So V over R is equal to I. Let's sub in our numbers. 5 volts over 132 ohms. That into our calculator to find out what the total current is. Where's my calculator again? 5 divided by 132 is 0.037 amps, or like we've been using milliamps, 37. Okay, really cool. That's what actually we were reading earlier when we were messing around with when we built the circuit. That's actually what we got in the reading. It was 37 point something. Do you guys remember? So at least we've proved that part. We've seen this. We've seen a replication of this. No. So some people do use U. I started the stream with it. U and V are used interchangeably depending on things like that, depending on your education. And it doesn't seem to be associated strictly with region. It actually depends on your lecturer and your research group. Exactly, EK. That's the really, really cool part about it, is that it's always going to be smaller than your smaller resistor, because you're creating more paths for current to go through. Okay. What's the formula for lightning then? Well, formula for lightning, I don't know about formula for lightning, but usually what we do is that's static electricity, and that's the buildup of positive and negative charges as clouds interact and rub against each other and lose electrons. So the classical demonstration is for me to get a pipe to rub a woolen cloth on it, and it can pick pieces of paper. The same kind of fundamental idea. U is voltage. So it's still volt. It's the exact same thing. U and V are the same thing. It's just some people will use capital V for the symbol, some people capital U. In all my education, majority of my education has been V. Blackshire, don't take it out of context. Don't take it out of context. Okay, 37.8 milliamps. Now, that is the total current in our circuit. But remember what I said about current. Basically, it's water flow. In reality, there's some current going this way, and there's some current going this way. So what's really happening is it's 37 milliamps here, 37 milliamps here, here. Oh no, it splits. Current has choice now. And it joins back together again here. And then it's 37 milliamps here, 37.8 milliamps here, 37.8 milliamps here. So it's 37.8 in total. But there's a split of a story here that happens. And we can use a current divider equation. And it's very, very similar to the voltage divider equation that we were looking at earlier, except ever so slightly the opposite. Because remember what I said, if your resistance is super, super high, your current is super, super low. If your current is super, super high, your resistance is super, super low. They are opposite of each other. And so we have to use the inverse relationship. What do I mean by that? So let's say I wanted to know what the current is across capital I. What is the current across this resistance? Now our total current, we calculated, is 37.8. What fraction of it is going through here? Well, it's going to be the higher amount of current, so we want a high number on top. It's going to be the 330 on top, over 220 plus 3. It's almost the exact same as the voltage divider equation, except it's the opposite resistor that's on top of what we're looking for. So milliamps is, yes, so the SI unit is amps, but because I never use, in any electronics that I've ever built and circuits that you will generally build in the lab, you'll be using milliamps. If you're working with amps, it's already when you're doing like battery work, stuff like I would be doing in my research. But generally speaking, we work with milliamps. So we can put that into our calculator. 330 divided by, in brackets, 220 plus 330. Multiply that by 37.8. Get 22. To get the current going through the second resistor here, 120, fraction of the total. And you can do really quickly mental maths there, or you can just get 37 minus 22. Energy cannot be created or destroyed. You cannot gain or lose more current. Leading current somewhere, but that's something that's a little bit more complicated and we don't need to cover now. And we get 15.12 milliamps going through the circuit. Okay, I used, this was really like, okay, how long have I been streaming? Almost 4 hours. In the last 4 hours, I covered pretty much everything that you would cover, let's say, at a high school level introduction to electricity. This, in 4 hours, we've completed everything like that. So this is great revision for anyone going into university. This is great revision, or great introduction, by the way, for the first time seeing it, for anyone who has done physics and has been 20 years since you last done it. And this should be a really, really good crash course revision. In fact, technically, Kirchhoff's laws and all of that, you don't technically study that unless you go into electronics. So there was a lot more stuff that we did cover. At least a refresher, exactly. I hope it was a good refresher. I missed the first 3.5 hours. I will upload everything on Adorn Box if you're interested. I will upload all of these VODs if you want to look back at this. No rebel. Volts is not power. So that is my 2 first sessions done. I have 2 more sessions planned. I don't know if I can get this done in 8 hours. Oh my goodness. And I need a break already. But the next session is going to be hardcore theoretical physics. And what I say by hardcore is that this is definitely not introduction level, what I'm teaching you, but it's still introduction level to semiconductors. I'm going to be teaching you solid state physics. I'm going to be teaching you about diodes. I can't dox myself too much saying. Zener diodes, but I'd probably not get to a Zener diode. Although Zener diode, like by the time I explain a Zener diode is okay to understand. But I'll hopefully explain a classical diode and obviously an LED, which is just a shiny version of a diode. Hopefully by then. It might be too theoretical. I'll see how I get on. I have my lecture notes ready. I literally made lecture notes in preparation for today. I'm totally not going to recycle them for my own students. But yes, I did prepare a lot for this lesson today. But unfortunately, it is very theoretical. I'll only use a very small demonstration to show forward a negative bias, and that's it. Gonna scare them with quantum mechanics. There's not going to be much quantum. So we're going to talk about things like holes and electrons and like electron hole annihilation or pair production, sorry. What else will I talk about? Yeah, I don't think it'll be too difficult. Giving you an imaginary Twitch apple. A lot of people don't know that reference, that teachers give or students give an apple to a teacher. Yeah, exactly, Stephen. The problem is, well, it's not a problem, but I teach mostly theoretical IRL. I don't do too much building useful things in my lessons, even though that's kind of sad. I do want to teach more about it though. Yeah. Anyways, with this diode lesson, what is so cool about it? I hope to build some breadcrumbs because in about a week or 2, I'm going to be doing a charity fundraiser. Every year, around this time of year, I do a charity fundraiser for my sister who owns a big, massive charity. Well, it's not that big, but you know, there's more than one person there. A charity to raise money for Zambian libraries and schools. And one of the problems I talk about is my whole PhD research is actually in this, is in electric grid stability and energy storage systems and things like that. And Zambia is one of the nations who heavily relies on dams. About 90% of its power comes from hydro dams. And I don't know if you've heard in the news, I know there's so many stories at the moment with war and things like that, so I know a lot of the stories might not be reaching. But Zambia and many countries at the moment are actually going through severe droughts. And they've built a library, they built free education systems, they built this whole thing in Zambia, and there's no power most of the time. They can't charge laptops, they can't charge things. So what we're doing is we're raising money for solar panels and battery energy storages for the library itself, which is going to be really, really exciting. And in topic and in theme, the physics I've chosen is going to be to teach you guys about photovoltaic cells. I'm going to teach you about solar cells. And what's so freaking cool about it, it's going to be based on the topic I'm about to teach, which is diodes. It's based on semiconductors. So hopefully I'll show you and teach you the bread and butter enough so that I can teach about solar panels. That's my plan anyway. And yeah, I'll start that next week or in the week after. Oh no, it just happens to be it's a known thing. Few statements, sorry. It's a known thing that solar panels. Oh, did you mean that? Was it a coincidence that I'm covering diodes and I thought about the solar panels and it's linked with the charity? Yes, that's a coincidence. Yes, that was a happy coincidence. Sorry, I thought you meant did I figure out that solar panels are diodes? No, that's an established science for sure. I did not come up with that. I wish I did, but I didn't. Okay, so like I said, a little bit of a break. I know that Twitch streamers are known for yapping, That's our job, I guess, as Twitch streamers. But I already noticed that when I teach physics, I yap a lot. My jaw's gonna hurt a bit. I do need to make a cup of tea, maybe a cup of coffee. I'm gonna pet Bambi. And when we come back, we're going to get into really crazy yapping session. Because we're gonna talk about some theoretical physics, some solid state stuff. Really, really cool. But again, I'm teaching it at a beginner level. So if you guys are coming into the stream now, hello everyone. Hopefully you're paying attention for just 2 seconds. If you're coming in now, perfect. You didn't need to be here for the last 4 hours. This is a new lesson, a new kind of intro. I'll build you all from the bottom up. I'm gonna raise you up. You raise me up. Sorry. Humble apologies. Oh goodness, my yapping session. I thought I yap anyway. I'm surprised I'm so tired. Don't I usually yap like this? I stream for 6 hours usually as well. Give us a demo. Like a trial run of what I'm gonna do. Okay, I'll show you what I'm gonna do. Where's my box of magic tricks? I muted myself. So, I probably shouldn't shake it there. There's some fragile electronics in there. So, I'm going to give you a preview, a little demo of what I'll be teaching. And I'll be teaching to you guys about these bad boys. These are called LEDs. Does anyone know what an LED stands for? The D, there is a trick to it because I've been talking about it nonstop. A light emitting diode. We are going to be teaching about diodes, and I'm going to use LEDs because it's a perfect demonstration to show immediately, yay, it's on, nay, it's not on. And it's going to be very obvious because the LED will light up if it is working and it will not light up if it doesn't. And the principle of LEDs is that it needs a minimum voltage to get working. And once it does, it doesn't need much more, which is why it makes it really, really, really efficient. A small thing about it from a safety perspective is diodes blow up easily because they don't need much current. In fact, they don't like much current. In fact, something, another thing. We have to be careful. We don't want to put too much current. But ultimately, if I do put too much current through the LED, I just burst it. It breaks. There's a little filament in it. It just pops. Nothing's going to explode. There's no health and safety. There's little health and safety issue with it. It's not the end of the world. But. And another thing important about an LED is that it's important if the current is going this direction or this direction. So remember when we were working with resistors? You know, remember with the voltage source had a positive and negative side. But I never said anything about a resistor. And that's because a resistor, it doesn't matter if current is going this way or the current is going that way. The resistor is happy either way. Resistor is really easy to please. If it has current going left or right, up, down, it's just chill. It's a chill dude, right? The resistor is the bread and butter of circuits. It's happy either way. However, an LED is very picky. It needs a certain voltage before it lets any current through, number one. And number two, it has to be in a certain direction. It's a very nitpicky piece of specimen. But before we even get to that, like I said, I'm going to go into very theoretical physics of it. Maybe this is it. Maybe I don't need to teach you anymore. There's enough information I gave you there, and it's happy. And if you're happy with what I just explained, go with it. There is really any reason to teach you more in terms of building electronics. But maybe it'll be a really nice kind of base explanation as to how semiconductors work. And the reason why I really want to teach this is because this is buzz news. So remember I told you nuclear physics, there's fission, fusion stuff, there's superconductive stuff, quantum computing, graphene, and semiconductors. Those are some of the buzzwords we hear all the time in news articles. I want to give you enough physics today so that when you read a news article, you can smell the BS. If there is any BS. But you know, the problem is a lot of scientific articles are not written scientifically. They're written by someone who doesn't have a science background, and it doesn't come off correctly. So I'm hoping to equip you with the knowledge and the gear to be able to, this doesn't seem right. Let me actually read the proper source. So hopefully that's my goal anyway. Theory is key. That is true. That is true. All right, I'm going to go pee. I'm going to grab a cup of tea. We'll be back in a couple of moments, chat. What time is it? It's 4 o'clock. Okay, I don't have to feed Bambi yet. I'll see you guys in a few moments. Bye-bye. What video should I give you? Do you know what? I'm going to give you Gimli. I know it sounds weird, but I'm going to give you Gimli, chat. You're going to love Gimli. I was going to get tea, but it's actually really hot. Yeah, couldn't do it. Couldn't do it. Okay, so give me a moment. I'm just going to clean up some stuff. Because we worked with a lot of things. No. Not initially. So initially he's accelerating, well, he is accelerating downwards in the sense of that he's decelerating, but he'll only start moving downwards after he reaches his max height. Let me put away this. Up the board as well. Oh, so what I'm gonna do about my laptop, because I've made lecture notes on this. That's how much I've prepared, chat. I am so prepared for this, yet I've no space. I have way too much sugar going on here. Hi, Alex, welcome in. We're always accelerating downwards. Okay. Lesson plan for today. All right, let's go. Let me clean up the whiteboard really quickly. Like I said, I was going to make a cup of tea, but you made notes? I did. That's how prepared I am for this class, Diaz, today. I made lecture notes for today. That's how committed of a tofu I am. You can't say I'm not committed to you, lads. Okay. Fair enough, yeah. Let's clean up the board, because today this is starting a new lesson. So if anyone has been here for like 2 hours and has been lost, good news, everyone. Okay. But number 2, also, we're starting a new topic. It's good that you know the things that you know, but it's okay if you don't, as you should be able to begin with me. And the beginning that I'm going to talk to you about is the atom. Okay, so a long time ago, a good long time ago, there was a whole notion that elements were made out of 5 things, or was it 4 things? Fire, air, water, ground, metal. I'm not sure. Anyways, it sounds like something magical, right? But different nations and different people had thought about the concept of an atom. I don't remember who it was, but for example, even during the era of the Greeks, there were some Indian philosophers who were already discussing about this topic possibility of things being made out of small indestructible items, things. Later on, there was different models that existed, such as the plum pudding model. Later on, the Rutherford and Bohr model. And then there's like the Schrödinger wave equation. And then there's all this Heisenberg stuff. And then Dirac did some contribution. Anyways, there's all these different models for electrons. And every single one of them is true. And every single one of them is not true. at the same time. This is a bit of a quantum mishap happening. And the reason behind it is that ultimately, I describe physics this way. Physics, to me, of course, is the truest science of them all. I'm going to be pretentious about that and all of that. But what it really is, and this is science, this is true to science of any sort, to be honest, is that we are observers of the universe. We stand back and we just watch things happen. We develop laws and ideas because of the observations that we make, and it's irrefutable. Because nothing has ever happened where it counters it. Eventually, things collapse. Our ideas and concepts need refreshing. Something happens, and we need to update our knowledge, our theories, our models, and so on and so forth. This is very, very true when it comes to the idea of the atom. We have constantly updated and developed the ideas and the theories of the atoms. All of them are correct. None of them are correct. And it doesn't matter which one you subscribe to. Ultimately, it's about using the model that best fits your story, not because you're biased, but rather to get the point across and to get your goal, whatever it may be. So, the usual description of the model, I drew it in the beginning of this session, was just a bunch of balls, bunch of electrons going around. That's fine. One of the things that we will draw or spend some time on is something called the Bohr model. Not to be confused with boring, Bohr model. So basically we have a nucleus of the atom. We have neutrons in it. In semiconductors, we don't care about this. We just care about the protons. 14 protons. So let's say there's 14 protons, the positively charged bulky bit, and 14 neutrons. Okay, so it's a balanced isotope. What we have is we have shells. We have energy levels where electrons exist. So in the first shell, the most inner shell, we have 2 electrons that exist. In the next shell, we have, I think it's 8. I hope I got it right. It is 8. I doubt myself. 4, 5, 6, 7. Okay. Last but not least, 1, 2. I've drawn 14 electrons in this system. Okay. And the reason I've drawn 14 electrons is because I want a balanced element. Can anyone tell me what this element is, by the way? 14 protons? An element is defined by the amount of protons. I don't care how many neutrons it has. I don't care how many electrons it has. Those are isotopes and ions. What I care about is the protons. Silicon. There's a reason why I chose silicon. Silicon is going to come up quite often, chat. This is silicon. Do you know silicon be good for anything? Oh, wait. It scared me. Carbon 14. I have to streams to replace carbon. Sand, oh yeah, I didn't think about it. It is used in electronics, yes. Very, very important. Making chips. It is used in semiconductors. I thought you guys were going to make a joke, but because you guys didn't make the joke that I thought it was, I'm not going to mention the joke. Okay. So we have 14 protons, 14 neutrons, and 14 electrons. If I replace the amount of neutrons, I took away a neutron or I added a neutron, it's going to change into something called an isotope. And we use the term isotope a lot in radioactivity. It's very, very important. If I took away electrons or added electrons, I would make it an ion. This would make it a charged, net charge particle. It could be positive if I remove electrons, or it could be negative if I added electrons. So just again, a quick revision highlight. A proton is positively charged, and an electron is negatively charged. Usually when we have a neutral, balanced atom, you have the same amount of protons and the same amount of electrons. So all the positives cancel out all the negatives, 0 net. charge. Okay. Now, these shells that I drew is quite important. This is shell 1, shell 2, shell 3. This is kind of the description of the Bohr model. Technically, the Bohr model is a bit more complicated than this, but we still refer to this diagram as the Bohr model. And the electrons that are in orbit, the furthermost away, have higher energy levels than the ones closer to the nucleus. The force of attraction of the positively charged proton and the negatively charged electron here, the distance is quite larger, right? Let me just make sure I wrote that correctly in my notes. I think I wrote it wrong. Oh, decreases with increasing distance. Yes. So where did I come up with this? Remember Coulomb's law. Force is equal to K times Q1 over Q2 over R squared. Q1 is the charge from the center of the sphere. Q2 is the electron on the outer plate of the sphere. And the distance between them is the R squared. This means that the force of attraction decreases a bit smaller if your distance increases. I was about to say do you know all of that stuff? F is equal to ma. If you can sub that in, you can sub in F is equal to ma. You can do a lot of calculations, and if I remember correctly, this was the disproof or the base of the disproof of Rutherford's model or Bohr's model. Forget my history now. It was basically Sorry. Thank you for letting me know. Now, something that we use in semiconductors and physics. Oh, I also have desktop volume off, by the way. Apologies. I have lovely Witcher music playing in the background quietly. We actually have a name for the outermost shell when we talk about semiconductors. We call it something called a valence shell. And the electrons that are in this shell are called valence electrons, okay? So I'll write that down. It's just a terminology, you don't have to panic. When those electrons in the valence shell, right, get sufficient enough energy from an external source. Maybe it'd be heat, photons, voltage. It could be so many different things. There's so many ways an electron can gain energy. It can break free from the atom. I want to break free. Yes, it can. It can very, very easily do so, if it gets enough energy to do so. Now, the point that we want to highlight is that of all the electrons that do break free, if you do get this atom excited, if you do get these electrons excited for whatever reason, be it voltage, heat, whatever it is, it's the ones on the outside shell that are going to move. We care about the electrons on the outside shell. And you might be saying, oh, tofu, like, why are you teaching this? What? So what? Why do I care which electrons go? They all... Oh, am I muted? They all are the same. They're like, why do I care? What really comes down to it fundamentally is that it's super important to know the structure of the atom and when you're using it. That's what's really, really important. We want to build things to be superconductive or non-conductive, i.e. insulators, or we want something weird, it's called a semiconductor. And these things are important to know the structures, the electron structure of these atoms. We want to know how easy or how hard it is to get electrons excited and get them to finally leave the house. Or, you know, that's an analogy for parents trying to kick the kids out of the house. So I kind of already hinted towards the next discussion, which is insulators. And we kind of mentioned it earlier as well. Insulators are things that do not conduct electricity very well. Conductors are things that conduct electricity very, very well. And semiconductors are ones that kind of don't do either, but kind of do. There's a bit of a mix. A bit of an odd mix there. So I'll show something to you. I'll draw a diagram. And the reason I want to draw a diagram is I want you guys to become familiar with energy diagrams and energy gap theory. So I want to start drawing these diagrams with you. The number one diagram I want to show is this energy. Energy is very low at the bottom and energy is very, very high. So if I were to talk about an insulator, we have the valence electrons, the electrons on the outermost shell. Right? The valence band, we'll say. And then we have conduction electrons. Finally, you get electrons excited, you give them energy, and they go. They're the conduction electrons. The difference between these two is called the band gap. So this is what I'm going to refer to quite often. This is the band gap. Not, you know, a bunch of rock stars in a band playing music. Adrian, thanks a million for your prime. Really, really appreciate the support. Thank you. Do quartz crystals conduct electricity well? I don't remember actually. Not on top of my head. We need to look at the bonding of quartz crystal to see if it is. I would assume no, but I could be wrong. So we mentioned this earlier, Shadow Pony, that there are different models for the atom, and all of them are incorrect and all of them are correct. It's just what we need to know to be able to do this. And so for semiconductors, this is a sufficient diagram. And yeah, that's the reason why we're using this at the moment. Now, the band gap is really, really important. Sorry, my mic. To talk about when we're talking about things like insulators, conductors, and semiconductors. If I were to physically move this band gap, I can move the conduction band or I can move the valence electrons, but basically let's move this guy down a bit. That was an insulator. Now this is going to be, again, a conduction band. We moved it down more and more. It's a smaller band. That's a semiconductor. And finally, we move this band even less, like really, really, really close. And this is a conductor. So the distance between the valence and the conduction band is so small. We don't need to put that much energy to actually get the valence electrons flowing to become conducting electrons. So this is what defines as a very, very good conductor or a very, very bad conductor, i.e. insulator. Something electron volts. So, something that is considered a semiconductor, an element, I kind of mentioned it already, is silicon. We like silicon. Silicon is a very good example of a semiconductor, and we do something called doping to it. Now, doping is a word that we will discuss a little bit more in future. But I think you might be familiar already with it when talking about, I guess the most popular term I see doping in is Olympiads or cheating. They take, drugs for performance enhancement, right? That's a term, doping. Quite literally in the name, we'll be doping silicon, i.e. inserting things into silicon to make it better or worse for different things. Does this conductivity rely on distances between these shells? Yes, so the more you are in the shell, the more energy, it's a higher energy level state, yes. So you'd increase in energy up here. You'd get higher and higher and higher. To give testosterone, sometimes testosterone and sometimes not, Grim. So you do both. With doping silicon, you want to do both things. And I'll talk to you about that in a second. Let me take a sip of water. So silicon is really, really good. Another thing that, okay, not another thing, but a thing that is a very good conductor is copper. What is the element for copper again? Or copper out. I'm going to draw a simplified version of copper because there's a few rings in it. How many rings does it have? It has 4 rings. So this is you. What's the element number for copper again? Does anyone remember? There's 2, 8, 16. You'll never catch me, copper. $29, thank you. I could have done maths, I just realized. And plus. Wait, is it not 27? Wait, did I do the mental math wrong? Why did I do my mental math wrong?
Final count.
42. It is not 42.
Oh, that's not bad for a pointy-eared elvish princeling.
Oh well. It is 29? Okay, I'll take your word for it, chat. So, you have the shell here, here. So this is shell 1, shell 2, shell 3. And in the 4th shell, you have an electron hanging out. Thanks for the 40. Appreciate it. During the summer, I'm streaming Saturday, Sundays, Mondays, Tuesdays, Wednesdays. I will be streaming tomorrow though, and I won't be streaming on the weekend because Ireland is going through a heat wave. It's 18. I put 16 in my head. There's my mistake. Okay, that explains it. But I'm not going to stream during the weekend. I'm going away. There's a bit of a heat wave in Ireland. I know that Europe has had their heat wave already, I don't know if the rest of Europe is going to still suffer, but Ireland is going to go through it starting tonight. Whew. So that is why I won't be streaming this weekend. I'm going away. Welcome in, Zero. But then during the semester, I'm a full-time lecturer. I'm a full-time researcher. I'll only stream on the weekends. So that'll be my only time properly streaming. Now, where was I? Train of thought. Yes. So we have an electron on the outermost shell here. We have one electron hanging out here. And it's in an extra shell, right? Which means that its valence electrons are in a higher energy state. It's up closer. So it's easier to get to the conduction band. That is why the valence band and the conduction band in copper, they're pretty much really, really, really close. It takes very, very little energy to excite the electrons in a copper system. There's a more like, I wouldn't say chemistry because this is still physics, but like there is a more chemistry outlook on this in terms of the bonding that exists in silicon with other silicon versus copper. It's got to do with the way the covalent bonds work with sharing the 4 electrons versus the copper, which is a metallic bond, and that electron is being shared in a pool of other atoms and it doesn't really belong to one atom. There's a whole spiel on this. But generally speaking, the way I've said it, the more the electrons that you put on the outermost shell, the more outermost shell you put it, the more conductive it would be. And so this is why silicon versus copper. Copper is a really good conductor. That distance is tiny, 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 while silicon isn't that tiny, tiny. There is a bit of a difference between those two. The electron from copper has an easier time escaping. Basically, an electron in copper has a freer ability or a higher probability of escaping parent basement, is the way I would put it, if you want an analogy of it. However, let's compare something, not copper this time. I'm going to talk about germanium. So germanium is another common semiconductor. What element number is it? 32? 16, 8, sorry, 18, 6, 4, 32? 32. 32 protons. 32 confirmed. Excellent, excellent. Oh, I actually have questions here prepared. That's very good of me. Valence electrons in germanium are in the 4th shell. Where are the valence electrons in the silicon? Let me move out of the way. So the germanium has 4 electrons in its 4th shell. Where are the silicons most outermost? Which shell? Third, exactly. Today was my physics test and I aced it. Nice, congratulations. Feels really good walking out of an exam that you did well in. Well done. Does this mean that the valence electrons have higher energy in germanium or in silicon? Is germanium what Germans eat for breakfast? I actually don't know where germanium got its name. Obviously named after Germany, but I wonder, like, who named it? For what reason, you know? Like, polonium was named after Poland because of Maria Skłodowska-Curie. She wanted to name it after her home country. Where's the story with germanium, though? That we exclusively do. So does anyone have a notion, a think? Does it mean that the valence electrons have higher energy in germanium or in silicon? Let me move away from the board. Just let me show it to you again. Do you think germanium here with 4th shell has higher energy in its electrons than silicon? Okay, thanks, Salation, for the tidbit. I'd guess lower. Very unfortunate. But that was a 50-50 gamble. And unfortunately, it's okay. Listen. I kind of said it earlier, but Benjamin Franklin, when he discovered how electrons or how energy is stored in capacitors, there was electrons being stored on the inside or the outside of a capacitor, and he had a 50-50 chance of gambling which was the negatively charged particles and which was positive, and he guessed wrong. For the next 200 years, we've been using current flow as positive flow of charge, when in reality, electrons flow in the opposite directions. So, look, we can make mistakes, and it's completely okay. So germanium, its electrons have higher energy. Its valence electrons, because they're in a higher energy state, okay? More outerwards, more higher energy state. However, this property, I have a few notes on this, makes germanium more unstable at high temperatures. It is unstable, and it results in excessive reverse current. This is why silicon is mostly used as a semiconductor. Now, that being said, there is a lot of experimentation done on germanium. I was in this field 7 years ago now, 6 years ago, and germanium was very much still in academic papers. It was still being very much so highly researched. What does higher energy state mean? Honestly, from this explanation, using this Bohr model, it's quite literally another energy level where electrons can. And electrons will always exist in the lowest energy available that is available to it. Meaning, the first 2 electrons will always occupy the first orbit, and it will always be 2. The next orbit is 8, and the next 8 electrons will orbit that energy level. Finally, again, the next energy level, a bit more outside, higher energy state. And the third one is 18. I always get confused. I always think it's 16, but it's actually 18. Again, this is a model of the atom that we use for semiconductors. It is not the most complicated and most truthful model in the sense of all the information you need. You don't need much more to be able to understand semiconductors. That is why we use this model. Exactly. And you always have to occupy the previous one. It's kind of like if ever you went to a concert or a show, you can't just go in and sit in the first chair. Or maybe you can. But usually when there's what is it called? Those vigilators? They always tell you, no, go down all the way to the bottom so that the next person can occupy the next chair, so that the next person can occupy the next chair. Ushers, that's the word, thank you. When people usher you, they ask you to move all the way down to the lowest chair first so that everyone can occupy the chairs one after the other. That's kind of how these electrons occupy their energy shells as well. Do you need an iPad to study? I've never had an iPad, so I guess I'll say no. And I've studied quite a lot. Oh, please don't freeze on me, laptop. Okay. So, if we look at an intrinsic model of silicon, a bit more involved here. Let's look at the outer shell of silicon. Okay, so we have silicon here. Usually, when silicon is in its crystal structure, I don't know if it's referred to as a crystal structure, I'm happy to be corrected on it. But what actually happens is that silicon forms a covalent bond with other silicons. They share their electrons in a crystal-like structure. Lattice structure, anyway. Hope you find something educational here. Eternal Loss, welcome in. Hi, Millie. I'm static and hyped over it. Excellent. So what happens basically is an electron shared here, electron shared here. Yeah, I'll draw it with the overlaps. Electron shared here, and electron shared. Hold your horses. Silicon has 4 electrons on its outside shell. 1, 2, 3, 4, 5, 6, 7, 8. Wow! By doing this covalent bond sharing, this silicon now has 8 electrons when it's sharing its electrons with other silicons. Now you might say, oh, but that's not fair. The other silicons don't get to share any of theirs. They do. This lattice continues. Because of this structure, you can continue over and over again, overlapping here, overlapping here, overlapping here. That's what a lattice structure pretty much is. And this is something called an intrinsic crystal. So this is the word I'll be using. Intrinsic. You might see this in publications or in, remember I told you, I'm giving you education so that when you read any of these semiconductor news, they might say something like this, intrinsic. Intrinsic means there are no impurities in your structure. What does that mean that there's no impurities? It means, remember that I hinted earlier, that there's no doping done. Again, doping is injecting yourself with cheating chemicals to make you perform better. We're not cheating with silicon, not yet anyway. It's an intrinsic lattice. We haven't doped it with anything. It's just silicon there. Hi, welcome in. But what about silicon atoms that live on the border? We're not going to talk about that. Tofu's moderation team is intrinsic, are they? If you use the word intrinsic in the English language, what do you guys think it means if you're reading a book? I feel like intrinsic means fundamental. Like important to the core, inherent. Yeah, I wonder. Originating from the inside. Okay, I would agree with inherent. Okay, cool. I'm glad, Splishby. Who's getting the boron? Won't be getting morons just yet. Now, remember I talked to you earlier about the fact that electrons can only exist in certain shells, okay? Electrons, they can only exist as 2 in the first shell, as 8 in the next, as 18 in the next, right? A thing that's important important to know is that they can only exist in discrete energy levels. This is crazy. The reason I say this is crazy is because if you look at an atom and you can imagine an electron moving all around it, for me, this was mind-boggling. It was like, how do you mean it can exist in discrete energy levels? What does discrete or continuous mean? Again, a quick revision here. Discrete means you can only live on the first floor apartment. You can only live on the second floor apartment. You can only live in the third floor apartment. You can only live in the fourth floor apartment. Okay? That's what discrete means. You can only exist in certain levels of the floor. Continuous means that you could exist anywhere in between, up and above and beyond. That means that you could exist between the first floor apartment and the second floor apartment at a ratio of 1.6. 7259. You know what I mean? It's a very weird thing. And you might be saying, well, isn't everything in the world discrete? No. Numbers are technically continuous. You can have as many decimal places as you want in number scale. We're going to get very philosophical if we actually talk about mathematics here, so I'm going to jump ship before I offend any mathematicians. But discrete levels, living in the apartments. Electrons can only exist in discrete levels. The other aspect of a continuous that I like to talk in physics is the light spectrum, the electromagnetic spectrum, from radio waves to microwaves, all the way to light, all the way to cosmic rays, UV light rays, everything else on the bottom. There is no discrete energy levels. It's a continuous spectrum that is undisrupted. That is an example of a continuous spectrum. And classical quantum physics, that's a very weird thing to say. We talked about electrons being in discrete levels is the other version. I live between floors. We will be talking about holes, yes. So, this is the nucleus. Usually this diagram is actually at 0 degrees Kelvin. We won't talk about that too much, but this has got to do with the third law of thermodynamics, but you know, a little bit of a talk for another day. So let's say this is energy going up. And go. We have the first shell, second shell, third shell. So we have electrons existing in each of these shells. 1, 2, 4. This is a diagram for silicon. The electrons cannot exist between these bands. They can only exist in discrete energy levels in ratio of Planck's constant, but that's another story for another time. And the difference between them, by the way, is called the band gap. Remember, I talked to you about this earlier. Not a band inside a garage, but there is a band gap between those two guys. Electrons are band nerds, kind of, yes. Now, let's zoom in and we can talk about something really interesting, very controversial. And the reason I say it's controversial is because this is kind of not intuitive. We're going to talk about imaginary things. And in reality, imaginary things are not that hard to imagine. Most things in the world are imaginary. Negative numbers are imaginary. That's a bit of a controversial statement, but you know what I mean. There's all these different kind of concepts and ideas that you might be taking for granted, but in reality, it's okay to talk about these systems better. The thing that I'm going to introduce to you, the concept of holes. We talked about electrons a lot. They're negatively charged particles that float around the outside of this, outside of the shell. What I want to mention is something called holes. And it's something that an electron does when it leaves its atom. Do you know do you know when you're in love and you found the love of your life pretty much, but they break your heart and they leave you? And you say the figure of speech of there's a hole in my heart where they left. That's kind of what happens with semiconductors and electron hole pairs and everything that I'm going to be mentioning. When an electron leaves, when an electron moves, it creates a hole in the material that it left. It leaves a gap where it's meant to be. Yes, this is a romantic story of semiconductors. No, nah, I can't relate. Fair enough. Fair enough. Talk about energy. In case you guys are wondering what I'm referencing, I'm just referencing my own lecture notes. I made lecture notes in preparation for today. Totally not going to recycle these for my students. Cough, cough. Yes, came here for the physics, stayed here for the quantum soap opera. Now, let's say this is the valence band, i.e. the electrons on the outermost shell. They're the electrons that are available for our story. So let's say, and this is the conduction band. This is the band to get electrons to be conducted. Make them flow in a current, right? Band gap. Now, for us to get an electron up and the other, we give this energy, we give the system energy, we increase the energy. It goes from here, and we give it energy. And so what happens is one of these electrons says, woohoo, I have enough money to finally leave my mom's basement. What does it do? It packs its stuff and it moves. The electron moves into the conduction band. And what it does is it leaves a hole in its mum's heart. You left your mum and you left a hole in her heart. So when the electron moves, it leaves a hole. This is not a real thing. It doesn't physically leave a hole, but it's just a concept, a story to explain this, because a lot of things are going to be moving, a lot of things are going to be interchanging. So this is the story that we use to explain these. I'm not trying to make you all sad, chat. I'm sorry. I think mom is, that's true. Maybe mom is happy, to be fair. To be fair, I think maybe mom is happy. So what happens here is that first of all, we've made an electron move from the valence band to the conduction band. We have a conducting electron. Yay! The other thing that we have is we have a hole. And so when this happens, when electrons get enough energy to move into the conduction band, we say that we made an electron hole pair. This is what, if you ever see this in any articles, the electron calling my mom right now. Did I inspire all of you to call your moms? It leaves home during a crisis. Yes, there is a huge housing crisis in Ireland, to be honest. I advise you to stay home for as long as possible. Save money as long as possible to be in Ireland. Which is 99.99% empty anyway. That is true. That is true. Another thing that to kind of highlight, I have a little note here that I say a recombination occurs when a conduction band loses energy and falls back into the hole in the valence band. So basically another thing can happen is suddenly the electron doesn't have the energy to be in that conduction band, and the electron can move back into mum's basement basically. When that happens, when that electron moves in here and the hole gets replaced, the electron goes back in there. This is what we call recombination. Okay, so there's two definitions: recombination and an electron hole pair. It's okay, no one's breaking into my house, West Banana. Thank you for your concern though. So what ends up happening is we can have the possibility of two things flowing. We could have basically positive charge flowing, and we can basically have negative charge flowing. Now, in reality, again, from a physics perspective, there isn't really anything flowing, but it's an apparent flow, right? It views itself as flowing. And so what can actually happen is you can have electron flow flowing in one direction, and you can have current flow, you can have electron flow in one direction, and you can have hole flow in the other direction. And so there's some things called electron current and hole current. Don't need to know too much about it. But if you look at silicon, let's zoom in at silicon here. Silicon 1, silicon 3, 4 silicon, 5 silicon. And so what ends up happening is, as an electron gets emitted from the surface here, yay, it got enough energy to move it out, it has a hole. The electron here moves in here to replace that hole. But that electron now has created a hole. the hole over here, the electron from here wants to move to this guy, but now as it's left a hole. And so the electron from over here will want to move into this hole, and then it leaves a hole behind. And then, so the electron from the previous atom wants to hop into this electron, and so it replaces this hole, but it leaves a hole as well. And it goes back and forth and back and forth. And so what you visually see, you see a visual flow of electrons going this direction in silicon, and you see a visual representation of holes moving in this direction. The infinite hotel electrons. Whew, I'm out of breath after that explanation. Got out of the while. I mean, that was a while loop, wasn't it? That was a tough loop to get out of. Jesus, I need to drink so much water with all the talking I do. I don't talk this much usually. Like my physics sessions are usually about 2 to 3 hours, and then I play games. Whew, this is tough. This is tough. Oh, sorry, I hit the mic. We're about 5 hours in. I can do this though. I can do this. Electronically wholesome. Okay, so we're actually getting good coverage here. This is amazing. I'm really, really proud of us, chat. Because now we can talk about something really cool. We can talk about N-type and P-type. We're going to start doping stuff. That came off bad. No, that actually came off correctly. But it can come off bad. We're not going to be doing the doping thing again, what we think about in English. What we're going to do is we're going to change the silicon structure a little bit. We're going to spice up our silicon life. Now, semiconductors, I mentioned earlier, are very, very good. Semiconductors. They're not very, very good conductors, but they're not terrible either. And so something that we do to semiconductor devices to make them possible is that we dope them. We add, for my burps, we add another element to silicon to change that energy gap. Okay? So there's two things we want to do. We want to make it one side more electron heavy, and we want to make the other more hole heavy. So that's basically what we're going to do. I'm going to teach you how it's done. This first. I might need to take a break. I've been drinking so much water, I just need to use the bathroom again. I apologize. So I might really, really quickly run to the loop because this is a new topic, N-type and P-type doping. So what I might do is I might go to the bathroom really quickly before we start this, because this will be a good natural break. I won't have another natural break for at least half an hour. So I'm going to run really quick. I'm going to have a pee and fill up my bottle of water. Be right back, chat. I'll put on another video for you. One of the big problems about studying is it before we start our P doping and N doping. Oof. Sorry, she's hiding right behind me. I can't really get her in the camera. Bambi, do you want to come say hi? Oh, there she is. Oh, let me move this. Trying to move the mic around her. Hi, Bambi. You're on the front page of Twitch. Yes, you're a celebrity bunny now. Okay, bye. She doesn't care for that stuff. Oh, she's thinking. She's thinking. Does she want to be here or does she not want to be here? And she's gone. So if you guys don't know, that is Bambi, my bunny. House. Laptop is here. I'll just move it for now. I am using my laptop as reference. I have my own lecture notes. Guys, I know we're in the front page. Sorry. Have boxes ready for a lot of demos later today. If you guys don't know me, I know that I didn't do an introduction for a while because, you know, I was trying to get a lot of teaching done. This is Introduction to Electricity, and so if you came in the middle of some lessons, it might be confusing, but there are breakdowns in lessons. So we did 2 major lessons. This is the third one, which is on semiconductors, and I did take a little break there. I just need to sit down for a few minutes and stretch my legs out, or the opposite, sit my legs down for a few minutes. I'll get my coffee in a moment. And we're covering semiconductors. We're doing a lot of theory with semiconductors. And then after that, we're going to talk about magnets, electromagnets, and I'm going to teach you how DC motors work. And the reason I want to teach you about DC motors is it's going to take forever to build it, number one. But number two, it just gives you a good feed of how power works, how like big, massive generators supply energy to our whole system. So I think it's really, really cool. Was magnets? Yes, very minor electromagnetism will be on the syllabus, Jibby. We haven't covered it just yet. Bunny, yes, we have some bunny emotes as well. We have Bambi hello. We have Bambi hop hop. And we have Bambi math. Because if you noticed, she might come in sometimes and she'll actually eat the books. She does love eating those books. So the last thing she ate was Richard Feynman physics lectures. It is up to chat to decide if that's a positive or a negative thing. Oh, good coffee. Oh, good coffee. Good water. Good water. So yes, we'll do some P doping now. Or no, N doping first. N doping is kind of easier to explain. Basically... Oh, sorry, I forgot. I was going to do an introduction and I got distracted. Let me go back to my train of thought because I introduced Bambi. I didn't introduce myself. Hello, I'm Dr. Tiny Toxic Tofu, or Dr. Toxic Tofu, evil tofu. I stream science and technology education and video games. Today is a very special day. I am on the front page, which is really, really cool. I'm so glad to see science outreach on the front page of Twitch. And specifically for today, I'm covering something called Crash Course Electricity, where I did Ohm's Law, potential dividers, resistors and series parallel combinations. Now we are doing semiconductors. In real life, I am a full-time lecturer and researcher. I have a lot of time off over the summer, which allows me to stream a little bit more. But during the semester, I will only be streaming during the weekends, while it's summertime, I have a bit more free time. I technically experiment on my lab rats. My community is called Lab Rats, where I test out ideas, experiments, constructions, buildings with my community on Twitch. And before I use them on my real students in actual real lectures and classes. So I test out lessons. I test out an experiment or a demo. And if it was really bad, I don't do it. Or chat helps me and comes up with better ideas of how to teach it better. We are the beta. Maybe even lower than that, Amelia, but yeah, that's the right thought. We get Cheetos in return. We get chocolate rations. Whoa, I get to be a lab rat. Yay, you do get to be a lab rat. We also have lab rat emotes, and the badges for subscription are different levels of lab rats. So if you're first month subscriber, you're a mine rat. Then you become... What's the next one? It's not a lab rat. It's like a rat, the worried one. Oh, what is it called again? Anyways, there's that. Then there's the lab rat. Then there's technician. Then there's senior. Then there's radioactive. And our final ranking, the final ranking is radioactive at the moment. Hey, Javad, thank you so much for the Prime. Really appreciate the support. Rat wants a treat now. Well, our chocolate rations are down at the moment, unfortunately, lads. The economy is tight. Chocolate rations are tight these days. All right. Let me pull up this bad boy here, which is my laptop and all my lecture notes on it. So even though this is, like I did prepare for the front page, this is also an experiment. I've prepared all these lecture notes in preparation to see if what I'm teaching is sound and good and cohesive, and if I need to alter a few things. So thanks, lab rats. I appreciate letting me, experiment on you. And we're all still around, right? We all survived. Maybe. Last pay raise was an increase of chocolate rations by minus 20%. Exactly. Hi, Silver. Organic kale to be... Stop. I'm still looking for organic kale. Who knew organic kale Or just kale and has season. Did not. I learned. Excellent. Okay. Let's talk about N-type. Now, N-type doping is kind of hidden in the name, N negative. We are going to be negatively doping our silicon. We want to adjust something. We want it to be ever so slightly more on the negative side than the positive side, i.e. hole 1. Welcome in, Simmer. Thanks a million. So, to increase the number of conduction band electrons, specifically we want to increase the amount of electrons that can exist in the conduction band, we need to dope silicon with intrinsic silicon, so it's not doped, but we need to dope it with pentavalent impurity atoms. What the hell is that word? Now, what we're going to look is, what we usually dope them with is elements such as arsenic, phosphorus, bismuth, and antimony. Have I ever used antimony before? So usually in these kind of things, we use phosphorus, if I'm not mistaken. Again, I'm not a semiconductor expert, but I think phosphorus is what's used in these kind of things. Penta means 5. You're absolutely right, chat. See, you guys are smart. So, there's a reason why we use that word by the 5, penta. It's because what we need to do is we need to make the silicon structure, or the structure of the, the crystal lattice. We want there to be an excess of an electron. So remember the silicon had, do I have that drawing still? No, I don't. Remember when I drew the silicon, it had, it shared 4 electrons, right? We made it share electrons. We want to do the exact same thing. Well, we want 1 excess electron. If we make a covalent bond like this with silicon and let's say phosphorus or antimony or any one of those ones, right? If we make a bond like that with it, we're basically not evacuating. What's the word? What's the word when you forcefully push someone out of a house or a renting place? Evict. There we go. Thank you. We're basically evicting 1 electron. We want to prepare a crystal structure where we're going to readily evict 1 electron. Exactly. We want one of them to be ready to go. And that's the idea behind this. We're going to dope a bit of the silicon to make it N-type, to make it have an excess electron. Technically, no, it's still an ion. Everything is fine. Everything is neutrally charged. But in terms of stability, it's not happy with that excess electron. Because the pentavalent atom gives up an electron, it is often called the donor atom. So that's what it's referred to. Sorry, I'm reading from my little notes here. Ah, yes. So there isn't a hole being created in this production, by the way. We're not pushing an electron into the conduction band in this case, like we did earlier. It's already readily available. So there isn't a whole pair being created like we were talking about earlier. Some holes can develop, by the way. So you can have still holes developed, but that's naturally going to occur. Something that we don't talk about a lot or too much of is that electron hole pairs are created all the time. They're wishy-washy. They create over here, they're created over there. They happen continuously. And that's just because of statistical physics, number 1. Number 2, entropy. I love to talk about this. Heat can flow one way, but it can actually flow the other, just statistically, possibly that the molecules won't end up on the other side as much as the other. Anyways, my rant being is that even though you might dope this side of silicon with a bunch of electrons, there will still be holes created. Not much, but some holes will be created. Thank you so much, CP Players, for the prime. Really appreciate it. Precious. Speaking of precious, I'm going to grab my coffee. Be right back. Behave, chat. Okay, I'm here. Had to have the coffee. Oh, fan is laptop is hot in here. Woo! It's getting hot in here. Da, 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 da. Where do you think she hides the treat? I'll tell you. My treats are over here. I don't think you'll like them, Chad. They're my treats. They're for Bambi. Ah. I don't think you're gonna like them, Chad. But she'd kill for them. She bites me over them. Anytime she hears this jar, she comes running in. Yes, she growls. She does growl. The vicious creature. The dragon incarnate. Okay, where was I? My notes. Da, 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 da. So yes, there are holes being created. Of course, they're passively going to be existing. They're going to happen. But generally speaking, we're mostly doping a silicon with extra electrons. Now, that's what's N-type called because it's negatively. It's negative, right? Now, P-type is positive. So remember, our silicon has 4 electrons on the outside. We doped it with pentavalent electrons or pentavalent atoms to make it have excess electron. Now think about it. If we want to make it positive, we want it to have holes. We want it to have gaps in its system, which means, hold on a second, we probably need an atom that has 3 electrons on the outside. We want the opposite to be true this time. So I think it's called trivalent. I don't know if I have it in my notes. But we want trivalent impurity atoms to be added to increase the number of holes. And these would include something like boron. Yes, yes, insert boron jokes. Indium and gallium. Gallium is quite a popular one. I think my research kind of touched on that as well. What are we discussing here? We're talking about N-type and P-type doping in semiconductors. If you're jumping into the stream, it might be a bit difficult to keep up because I spent about an hour and a bit on this already. But if you want to hang out for a little while, I'll finish on the topic of semiconductors, and then I'll be moving on to magnetism, which will be a new topic, and you can come in and start from scratch again with me. So, a trivalent atom can this time will be F silicon, right? We have an electron or silicon here, silicon here, silicon here. Let's say we make this boron, right? Have an electron here, shared here, shared here, shared here, shared here, but over here, instead of the 8th electron being shared because of the trivalent bond, have a hole. We've created a gap in this guy. And so, this is how you make a P-type semiconductor, P-type material. You make, you dope it with something that has 3 electrons on the outermost. And so when a crystal lattice is formed, it has a hole created. Something that I didn't mention earlier before, but in N-type material, your majority carriers are electrons. Kind of in the name, it's the majority form of flow of current that's going to happen. In a P-type, your majority are holes. That's going to be your major talking point or major discussion. Now, of course, there are a few conduction bands as always. There will be electrons ready to be in the conduction band, but again, this is passively made. Well, not impurities as much because semiconductor production is actually days. It's a really, really accurate science now because it's been around for so long. But usually thermally generated is a popular one to talk about. Now, I talked about P-type, I talked about N-type. Time to put everything together. Quite literally. We are going to put a P-type material in conjunction, in joint with an N-type. So, that now? Hey, Sleepy! I'm so sorry, I was a little bit slow there. We're going to put P-type and N-type together. We're absolutely going to do it. And I'm going to try my best to explain theoretically. So, I have a diagram drawn here. Let's say this is the P region. This is the In the N region, we kind of have an excess buildup of conduction band electrons. What's really important to note, by the way, this is a bit of maybe a possible misnomer or misunderstanding. it's not a positively charged particle or a negatively charged material put together, right? These materials, in terms of net charge of like the elements put together and everything like, they're neutral. I'd like to highlight that. This is why I'm trying to get your brain working with p-type and n-type, about doping, about electrons being in the conduction band or in the valence band or being a bigger gap and things like that. They're not ions. They're not net positively charged or net negatively charged materials. They're neutral. So this is kind of like an important point. This is why I spent so much time about electrons in the conduction band and holes being created in the process. We have a lot of electrons. And of course we have some holes. Like I said, thermally generated holes will exist. And in the p region, we have a lot of holes with a couple of electrons, okay? And we put these two together initially. What happens for the first few seconds of creation, right? Let's say we're playing God here. We put these two guys together. There is someone walking around in the house, in case anyone thinks it's Maxwell's demon haunting me again. It's okay. For anyone coming in, there's a very interesting thought experiment called Maxwell's demon, and I hate it because it doesn't make sense to me. I do understand it. It's just, I don't think it's a really good thought experiment. Anyways, if you want to search it up, you're more than welcome to, but the joke and the lore in the stream is that Maxwell demon haunts me to this day. Now that lore is explained, let me have a sip of coffee. Coffee, good coffee. When we put initially these two materials together, they're not in equilibrium. We've just mushed them together, and yeah, there is a bit of a junction really, really quickly. We call this the p-n junction. Why do we call it that? It's the point they join together. It's quite simply just that. Note, despite there being loads of electrons and holes in the respective regions, there is net zero charge. Just to remember again. So if I put a voltmeter across this, there is no potential, okay? There is no potential charge. This is a net neutral material. So again, I hope that I've reinforced that. The free electrons in the n regions are randomly drifting in all directions. Now, just to kind of emphasize this is very chemistry and electrochemistry and things like that, but also classical fluid dynamics and physics. But if you guys remember, this is a bit of entropy, this is a bit of statistical physics. If you have a bunch of red balls floating in your air around us, and you have a bunch of blue balls. And let's say this is a bit of a Maxwell's demon problem actually. Let's say I picked all the blue balls and I put them all in this room and they're floating about, right? And I picked up all the red balls and I put them over here and they're all floating about. Let's say I put them together. There's nothing interesting about these balls other than the fact that some of them are red and some of them are blue. Stop giggling, chat. Jesus Christ. Come on. You're adults. Well, maybe. Yeah. Anyways, there's nothing weirdly different about these balls, okay? If you give them enough time, they're floating around, they're going left, they're going right. Even though the majority blue balls were over here, majority red balls were over here, over time, they're going to scatter and overlap. The more time you give, the more scattered they will be. This is just natural diffusion. This is natural statistical, where things have a probability of going one way over the other. Now, where entropy and heat and thermodynamics comes in is that, let's say the red balls are given a lot more energy and they move a lot faster. That is the case. They tend to move a lot more than the blue balls, and that is why heat travels through things instead of cold. That's where the concept, by the way, just a side rant. Okay, now the same thing is happening here. The electrons in the n region are diffusing in this direction, and the holes from the p region are slowly diffusing into this region. Because, well, it's just natural. It's statistical physics. It's bound to happen over time. For every electron that diffuses across the junction and combines with a hole, positive charge is left. So with this recombination that occurs, you built up a positive charge in this moment. You do this over time, right? One goes over, fills up with an electron pair, you've held up a positive charge. But because an electron left here, you're building a positive charge. But because an electron came in here, now you're building up a negative charge. And so what happens is, give it long enough, and this region gets bigger and bigger. And what actually happens is you build up a barrier. There's a whole bunch of negative charge here now. And there's a whole bunch of positive charge here. There is huge potential difference now being built up until it reaches equilibrium. Give enough time and it will reach equilibrium. And suddenly, there's an electric field inside our semiconductor. Suddenly, we have a huge potential buildup. And this is the beauty of the p-n junction. This is the beauty of semiconductors. And this is where physics just goes crazy with electronics. Absolutely amazing stuff starts happening. We call this, by the way, a barrier potential. I don't know, like it is a barrier, sure, but it is referred to that. And I'll explain in a minute why. I'll just write it down. Barrier. It is pretty dope. It is. Does that make sense? Is there any questions? I'll actually look at chat properly. If you guys have any questions based on this barrier potential that I've explained. I hope I've explained it kind of okayish. I know if you came into the stream and you didn't, you're jumping in a little while earlier. Yeah, it's called a depletion region as well. Yes, absolutely correct, Sleepy. Is a capacitor created through this process? Very similar, easier. It's way easier. You don't need a fancy equipment and fancy doping in a semiconductor, in a capacitor. All you need is 2 plates and you need a bunch of electrons to be available on one side. You build up a bunch of electrons on one side and the lack of electrons on the other builds a supposed positive side and you have a big potential. Very basic idea, but absolutely true. Oh, I've seen a lot of them, Alchemist. They're very good, yeah. I think I know which ones you're for. I think I use them for my lecture notes. Exactly, Ice Crack. It's a little bit more complicated only in terms of the train system that exists and the way the voltaic piles, not the voltaic piles, the solar piles, not solar piles. Oh my goodness, PV. Sorry, I've been streaming for too long. But the idea is absolutely correct, yes. Now, oh, I actually write a little thing here, Sleepy, by the way. I have something in my lecture notes. The term depletion refers to the fact that the region near the p-n junction is depleted of charge carriers. That's why we use it. So remember I said the n region, the charge carriers are the electrons. In the p region, the charge carriers are the holes. In this case, the depletion region is called the depletion region because it's depleted of its carriers. So that's where the name comes from. I had it in on my own lecture notes. I just forgot about it. It will get larger and larger until it reaches an equilibrium point. Until this potential becomes too much that no more electrons will come in anymore. Allowing current flow in one direction but not the other is a fundamental to the operation. Yes, so hopefully, especially for people who are familiar with this, maybe this is like a click moment for you, an aha moment. Oh, there's a buildup of negative charge here. There's a buildup of positive charge here. We need to replace the electrons that are supposed to be in the n region so we can continue the flow, i.e. current can only go in one direction. But because of this electric field buildup, current can't flow in the other direction. So there is this forward and negative. I'm jumping ahead. I will cover this. But in case anyone is already familiar with this, hopefully your brains are kind of clicking now as to why, from a fundamental physics perspective, semiconductor works. Okay, so suddenly now we have a big potential difference. We've built up a quite literally a big energy difference between the P region and we have a voltage buildup, right? There is a voltage difference now between here. How do we overcome this voltage, chat? We supply it with voltage. So let's say I build up about, let me use a curious number here, 0.7 volts. Let's say there's a buildup of 0.7 volts here. How much voltage do I need in my circuit, let's say a simple circuit, to get current to actually flow? Oh, thank you. I like it too. I need a dress. It's really, really hot right now. More than 0.7. Exactly, Empu. Second that comment. We need 0.7 volts or more to actually get current to move. If there's a buildup of 0.7. Now, you could have a little bit of current flowing through just below 0.7 or just around 7. And I'll show you the graph in a second. But you guys are physicists now. I taught you everything you need to know. Remember what I said about statistical physics. There is a probability always associated that something can move in the other. Let's say hot always moves from hot to cold objects because they have higher kinetic energy. They have a higher probability of moving from the hot place to the cold place versus the cold objects into the hot place because they have lower energy, lower speeds, all of that good stuff that we know from statistical physics and classical kinetic theory. So think about it from this perspective, that we give some of the electrons a certain amount of voltage, but just by pure statistics, right? By pure probability, a couple of things are going to cross over. And so that is why I'll show you the graph in a second. It's not a direct, just immediate straight line slope. There's going to be a tiny bit of a curve. That was a mean question, giving us the 0.7 and me not knowing anything about it. I was sure the answer was 0.69. Well, you were close. 0.71 would be an ideal. Yeah. If you connect a voltmeter across a diode, why don't you see 0.7 volts? Excellent question. You mean when it's not connected to a voltage source, when it's just external? Why do we not measure 0.7 volts? Is that your question, Techie? If I grabbed a voltmeter now and I just measured it across here. Yes. Brilliant question. Where would I put the voltmeter? I put it here. Remember what I said about a P junction and an N junction, or like a P doped material and an N doped material? They're not ions. Yes, there are majority carriers electrons and majority carriers holes, but they're not ions. There is an equal amount of protons and electrons. Everything is neutral, everything is fine, everything is in equilibrium. When you put these guys together, there is a bit of a shuffle and movement around electrons and holes in the middle, but the total story is still the same story. There's still the same amount of electrons, there's still the exact number of holes, and there's still neutral. If there was some weird way that you can measure the potential over here, then you would measure potential inside the semiconductor. But the potential difference is only in the p-n junction. In the total big story, there's no net change. It's kind of like, let's say, I don't know why I'm bringing this example. Let's say we're out nightclubbing, lads, all right? And there's boys and girls nightclubbing. Whoop, whoop, whoop. This is the room. And let's say boys and girls got split in half. Not physically. I mean, like in the rooms. There was a boy corner and there was a girl room, and we're dancing all night, okay? Now, then someone said, then they put those rooms together, they go, and they allow people to mix. So there's a big mixing thing going on here in the middle. Okay, they're all mixing, all the girls and boys. There's still a lot of girls on this side. There's still a lot of boys on this side. But there's a lot of mixing going on in the middle. Now, you put in 100 girls in there. You put in 100 boys in there. Something happens. You step outside and you look away. There's still 100 boys in there and still 100 girls in there. Nothing has changed. That was a really weird analogy, but I hope that helped. Probably shouldn't be using that analogy. I don't know why. Does that answer it a little bit, or did I make it worse? Hi, Gov. Welcome in. Sometimes I come up with weird stuff, man. An increase in total population. That is true, Alchemist. I probably shouldn't have done that. Does the PN junction shuffling generate any heat, for example? Oh, I actually don't know. So the whole production of semiconductor industry is really huge. We have a huge one in Ireland. There's a lot of companies that do it. I actually have no familiarity with the actual applied physics aspect of it, the experimental side of building them. It's a good question though. Genuinely don't know. Based on the amount of material side. Yes. So that is when you get an LED or a diode or anything, it will tell you what voltage you need to overcome at rating. So it will give you the number because do you know that crystal structure lattice that I talked about, the P-type and the N-type doping? It is so well done. This is a science that has been perfected for many, many years. And so it's really, really well known and the structure is really, really good. And so they can get it down pretty accurately. Okay, so that is an explanation of P junction and N junction, and that is where all my notes end. That's all I was able to prepare. But I think this is a very simple concept that I can teach you very, very quickly, which is finally to get to a diode. A diode is a P and N junction. And I'm going to show you something really, really quick. Sorry, I have a few notes on solar panels, but I'm going to save that for the charity event. Like I said, I'll be doing a charity down the line. Next week, I think, or the week after. So I want to explain what a P junction is really quickly. Or sorry, what a diode is. Do I have any notes on this? It's okay if I don't have any notes. I should get this correct. Just bear in mind, like I might say something, not say something incorrectly, but I might not have the full knowledge on this. I'm working on something called memory at the moment. So, and I haven't done all of this in a very long time. Let me... Okay. So chat is more than happy. You're more than welcome to participate if you guys know something. Hey, Sagi, thank you so much for your prime. Precious. Thank you so much for your support. You're very, very kind. It is, that's right, Evil Perf. We were mentioning earlier that germanium is super unstable thermally. That's why it's not used. But you're absolutely right. The whole construction and the whole, like technically as 4 electrons on the outermost shell, it should work very similar to silicon. But because it is very thermally unstable, we don't use it. So if the voltage is only in the junction, how do you use it? Perfect question. We're about to get cracking on that. So here we go. We have a P-N junction. I've explained how it works now. Right. Do I have anything to help me with? It's okay to make a mistake. I make mistakes all the time, but I'd hate to make too many mistakes. Front page kind of. Okay, so we have N and P, and we have electrons flowing this way. We apply a voltage. We have a buildup of a potential, let's say 0.7 volts. Very suspicious number, are you? Now, when we're looking at the zoomed in, we're looking at it this way. We have electrons flowing in here and electrons flowing out here. And let's say we apply 0.7 volts. We overcome this barrier. What happens? Well, we have a bunch of holes here that when the electrons come in, they will conjoin together. They want to be replaced by the next number. This collapses here in the middle. The electrons that are in here will flow in this direction. And so to continue replacing everything that we're doing to these guys, the holes need to be regenerated, the electrons need to be regenerated. And because it's going in this direction, this from, wait a second, did it wrong. Haha, told you. This is why I wanted to make sure I had notes. I knew I made a mistake. We have electrons here, N-type. We have holes here. We have a barrier to overcome. We overcame the barrier. The electrons are coming here. They are joining whole pairs. Some excess electrons are being used to cross over here in this direction. Because the electrons are being lost as they're transferred over here, they need to be replaced. That's being replaced by the current that's flowing in this direction. All good. This is what we call force. In semiconductors, this is the language that we use, that this is why directionality is super important. This allows the electrons that are moving, annihilating, recombination. Recombining? Yes, I suppose you can say it, recombining, and then the electrons continue to flow out. We're constantly replacing between these things, and we allow current to flow. We're happy. We've overcome the voltage, i.e. we've set our voltage source to above 0.7 volts, and the current can flow. Yay! Hi, Gia. Welcome in, welcome in. However, let's do the opposite. What happens when I make the electrons this way? Well, the electrons come in here. There's a bit of annihilation going on, but you know, nothing gets transferred across here. We're not replacing any electrons because there's no electrons flowing. There's kind of a traffic jam, actually. Nothing can happen across this depletion region anymore. So this is what we call a negative. Is it negative bias? This is why I should have had notes. The negative bias, chat. Can I? Physics teacher. Welcome in, welcome in. It's reverse bias. Thank you. Reverse bias. Reverse bias. And so electrons can't flow in this direction because of this idea. This is amazing. We have an instrument that allows electrons to flow in one direction only, for one. Number two, Frank McCourt, if it meets a certain voltage threshold. Two super important conditions. Vitally important. And you might be thinking, so what? I don't care about that, which is fine. That's fine. But it can be used for so many cool things. You can now do a lot of really, really interesting things. You can put a thing where, well, if current flows this way, I allow it in. If it flows this way, I don't allow it in. This is, what is it called? A rectifier bridge, I think it's called. This is where you can change AC circuits into DC circuits. There's a lot of really cool things that you can do about it. You can also have a system, like a Zener diode, where you only allow current to flow when it meets a certain threshold. And you can have very efficient switches. So for example, you could have let's say a thermoresistor or a luminosity resistor. I don't know what it's called, where you know shine light and it's less or more resistant. And you can have a light switch set up. And so if you have a Zener diode in your system, you can be super efficient about it. It won't just eat all the power and your battery will die very, very quickly. Instead, you can put in a diode to ensure that your system works super, super efficient. Is this relevant for 12th grade? Maybe in an electronics thing, but not physics. I don't think this is taught in a lot of physics degree, 12th grade. This would be, yeah. Not in Ireland anyway. We don't, photoresistor, thank you. Thank you for helping with the English. Photoresistors would definitely be the one to use that for, yeah. Oh, I'm sitting down because I'm tired, but one last important thing I should cover before we build the experiment. I only know stuff gorgeous. Thank you, Gia. If you guys don't know Gia is a wonderful human being. We actually played Split Fiction together. Great physics in there. Gia loves to cosplay a little bit, and she does these gorgeous things with her elf ears. And so I did a bit of a sci-fi cosplay in Split Fiction, and she did a more like elf and green growth kind of cosplay, and we played Split Fiction together. If you guys are interested in seeing us play, I was very surprised at how wonderfully we matched together. Hi, Trail Runner. Okay, so a quick thing I want to show you. If you push, say, 1 volt through, 1 volts will get used. Okay, I'm about to answer your question, Sleepy. You are asking great questions. You should be guiding the lecture. have a small note here. I hope I got the graph right. I'm going to draw you a graph. This is the voltage versus current graph. Diode. I'm going to draw a marker. I'm going to draw current on the y-axis. And I'm going to... No. Yes. Current. And... Whoa! Sorry, I almost died. And drawing this axis like this, we're going to get negative, right? There is a negative possibility here for sure. And so what happens with a diode is that, let's say we start increasing the voltage in our system. No current, no current, no current. And boom, we hit 0.7 volts. Ideally, in an ideal system, it would shoot straight up. It's not perfect though. There's a little bit of a curve because of statistical physics. I drew that a bit wrong. It's too exaggerated. 7 here. This is a bit better. So this is in forward bias. As we increase the voltage bit by bit by bit by bit by bit, no current. No current. Current is 0, right? It's 0. Oh! We hit 0.7 volts. Suddenly, the current shoots up and it continues. This means that the current will continue. Let me think about this. As you increase the voltage, the current pretty much stays the same. Yes. There's very, very little that you can do to alter it. Breaking potential. There is a breaking potential. You could burn your LED, but we don't care about that. Obviously, don't do it, but be careful. Don't put too much current in your system. There's always a limit to your current in your system because you always will put a resistor in your circuit. Won't you, chat? Chat, you'll always put a resistor with your LED. Don't do what I do. Chat. Chat. You will always put a resistor, right? Right? Okay. So this is in forward bias. There will always be a voltage drop of 0.7 volts, or you need to reach 0.7 volts to get current to flow. And you have to manage your current externally, basically, by putting in resistors in your system or other diodes or things like that. There is no resistance associated with the diode, pretty much. That's the weird thing about it, which is really, really cool. Now, in reverse bias, another thing can happen. So obviously, a diode is really, really useful. If there's current going in the other direction, if there's voltage, yeah. If there's current going in the other direction, it won't let it through, which is great. We kind of want that a lot. But something can happen, which is called the breakdown voltage. Breakdown, I think it's called breakdown. Again, I'm so sorry. I'm doing all of this from memory. I have unprepared this part. So correct me, chat, if I'm not saying the right thing. This is the breakdown voltage. And I think this is called the knee. I don't know if there's a joke in there, but I'm guessing, do you know the way... Okay, I'm approaching my 30s now. I think there's a few people here in their 40s, maybe. How are our knees, chat? Is this a sensitive topic? How's everyone's knees doing? Hi, Nerdvino. Welcome in, welcome in. Nerdvino, do pray tell. Tell us how our knees are doing right now. We don't talk about knees. So, the knee is, it's physically kind of looks like the knee as well, but also this is kind of where it begins to break. Usually, this is probably not the right story. I'm just going to say it this way anyway. The knee is one of the first breakdowns in our bodies as we get a bit older. So this is the breakdown voltage. It is the voltage with the negative polarity, i.e. in the negative direction, that we have to reach where the diode breaks. This is not good. We don't want this to happen. This is a bad thing in diodes, some of them. Except for xenodiodes. Xenodiodes are really cool. And this is what we call the breakdown voltage. But in a classical normal diode, especially an LED, a light emitting diode, this is not good. We don't want this happening. Don't do this to your LED. You will blow it up. Obviously, I said that, and now everyone wants to blow up their LED. Listen, look, okay, look, we have all done it. It's like electronics 101. If you're into electronics, you have to blow up something. Is it called the avalanche breakdown? Gonna need a new LED, exactly. That's actually how most LEDs break. So if anyone has worked in a lab, or if anyone, you know, did physics or electronics in any of their courses and you were building stuff in a lab, and you're like, oh my God, none of these LEDs work. Why do they not work? Someone broke it because of the breakdown voltage. I think it's time for me to get that power supply. Nice, Teddy. It's actually very cheap. I got it on Amazon when I started out. Sorry, I burped a little bit. So we have covered everything about diodes theoretically. That was a huge lesson. Very, very, very dense. This is not usually done in an introduction to electricity. This is usually introduction to solid state, number one, or number two, introduction to electronic devices. This is a little bit more, you know? So don't worry if you've never covered this, number one. But number two, I think this is really interesting if you haven't done it and if you have done it. It's a little bit of revision, and revision for me. I haven't done this in years, which is really, really cool to apply it. So we won't get into source and drain and all that. No. Well, what do you mean source? So source is like the source voltage? Why do I know those terms? Explain to me again what they are. Is drain the same thing as bleeding current? Is drain and bleeding the same thing? Oh, it's the transistors. No, I'm not doing transistors today. I do have to teach it soon. But I have no lecture notes prepared for that, no. Do you want me to? I could do it. I'll be doing it over the summer, so yeah. I'll be doing it sometime at the end of July or August. So if you guys want to follow me, keep an eye out on Discord and social media of what I'll be doing. I will be covering it. I'll be learning about it mostly. So before we finish on LED, that good stuff, we have to do an experiment. And I just want to show you how an LED works. Now, diodes usually work with 0.7 volts. The reason why I chose that number, it was not a number I chose at random. It is an important number. But another thing that is a diode is LEDs. LEDs are light emitting diodes, and they're different lights. Hold your horses, a little bit of cool physics chat. Certain lighting emitting diodes need higher voltage than others. Okay, so let me pull out some lights here for you guys. I need to do a bit of Ohm's law as well, because I need to put a resistor. I'm not going to make the same mistake that I did before. Blue, and we'll take green. Okay. So we have a bunch of LEDs here. I'm going to show you them. Zoom in for you guys. Table. Oh, too much. You can see Bob's wheels peaking. 2 seconds. My Witcher music has stopped. Great. Perfect. Okay, where was I? Yes, so we have LEDs. Now, what's really interesting is I'm going to show you something. Do you notice something very interesting about the pins coming from this LED? One of them is shorter and one of them is longer. Exactly. And the reason why we have one slightly longer and one slightly shorter is directionality is important. Remember, I said that we want electrons to flow from the negative, the N-type junction to the P-type junction. The electrons will not flow in the other direction, and so we do need a LED. We do need to connect the positive port of the voltage to the longer shtick, shorter one. Let me think. I'm just going to do some quick maths here. I'm going to be using a voltage of up to about 3 resistors. What size resistor should I use to LED? 1 kilo ohm will be very safe. Might be overkill. We have to share the voltage drop with the... Yes. Might do here. This out. I'm gonna get probes ready. Probe these LEDs in a second. Oh, is the mic cutting out? Sorry, I was thinking. I was muttering to myself. Let me get these guys. I'm sorry, I have so many circuits I need to clean up. Okay. All right, let's go. Fair enough, fair enough. It's okay not to know things. I don't know a lot of things. Funnily enough, I know a lot more things that I don't know than of things I do know. Wait, did I say that correctly? I think I'm confusing myself. I think 1 kilo ohm is plenty. It's very, very safe, and we'll measure the voltage drop accordingly. Hi, Kawaii Guy, welcome in. Don't cut the red wire. Wait, but that's the live. If you're dealing with bombs, that's the one you want to cut, right? Don't take what I say for granted, chat. I do not make any explosives. I don't know what I'm talking about. Don't listen to me. Okay, so we're going to use milliamp and... No, we're not. We're measuring voltage. Voltage node. And we're going to use the COM. So remember, COM is our reference point, right? It's the common ground. Don't confuse with earth ground. Earth ground is quite literally a physical pipe that you connect to the ground. But we do use those terms interchangeably all the time. Wow, it barely got in there. Because this is quite poor. But it should still work. The idea, the premise is still the same. And I have 2 needles. Positive and negative. That works. So let's put in a resistor. I'm not sure which resistor this is. So I'm going to put in a 1 kilo ohm resistor that I know is 1 kilo ohm. What about Mars ground? Okay, here's a physics question for you, chat. Why does charge flow to the ground if we put a metal pipe and connect all the circuits to it? Why does everything go to Earth? Why is the reference point of Earth so good that electrons want to go to it, chat? Whoa, conductivity. Okay, why? Anyone have a notion? This is a bit of a quiz. And I'm looking forward to explanations. Biggest reservoir. I like that. Yes, that's a really good phrase there. Because Earth is a negative place, Jesus Christ. I like that explanation, the reservoir. And I like that because I'm a person who loves thermodynamics and loves physics, and we love to use the term reservoirs a lot. So you're absolutely on the money there. Absolutely on the money. Earth is a huge, huge reservoir. There's a lot of charge happening in Earth. First of all, in the center of the Earth, we're building up a lot of electric currents, and we're building a magnetic field because of that, i.e. Earth's magnetic field that protects us. But also, there's just a bunch of stuff happening. I put a lot of charge into it. There's positive, there's negative, everything like that is happening all the time. But wait for it. It's so massive that it's net pretty much zero. It is so big that pretty much nothing can change to it, no matter what you do to it. Don't challenge yourselves to shock Earth. That it's pretty much as close to zero as it gets. Well, I'm glad that's how you got here. You guys are all more than welcome here from the front page, discovering me from the front page. Really, really appreciate it. We had a few silly gooses in the beginning, but honestly, chat has been amazing. I really appreciate the positivity because, you know, I do want to make this a bit of an educational and positive environment, and you guys have been honestly amazing. You're very awesome, lab rats. Very, very awesome. Let me just do a quick thingamabobby. I'm going to measure the resistance of this. Oh. I have a resistor already, Tofu. What are you doing? I've only had 4 cups of coffee today, chat. Let me just measure the resistance really quickly. Even though I have my boxes labeled, boxes lie. Labels lie. Always test your resistors. Turn this on. Okay, that's 0.985 kilo ohms. So that's pretty much 1 ohm. That's good. Okay, so we have 1 kilo ohm resistor and we have an LED here. Again, I highly recommend you do not turn on your power supply, your battery, anything, unless... Oh, Jesus Christ!
Gee, Ray, what do you want to do
Unless you have
tonight?
a resistor in series.
Same thing we do every night, Pinky. Try
and take over the world. You scared the shit out of me, though. My goodness, indeed. My heart. Do you know what? I really do need to turn off the sound alerts when we're doing soldering. It's fine if I'm building these electronic stuff. It's a bit of fun. It's a bit of crack. But when I'm soldering, I think it's a health and safety risk issue here. Okay. Let's, okay, so we have the resistor. Everything is working. We have an LED in series. I think I have everything correctly connected. And want to measure voltage as well. Oh, are we hitting the current limit already? Hold up. No way. It's shutting down already? Should start with the red resistor, by the way. Red volt. Alongside it is. 2 seconds, chat. Let me just see something. Connect these bad boys. And on this guy. What's going on? Down to like very delayed. Okay. 1 volt. Okay. Let me short it and then I'll put a current limiter to this as well. Let me think about this. How much current? I think I want 20 milliamps. Am I right, chat? If anyone knows LEDs, what's the limit that I want? $20 is loads. Hi, Snoods. Welcome in. $26 milliamps. What do you think, chat? Is 26 milliamps more than enough? Let me see. What is maximum current? Maximum current through LED. 20 milliamps. Okay, let's go a bit lower. Let's go a little bit lower, chat. Just a little bit. Oh, this is so sensitive. Because it can go up to 10 amps, it's a really, really sensitive piece of machinery. Oh. Okay, 22 milliamps, 21 milliamps, good enough. It'll shut down if it gets to 21 milliamps. It might be too late. We might have blown this already. But listen, it is what it is. Oh, sorry. Alright. Oh, well, I should have actually. Let's connect this resistor again. Go. And this guy here. Maybe this LED is blown already. Not sure. Okay, let's increase. Let's turn on our voltage. Am I doing something wrong here? Pause, champ. Yes, we're trying not to blow an LED. Is pretty much the correct thing. Why is there no voltage? The current limit? No way. Let me think about this. Has the LED blown? Yeah, I wonder. Let me just do something really quick. I'm just gonna test that everything's working fine. I'll just put the thingamabobby in. No, it's not working. What the heck is going on? It's my voltage supply. Positive to negative. Like I just have a resistor in series, you know what I mean? Come on. Ah, it's my power supply that's acting up. Sorry, chat. 2 seconds. So weird. This is just a normal 1 kilo ohm resistor. Oh. Working now? So weird. So bizarre. Sorry, my power supply is a bit funky. That's my bad. Okay. And increase it all the way. Amps. I don't think I did the math wrong on this. I mean, I could have. I make mistakes all the time, of course. Everybody makes mistakes. But I put 1 kilo ohm resistor and I put a tiny amount of voltage just where I already hit the cap, you know? So we put a 20 milliamp limiter, which means if it hits accidentally 20 milliamps, everything shuts down. It's dead, Jim! 1 volt over 1 kilo. Yeah, exactly. It should be very, very, very good. Very fixed. Let me unshoot it. Yeah, it should work now. Okay. I'm just gonna do something slightly dodge, which is put it together live, because like it was doing weird things when I connected it. Negative port, I think. Go here. Okay. This looks fine. And then I increase the voltage. 1.5. 2 volts. Wait. How much voltage do I need to drop? So I don't actually know if the LED... How much... Oh! No! Whoops! Abort, abort, abort. My thing unplugged. I didn't notice it. Abort, 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 abort. There we go. Make sure my crocodile clips are connected. Hey, Bruce. Welcome in, welcome in. Ah, there we go. Okay, works now. Woohoo! Do you guys see it light up? And decrease the voltage down. Okay, so what we're going to do is we might need 5 volts sometimes, Panda, but I think it's red. It's the red LED. So there's a really interesting thing that happens depending on which LED we use. Okay, so let me show you something really quick. I'm not going to touch the power supply because there's something funky going on with my power supply. It is a cheap one, but listen. Let's increase this voltage ever so slightly higher and higher until the LED lights up. Oh! Somewhere around this voltage, it begins to light up. Do we see that? No, it's a 1 kilo ohm resistor, Panda. 1 kilo ohm. So that's probably why the maths is a bit. Now, what we can do here is measure the voltage across. So let's measure what our voltage is. It is 1.74 volts across here. And the voltage across this resistor is 0.115 kilo ohm, volts. About 0.2 volts. That adds up correctly. So we have about 1.7 volts here. And about 0.2 volts here. Let's increase the voltage ever so slightly. Do you guys see this monitor? You can. Let me angle it this way so you can see it better. Let's increase the voltage ever so slightly. Oh, it got really bright there. Very, very bright. Let's measure the voltage across the LED again. 1.8 volts. And 0.80. 0.8 volts. Kind of jumping around because I'm a bit unstable with the needles. Seeing it clearly now. Yes, pretty lights. So, again, I'll measure it. It's about 1.8. It is increasing ever so slightly in voltage, but most of the time it shouldn't be. It kind of doesn't. So, the voltage that we're measuring across the LED should be about 1.7 volts. It's turned off now. Visually, I know you can't see it properly, but let's move this a little bit up and up and up. Around 1.7 volts is when it lights up. It starts to light up ever so slightly, 1.8 volts, okay? So about 1.7 volts is what we need to power this LED. And all of the voltage, like we could increase this voltage more and more and more and more and more, but most of the remaining voltage will be dropping across the resistor. At the moment, a very, very tiny amount of voltage is being dropped here. The more we increase it, 1.77. It does increase ever so slightly, but remember the graph I drew on the board. It wasn't a straight line. There was a little curve to it. So this is the part of it, okay? Now, let me decrease this down to 1.7, or the moment it shuts down very slowly. It shuts down. Okay, what we did was we used a red LED. Let me replace this with another LED. So remember, 1.7 for red. Let me use a yellow one. This is the positive port. Go. Okay, so at the moment, we're supplying 1.1 voltage. The resistor get hot? Absolutely not. This is so little. There was so little current in the system. Everything's okay. We're not going past 20 milliamps. I'm not saying go lick that, but basically it's fine. We're working with such tiny currents. Everything is safe. So safe that nothing gets warm. But absolutely don't go licking electronics, chat. Don't do it. I have very, very aggressively said not to lick anything. What's the V? It's the voltage. The potential. Is the longest lead on the LED always positive? Yes. Absolutely. It's the positive. And not just in LEDs, in anything. Capacitors. So I have a capacitor here. An electrolytic capacitor also has a positive port. Let me show you this bad boy here. This is a capacitor. And look at it. Oh, it also has a short and a long pin. This is conventional electronics. All what's the word? All electronics that have 2 pins will have a longer pin to show you the positive port versus the negative port. Now, let's increase the voltage up to 1.7. Oh, sugar plum on a cracker. It's not lighting up. What? 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 It only took 1.7 volts to... What's going on here? I feel like a bit like Dora the Explorer. Did it blow? No, not yet. Let's keep going. Oh, she's alive! That's a lot of voltage. Damn. Let me see at the point where it lights up. About here. It barely lights up. It's very, very tiny, but it's the tiniest light up. Higher band gap. Lovely explanation. So that depletion region, remember I showed it on the board, that big region in between the P and N junction, it's bigger here. The voltage to overcome a yellow LED, and this has got to do with really cool physics because it's got to do with wavelength of light. So chat, remember your wavelength of light. Anybody remember your rainbow? The first color in the rainbow is red. Then we go to yellow. Well, there's a few other colors to get there, okay? The next wavelength is yellow. Let's measure our voltage, by the way. I can increase it ever so slightly to make sure it's bright. The brightness of it does affect it. The voltage drop across this guy is 1.8. So it's ever actually slightly higher voltage. Not that much higher voltage. 1.8 consistently. So the red one was 1.7. This one is definitely 1.8, just to even get it going ever so slightly. So, well, let's check what green is then, Menace. Let's check what green is then. So let me just decrease the voltage down again. I'm dealing with the live voltage because for some reason my power supply goes crazy if I shut it down. Let me see. Let's take the green LED now. The long one is here. Short one. But again, we're dealing with such little current that everything should be fine. Oh, I almost shorted it. Okay, let's do the exact same thing again. I'm going to increase the voltage bit by bit by bit by bit by bit. We're reaching 1.7. It should be lighting up. Okay, it's not. Let's keep going. 2 volts. Okay, still not. Oh! It's lighting up. There we go. Our green LED lit up. Let's measure the voltage across this guy. Oh, come on. We can't be overloading. Are we? Oh, it's limited to 2 volts. Whoopsie, sorry. 2.17 volts. Okay. So the red LED needed 1.7 volts. The yellow LED needed 1.8 volts. The green needs 2.1 volts. Hot damn. Hot damn. It needs a lot of voltage to light up. Again. And last but not least, let's get the blue one. The long port is one. Port. So if you remember your colors of the rainbow, is this going to be really, really big or really, really small? Make your bets. Gamba, gamba away. So let's increase the voltage. Damn. Okay, we're reaching 2 volts now. 2.3. Oh! And Tofu said, "Let there be light" at 2.6 volts. Let's measure the voltage across it now. 2.49. Hot damn. Hot freaking damn. Oh no, don't do it. No, I should put it down. Fine, it's 5. She's alive. Good. Okay, so This guy needs a lot of voltage to get going, the blue LED. And this is a very, very popular thing with LEDs. The red LED needs the least amount of voltage to power, then all the way to the blue one. And this has got to do with the spectrum of light. If you remember, red LED has a lower wavelength, while blue has the higher wavelength, and you need more energy to basically get that blue light going. Where is my last chocolate surprise? Here's a very big surprise coming now. I want to show you something cool. I'm going to pull out a white LED. Where is the color white on a rainbow, chat? Because this is, I put these guys in the order of the rainbow, from lowest voltage to highest voltage. Ooh, dropped it. What is white light? White is the absence of color, is it? It's all the colors, is it? Ooh, very interesting. It's a big Skittles. I think so as well. I think it's all the wavelengths. I'm going to gamble and take a guess that it's going to be a lot of voltage. It's magic. Good. That's a good answer too. Let's test our theory out. I think it's going to be a lot of voltage. Let me decrease the voltage a bit. I have to keep it on because it's weird. Ideally, I should be turning it off. Okay. Volt. Let's go, chat. Are we ready? Dun, 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 dun. 1.9 volts. Not lighting up. 2.48. Is it lighting up? Let me see. Oh, there we go. Let's measure the voltage. It barely lights up. 2.48 volts. That is higher. Am I right in saying it? That is higher than the blue light. Or is it the same? I actually think it might be the same, chat. It was 2.47, wasn't it? 2.48. Bang on blue. It is, isn't it? Now, why is it the same voltage as blue? It was 2.49. Okay. So white light turns out to be blue light. Oh no, this is where Tofu starts the drama. Because it's not white light. That's one way of looking at it for sure. That it's basically a combination of, oh, let me remember my color theory. Green, yellow, and blue? No, green, red, and blue? Which one is it? So blue light is on the maximum part of the spectrum, okay? And so everything, any color combination that you can make violet, well, purple is a weird color because purple doesn't exist technically. You can make greens, you can make cyan, magneto, browns, you can make all of these beautiful LED colors, right? But in reality, what they are they are just combinations of the classic primary colors. Again, I'm no expert in this, but this is my knowledge on this. Magneto, I don't know colors. I'm sorry, Grim. I'm not a color person. I'm not very good at this. And so, out of the whole spectrum of light that we do use, red, green, yellow, blue, no, there's 3 colors, RGBs, right? Not yellow, I keep forgetting. Blue is the most demanding. And so that is going to be your limiter. Whatever color you make that uses any bit of blue LED, if you spice up your LED colors or any of your colors with a bit of blue, it's going to need that cap. It's going to meet that voltage cap if it meets that requirement. That is why anything bluish looking is quite expensive in terms of LEDs, not in terms of production, maybe I'm wrong about that, but mostly just by power, just in terms of feeding it. But because white LED is a combination of a couple of LEDs, everything is capped at blue. So if you use blue in anything, you're always going to be capped at that maximum voltage, 2 point. Yes, I do actually, John. Yeah, it's very good. Because they're long lost souls, Stark Toasty. And that is the introduction to solid state physics and to semiconductors. I hope we learned something. I know that the experiment wasn't that crazy, but it was really, really cool to see visually and actually like see the measurements of the voltage and stuff. Sorry, my power supply was a bit wonky there. He's a bit temperamental. We all are a little bit. It's a bit hot lately, so it can be understandable. Sorry, I'm burping. No, I don't have IR, or UV LEDs. I don't have those. The blue LED did take the longest. That's true. I think Veritasium has a video on the blue LED. A lot of white LEDs don't work by mixing. I see yellow opaque mass. Oh, okay. So is it usually yellow then, and just kind of diluted yellow with the frame or like a glass kind of casing that gives it the white tone? Take care. Bye bye. Oh, okay. I can't believe I've been doing 6 hours of teaching physics. I've never done such a long session on physics, but it is really, really cool. And we still have not finished. Can you believe it, chat? I'm still not finished teaching physics. Because the other thing that I want to teach is a bit of magnetism and then build a DC motor from scratch live here on stream. That's my plan. I can't believe I'm still not finished. Whew! We have a lot more to do, lab rats. Will there be class tomorrow? There will be. I'm taking a break this weekend, but tomorrow there will be one more class before I take a break for the weekend. Absolutely, Trooper. We can't put too much voltage across them. And it's not even so much as voltage, it's current. Current is usually the breakdown for the LEDs. In fact, 20 milliamps. So I set a current limiter, and that's why I had a resistor in my setup to make sure that more than 20 milliamps did not go through. Will this be on the test? Are you doing the wiring for like wrapping the wire around? Yes. So I'll give you a bit of a spoiler of what I'm going to be. I put it. Oh, okay. Oh, Bob is hiding it. Bob, give me back my motor setup. So. What I'm using. Power supply. This big wire. And this. Yeah. Bob, the assistance has it. Yes, exactly. So I'll be wiring it 7 times, I think. We can do some maths on it if we want to, but yes, I hopefully will show you how a DC motor is. What is this? This is a very classic. I muted myself. This is a classical DC motor setup to demonstrate how DC motors work, and it's very, very important. Because it gets the students to build it themselves, do the winding themselves, which might take a little while on stream. It will be very, very difficult to do it on stream, but hopefully. Because of its functioning as a diode. Ah, thank you for the plus or minus 5%.
And they call it a mine.
Dave, welcome in. Thank you so much for resubbing Tetsu's gift sub. Hi, Stray. Completely unrelated question. Do you believe we are being visited here on Earth by aliens? I don't think so. No. I don't think aliens want anything to do with us, honestly. Oh, power, wire, and this. So this is just a... Okay, so I'll show you what this is. A bit of spoilers. It's just a frame. I'm going to be putting a needle through it, the thing that's going to be rotating part of the motor. And in here are permanent magnets. Spoilers We need magnetism for DC motor. So that's what this is. It's just a frame for a DC motor setup. I'll show it to you. I will show it to you soon. Okay, chat, I need to go to the bathroom. I'm going to eat some jelly sweets to get some sugar. And I'm going to come back and we're going to start our last and fourth lesson, which is magnetism. And then I won't do too much electromagnetism. Here's your crash course in electromagnetism. When there's current going through a wire, whee! It has a friend. It wants to detach from this friend, but it can't. It's a magnetic field. So anytime you have an electric current, you create a magnetic field. Hold your horses. When you have a magnetic field, there is an induced current. Oh, shockers! There we go, spoilers. That's what electromagnetism is all about. I'll be right back. And we'll talk about flux. Not flux capacitor, but flux. Rise up a bit. All right, chat. Now we are going to the last part of our lesson. So if you missed lesson 1, lesson 2, and lesson 3, we are hitting lesson 4, and it's completely okay if you missed everything. Where was I going? But anyways, it's completely okay if you missed it. We're starting a new topic. It should all be fine now. And what we're going to talk about, before I actually do the, anyways, I will clean the whiteboard. I'm actually going to start with a demo. Then I'll do all the physics and the science and the maths, and then I'll go back and finish with the demo. So I'll do both things. So let me just clean the board first. I'm really sorry. I've been teaching for 6 hours, over 6 hours now. I'm a bit tired, so my brain is kind of slow. All right. This board as well. Buffering IRL. All right, here we go. Yeah. Brain depletion, yes. Talking about the depletion zone in PN junction, I have a depletion zone in my own brain right now. So the thing I want to show you is actually a really interesting and fun demo. It's a very classical thing. Oh, this is going to get so messy. I'm just asking for trouble doing it. But honestly, we just finished Semiconductors, Ash. We just spent about 2.5 hours on it. We finished all our lessons. Now we're just starting magnetism. Make a generator. Let me move my camera over here. Let's move this guy over here. Oh my god, there's such a mess. I really shouldn't be streaming tomorrow. I'll need so much time to clean up this room. Maybe that's what we'll be doing tomorrow, a cleaning stream. Let me, there we go, put you guys down here. Nice. And I'm going to show you something. So, hopefully the camera is going to catch everything. A bit of cling film here. So, oh. This is just some cling film. This is not a magical thing. I'm not trying to hide any secrets or anything. It's just for visual kind of, sorry, I'm moving my mic there. Promise nothing too scary or shady going on there. I have a magical thing in my hand. This is a magnet. It has a north and a south pole, and I'll cover that immediately or soon. But I want to show this demonstration because I can't jump too much between the whiteboard and this. So I'll just show this very, very quick. I'm going to put this down here at the bottom. And I have something very, very interesting here. This vial is a magical sprinkle of iron shavings, iron filings. And iron is one of these metals that actually warps itself or bends or gets attracted and all that good stuff to magnets. So what I hope to show, I hope the lighting is good enough. I don't know how well this is going to work on stream. We did finish the diode just there. Yes, Ash. Let's hope it works. So you definitely can see the magnet. Oh, I moved it. You can definitely see the magnetic field lines. Question is, how good? Right? When I teach it to my students, I actually put it up on a projector usually. That the field is very, very seen. Zoom in as well. Okay. So what we can see with these iron filings is that we have, they're actually demonstrating to us the magnetic field lines. We have lines coming in or going out. It depends. We're not too sure just yet. We have magnetic lines going out this way, but also kind of, if you look very closely on the side, we have some going out on either side as well. And they're kind of going in or going out, we're not sure just yet, in at this side. Now, what's really interesting about this is if you see it from the side, these filings are actually emitting ever so slightly upwards. Yeah, I'm so sorry that that the lighting isn't great. Maybe let me check a flashlight here. Oh, I think I made that worse. Tofu, stop doing that. I don't know. I don't think this is working. But hopefully you can visually see the magnetic field lines. So this magnet isn't much different to the magnet that you guys use, you know, on your fridge or on anything like that. But we have lines going in from one pole and out from another. Now the in and the out might be a bit confusing, and that's okay. But one of the poles is south and the other poles is north. Hopefully, we would know. Hopefully we could. We're already kind of instinctual about that. White page is a good idea, Lind. Welcome in. Do I have a white page, though? I don't think I do. All the things I have on this stream. White piece of paper is not... Sorry, I don't have something like that. We can see them curving. Excellent. Excellent. I'm glad you can. I want to lift it up, but I'm going to cause problems if I lift this. And I'm going to spread. Oh, I knew it. I was going to make a mess. Okay. Now this is the cleaning stream happening. Because of the attraction force. We have crazy stuff happening here. Now, I'm going to clean up all the iron shavings by just moving the magnet around, picking it up. I'll be right back, chat. I'm just going to move this to the kitchen, because I can't afford to dirty this room any more than I already have. Be right back, chat. Ugh! Lucky I didn't spill anything, which is great. No, it all worked out. Ooh! Ooh, my laptop. Dropping that. Okay, so let me get out my notes now. It's been a hot minute since I last taught magnetism. In fact, I don't think I really teach it in all my degrees, not in my degrees, but in all my courses that I teach magnetism, teach electricity and stuff. I don't really teach magnetism, but I do have my own notes on this. Notes that I've developed. Where are they? Go. Just to keep me in line. Okay, so when we talk about magnetism, there are things that are just inherently magnetic that exist in this universe. Magnetism is a weird one. You will study magnetism in different ways. You will study it in solid state. You will study it in quantum. You will study it in electricity. You will study it in all these amazing ways. Every field of science wants to do stuff with magnets. It loves it. It's very, very cool. And the magnetic field of a bar, the one that I was messing around with, see ya, Jimmy, take care of yourself, has a north and south pole. And if you guys have watched, what's that called? The Big Bang Theory, one of Sheldon's projects is about searching for monopoles. I believe it's still are only theoretical and are unsure if they exist. And the magnetic lines, this kind of invisible force that exists, yes, you can call it an invisible force, moves from the North Pole to South Pole. And we saw that with the iron filings kind of sticking out from the ends of one end and the other. The magnetic fields move from north to south. Now, chat, here's a question for you. Our Earth has a North Pole and a South Pole. Our Earth also has a magnetic field. Which pole has the North magnetic pole and which pole has the South magnetic pole? They are flipped. Exactly, Mullins. They're inverse. At the moment, they're inverse. They can switch every few, I don't know, 10,000 years. I'm not sure how long it takes. But at the moment, our North Pole is actually the South Pole of the magnetic pole. And at the moment, our South Pole is actually the North magnetic pole at the moment. I hear that it's apparently going to switch soon, but I'm not sure. Now, ceramics are excellent magnets, ferrites. That's a term that we tend to. But they're very, very, but they're also very, very good electrical insulators. So one of the things that we talk about, magnets are metallic, they're good conductors, but there are exceptions to the rule, and ceramic are kind of highlighted as one of them. They're very good at hard disks to write, to read and write. They're used for sensors and magnetic resonant imaging and motives. Now, these lines that I've drawn from north to south pole, all these lines, is basically if I were to spray my iron filings, this is kind of the shape of it would. We kept drawing it out and out and more. It can expand further and further. The further away from the magnet you are, the less of the force of attraction or repulsion that you feel. Now, these lines that we draw for magnetic field lines are called something very interesting. They're called, number one, lines of force, or my favorite one, flux lines. I don't give a flux. This determines, number one, the strength of the field, and number two, the direction of it. Very two important things. How, in my diagram, would I draw the strength of the magnetic field? What do you think I should do to the line to show that they're stronger? Want to have an idea in mind? You can take a guess, it's okay. The worst thing you can do is be wrong. Get the lines closer, exactly. More lines. So if I have really, really close lines overlapping here, super, super strong magnetic field. Further and further apart, less of a strength of magnetic field. So that's how we usually mess around with it. Now, kind of on what you're saying there, Maxer, is that what's really important about magnets is that opposites attract, likes repel. This is true to electric charge as well. There's a lot of similarities with electric charge and magnetic poles. You will notice that magnetism and electricity come hand in hand. Oh, very suspicious indeed. Now, where was I with this train of thought? Yes. So if I had another magnet and I tried to force north and north together, they would be pushing each other away. They're like, ew, gross, stay the hell away from me. But if I was putting another south pole closer to the north pole, it'd be like, yay, bro, and really, really trying to get super, super close to it, and there'll be a force of attraction. And I'm sure as kids, we've messed around with this plenty. We played around with magnets, tried to force two sides together when they don't want to be together. So it's a very, very important thing to remember. Opposites attract. Don't use that as dating advice. Opposites attract, likes repel. Hey, bro. I'd say it way too much. Welcome on, Giselle. Now, these flux lines, we need a way to interpret magnetic strength, magnetic fields. What is all of this about? How does it work? And one of the things that we use is called magnetic. Magnetic flux is a measurement of, well, the strength of these lines, and these lines inherently all together. And the unit that we use for it is Weber. In brackets, capital W, lower b. This is one of the lines that we use. If in case anyone is familiar with this, 1 Weber is equal to 10 to the power 8. It is 10 to the power of 8 Maxwell lines. But again, you don't need to know it. And also, I don't like Maxwell, so we're not going to talk about him. Actually, Maxwell was a lovely person, I'm sure. Maxwell's demon haunts me to this day. Now, fine. You gave me a measurement of lines around magnets. Cool. So what? What's really important is to know how many lines you have in a certain area. So you know that the magnetic force here is way, way stronger than over here, but you need to give me a representation of it. And the way we do it is by surface area. And so one of the important units that we use is magnetic flux density. Magnetic flux density. Symbol for it, capital B. It's the amount of flux per unit area. What is the unit for magnetic flux density? You might, guys, take a guess at this one. It's a very famous person. There is a car named after it. There is Tesla. There we go. We've guessed away. Tesla. Tesla's the unit. We also have a unit, by the way. The Gauss is the one that we tend to use. And the reason why we use Gauss is because 1 Tesla is massive. The unit Tesla is way too huge. It's just unrealistic. The flux per 1 meter squared is way, way too big. So we tend to use something called Gauss, which is a good bit smaller. It's 10 to the power of 4 Gauss is equal to 1 Tesla, because it's just a more standard kind of DeLorean. Higher the flux density, the stronger the field. Absolutely correct. Is Maxwell making coffee? No, it's almost 7 p.m. for me. Even if I'm getting a bit tired, I don't think I should have any more coffee today. Otherwise, I won't sleep tonight. I have to stream tomorrow, so got to do it. So just to put it in perspective, Earth's magnetic field actually shifts, and it depends where you are on planet Earth, but the magnetic field on Earth is very, very different. But just to put it in perspective, the average value is about 0.5 of a Gauss. I hope I'm pronouncing it correctly. I feel like I'm saying it a bit weirdly, as if I'm making fun of it. I hope you guys know I'm not making fun. Yay, 24-hour stream. No. Farad, Tesla, Henry, all huge values. What's with that? Well, that's because it's got to do with area. I think it is. Correct me if I'm wrong. The reason why all those units are way too big to use usefully has got to do with the metric system, with the SI unit of the meter. We use meter as an SI unit, and you can imagine that, you know, the magnet I played around with, and, you know, I played around with the filings, I played around with the LED and all of these things. They're used per meter squared. Now imagine what 1 meter squared is. 1 meter is about this big, then that big by length, by width, by, like, imagine that area. So I'm talking about measuring flux this big. How many lines of magnetic lines are in that area that I just showed you? That's a lot of lines. That's why these units are so massive. It's got to do with the meter squared. And in electronics, we deal with tiny, tiny, tiny things, and we don't care for these big, massive units. That's why everything is so off the scale. Hi, Branka. Welcome in. How many meters in a meteor? Fan here. Whew. Getting hot in here. Getting hot in here. 1 meter is about 2 feet perspective. Okay. Sure. Okay, so that's a little bit about magnets. And here's the thing. When there is... Sorry, my hair's flowing in. When current is flowing through a wire, right? We've been doing it all day today. We've been making loads and loads of wires and making current flow through them. All of them, every single one of them, was actually producing a magnetic field around it. Not just around it, technically perpendicular to it. And there's something called the right-hand rule in physics. I think it's usually the right-hand rule, but I can double check it. Now, the electromagnetic wave, we can even use light for it. Light is a perfect example. Light propagates, i.e. moves in this direction, let's say. This is where I'm looking. I'm making light go that way. Let's observe light moving that way. If light is moving that way, it means that the electro aspect of the field is moving up in this thumb direction. So it's actually moving in this direction, this wave. Up and down, up and down. The magnetic aspect of that field is moving perpendicular to it, but it's not like going this way towards you and on for infinity. It's also a wave. It's going moving from one in one particular perpendicular side, and the electro aspect is. Hold your horses and your cowboys. I don't know where I said that figure of speech from. You put those two words together and you get something called the electromagnetic field. You get terminologies of electromagnetism, electromagnetomotive force, all of these wonderful words, and it turns out it's because they're paired up together. You pretty much can't have one without the other. It's like a twin that will never leave you alone, and you can't separate them. There's really cool aspects of you do. But generally speaking, you kind of can't get rid of them, if that makes sense. So, what I want to do is a very crude demonstration of how DC motors. The creation or the discovery of DC motors was really, really cool. And the idea of it is very, very simple. There's a few ways of doing it at home. A bunch of batteries, magnets, and wires. But the idea behind it is have something. Basically, a little resistor bobby that was about to shock. And we wrap a wire around this piece of plastic many, many times. 1, 2, 3, 4, 5, 6, 7. Chose that number arbitrarily. And I'm going to make current go through it. Okay? I zap this and I make current go through it. Nothing happens. Yeah, there's current going through it. Yeah, there's a magnetic force. So what? Hold your horses. What if I put a permanent magnet here and a permanent magnet here? So what happens is, if I power this plastic piece that's a lot of wires wrapped around it, if I give it power, it produces an electric current. That electric current produces a magnetic field. That magnetic field and that magnetic field are going to interact. This magnetic field and what happens is these guys are going to be pushed in this direction when it's swinging this way. When it's on the other side, it's going to be pushed in this direction to swing it on the side. Then it reaches the other magnet. That's going to push it in this. And the cycle continues. It moves it over and back, over and back, over and back. And this is fantastic. And you're like, this is amazing. If I continue supplying electric current into this system, it will continually move the motor. That's amazing. Where's our problem? pushing all of this whole system. This plastic little thing here that has the wire wrapped around it. It'll be pushing it. Instructions unclear, can't stop spinning. That is a very important point. It keeps spinning. So if you have a wire connected here and a wire connected here, you can imagine that, oh my God, all those wires are going to get tangled. That's going to be a complete and utter mess. So what we're going to do is we are going to have, let's say, a power supply, our voltage. Positive side, negative side, we're going to connect it. We're just going to have two closed wires here, which means that when this guy swings around in the first moment of connection, boom, it gets current. We close the circuit, it moves, and it starts to spin. The minute it begins to spin, oh no, I've lost my connection. I don't have any more magnetic force helping me to. Wait for a second though. When it moves 180 degrees, it's just upside down, the wires reconnect, and it gets more spin. Another 180 degrees it spins, it gets a connection again. It'll spin again, over and over again. So what's really happening is you give it power, it moves, it jolts, and it's basically classical mechanics where you give it enough momentum to actually move it. It has mass, it has inertia, right? You're giving it enough inertia to get to 180 degrees. It gets picked up again and moved, picked up again, picked up again, moved around. That's what we're going to try and do. It's a very crude explanation. It's okay if you didn't understand it. It'll be way better if I could show it to you. That's my goal now, live. Build this. Now, the problem with building this is it's going to take a while, number one. And number two, it won't work. This is the story of physics. So what we're going to do is we're going to have a nice, lovely, fun physics sense of we're going to do a bit of just chatting. It's going to be a minor just chatting stream while we try and build this. It does, yeah. Same way, Grim. Another thing about generators is that they do have inertia, and that is very much capitalized for response systems in electric. Get a bit more complicated. Don't mean to be complicated about it, but this is a really important aspect of electric grid systems. Where's my stuff? Oh, there it is. So this is the wire. This is this guy. Yes, but the current will be no, because you're breaking your circuit, Grim, and so there is no current flow. It's not inefficient. I'll show it to you. I'll show it to you. You'll see it now. It's basically an open circuit, and there is no current flow in that moment. Current will only flow in the moment when there is what's the word? What's the word I'm looking for? When there is a closed circuit. Now, I'm going to wrap this about 7 times. 1, 2, 3. I'm just taking a measurement here. 4. Yeah, exactly. This is where water pipe analogy doesn't work. 5, 6, 7. This is where the water pipe analogy doesn't work. There is no flow of water outside of the pipe. Current will not flow if there isn't a closed circuit. 1, 2, 3, 4, 5, 6. Am I right? That again. 1, 2, 3, 5. Wait a second. 2, 6. I only have 6. One of the FM lectures has a table of the hydroelectro analogy. Does it? Are you talking about the Feynman books I have? Where's my snip snip? My snip snip. Oh, I have my snip. Excellent. I'll snip it a little bit longer here, because if I have excess, we have room to make errors and mistakes, basically. So yeah, while I'm building this, I'll just be chatting with you guys. Oh, well, no. The concepts of brushless and everything that you guys are covering now is a little bit more conceptually a little bit more difficult. I'm trying to build the most simple DC motor ever with the introduction of, like, we are doing introduction to physics here, you know? I'd like to cover some basics if possible. Oh, my finger hurts so badly. I have, imagine my luck in life that I love electricity. I love to teach it. I'm a lecturer in this, and you know, my PhD is in involved a lot of electronics, all that. And no, lo and behold, my luck, chat. I'm allergic to certain metals, and the allergic reaction causes me to the allergic reaction causes me to have skin breaking all the time. We've put a pipe through this. The reason we've put a pipe through this is to ensure that it is very low resistance. The higher the resistance in the turning of this guy, the worse the system is going to be. So you can see that this guy is moving very, very easily, this plastic piece. And that's the idea behind it. We want it to be able to move really, really easily through the system. Why not wear gloves? Oh, God, I wouldn't be able to do anything wearing gloves. You need to be on top of it. You need to be sensitive to touch and feel of all these buildings. A ring coil made with one magnet? Well, there are like demonstrations of DC motors using one magnet. The one that's used is with the battery. It's not too far from how you need it to work. Okay. What are you making? I'm building a DC motor. I'm going to be winding this really, really tightly as I can, and making 2 snips coming out of it, because we want these little antennas to be sticking out. Let me zoom in so you guys can see this a bit better. Go. We want to be able to see some of these snips coming in. What was your subject? I did electric grid stability. I worked on vanadium flow batteries and wind turbine integration with electric grids. I now work with a lot of science material, a lot of batteries. Yeah. Well, while I'm applying for research at the moment. 1.1234, 4 wraps. Let's keep going. South Africa needs your help. Funny you say that. South Africa is talking about that stuff with us. Well, not with us, but you know, the vanadium flow battery research. I think they're actually looking at it. They're one of the peeps needing help and talking about it. Yeah, renewable energy, exactly. So I do a lot of work with renewable energy. Let me count how many times I've wrapped this. 1, 2, 3, 4. Oh, I can't count. 1, 2, 3, 4, 5, 6. One more time. Go, and then I weave it in here. It's okay to weave it. You know, some people might be thinking, oh wait, your electromagnetic field is going to be distorted a little bit all over the place. You don't need to worry about it too much. This is not an inductor thing we're trying to build here. We're just trying to get some sort of magnetic field to get a bit of a push. Through. Can I weave it like this? Come on, bad boy. No, you won't. Yet. Ah, you bastard. Come on. Try. Go. Right. Do a small snip. Right. Not bad, not bad. Been working on renewable energy for 2 years. Nice. Do you do research or are you in industry? Take a sip of water here. Yeah, the grid stability stuff is really interesting. But what's really interesting about the electric grid, I talk about it sometimes. I'm not very knowledgeable in this. I'm not too accurate about this. But so there's 3 major sections in the American electric grid. You've got the West grid. You've got the East grid. Again, you guys, if anyone's watched my stream for a long time, you've heard me talk about this before. You got the East, you got the West, and you got Texas. Texas has its own grid. Now, it is interconnected. It's not a completely isolated grid. No grid really is isolated completely. But what I find really interesting about it is the instability situation that they have about it. Again, not trying to make fun of it. It is a serious problem. But they have some serious outages over there. Despite how massive Texas is. The distribution is quite difficult to control over there. It is a big case study, though. This is Tofu's favorite America fact. Is it my favorite America fact? Let me think. Do I have a more interesting America fact? America and 2 other countries are the only 3 nations, including Ecuador, I think. No, not Ecuador. That do not subscribe to the SI unit. The only other one I can think of. They prefer their freedom units. That's the only one that I know. Myanmar and Liberia. Thank you. What is that sound? Oh, that's my freaking glasses frames coming out. I was wondering, there was like a clicky sound, and it sounded like almost like current zapping. I was like, Jesus Christ, I haven't done anything yet. Okay, so we build pokies. Look at this. Rawr. So we have built some pokies sticking out here. What are we making? We're making a DC motor. So the other thing we want to make is we want a power supply voltage to come out. Okay, so here's what we want to do. Oh, let me poke this through. We might have to do a bit of work to make this work properly. But we've built the first part of the DC motor. We've built basically the DC motor part. Wait, let me thread that through. There we go. Why is there resistance? Don't do this to me. Why are you resisting turning? Because, Tofu, your snippies are too long. Okay, I forgot about that. So my snippies over here are too long and they're getting blocked mechanically. But also blocking this. My wire too sticking out? Is that a problem? Sorry, let me move the mic. Want to make sure it's not touching. Looks good. So as you can see, mechanically, these wires are being stopped here. It's because they're too long. We're going to snip them later. But for now, it doesn't matter. The other thing we need to do is we need this wire, a positive and a negative port, connected to the positive and power supply. And you might be thinking, well, Tofu, how are you going to do that? Well, good news is I have a crocodile clip. A positive and a negative terminal coming out here, basically. And we're just going to make a crude wire coming out, positive and... Let's get snippety. About this long should do. We're going to expose the bottom so that it can connect to the power supply. And we're going to expose the tip so it can connect to our system over here. And I'll show you how it will connect. Engineering term of the day, snippety snip. It is scientifically accurate. Oh, I thought we were doing a vasectomy. Close enough. Close enough. Kind of is, right? I guess it kind of is. Okay. A lot of this time, this stuff doesn't work. You have to work with this a lot. It takes a lot of effort to get this to work. And another thing, if you're building this yourselves at home, chat, make sure to use single wire, none of those multi-thread things. The multi-thread stuff is not going to work for the setup. Just going to snip the bottom here so that we can connect it to our power supply. There we go. And we're going to do the same to this guy over here, but we're going to do a bit longer just so that we can ensure that it does definitely. I'm going to do a double little thing here as well to make sure that structurally very sound. Is the insulated wire an issue? For what, I'm gonna, by the way, hi. An issue for what? For connectivity? That's the reason why I'm snipping it, to get it exposed, otherwise it won't connect. Or is there another issue that you're referencing? I know for today's stream, I didn't know how long I'd do these sections. I did 4 lessons plans. I thought that, oh, I'd get them all done in 4 hours. But as you guys know, we're on our 7th hour and I still haven't finished the lessons. So we're not going to be playing any games today, I think, chat. But if you guys are interested, I do play games. At the moment, I'm playing through a game called The Alters by 11-Bit Studios. It's actually really, really fun and there's really interesting physics concepts. In terms of science concepts, we talked about Dolly the sheep before, but I was trying to figure out a good lesson on wheel physics. So if you guys have any ideas about good wheels, let me know. Just would it be better to be insulated around? Oh, that way. I see your question now. No, it's actually better because then if the wires were overlapping here, Tom Gunner, there would be a short. We would be shorting our wires. By insulating, we're forcing the current to go through each single one of the wires. Does that make sense? So, in fact, a non-insulated wire would be a problem. That's a bad thing. All right. Build our system. So I would come in through here and out through. Threading the needle. Now the frame and everything that I've built, you can actually 3D print it and crudely build it, but I'm using a classical, not high school setup. I don't want to be rude and saying, oh, we're doing high school level physics, but this is like an experiment that can be taught at a high school level. It is definitely not, you know, I'm not doing anything dangerous here. This can be taught to children. Adult-ish children. Jesus, threading the needle is really difficult. Dolly Parton, that's right. Yeah, so when I was in secondary school, we didn't do this actually for physics. But now it's in the high school level in Ireland, secondary school we call it. It's part of the secondary school curriculum now, DC Motors. It's very difficult. I'm very surprised they're covering. They have to cover so much in 2 years. Okay, so we've threaded the needle here and we're going to do the same here. The reason why I'm double winding it instead of, you know, just threading it once. You're like, why are you just not threading it immediately from below? It's just got to do with security, rigidity. If the wire isn't double probed or double looped, whatever way you want to kind of see it, it won't be as rigid. That's why it's so difficult to get it through, because it is so rigid. And that's the idea. We don't want this guy moving too much. I miss having a 3D printer. I hope to get one. I cheekily made a post on social media on Instagram asking for, just like a couple of hours ago, asking for a 3D printer for Bob. I made a post about it. And if anyone wants to go and support it. And I cheekily said, does any 3D printer company want to sponsor me? But even if I don't get sponsored, I think I will see if I can buy a 3D printer for my birthday as a birthday gift. So the American curriculum is a bit weird, right? In the sense that it's state governed. So for example, in Ireland, it's all of the nation of Ireland obeys the laws of, you know, what is in the curriculum education. But in America, correct me if I'm wrong, outside of SATs, any other subject is up for grabs and they can pretty much do whatever they want, state accordingly. Is that correct? Okay, sorry, it's taken forever. I got it through eventually, though. Eventually we got there. All right. Oh. Are you from the UK? No, Ireland. We're from the Republic. Hey. We've built our wire system. Let's go. So now I just need to clean this guy up. I need to... I think I actually need to take it out and snip this a good bit. Snip, snip. Sounds about right within some limits. Yeah, you can get pretty cheap 3D printers. The ones I was looking at are on sale at the moment for like 100 and 200 euro, which is really reasonable. Back when I was first looking at 3D printers, they were crazy expensive. But in the NATO, it didn't end up... Okay. There's definitely like weird and odd things. Oh, for 50 euro. Okay. I was looking at Bamboo, I think, is the company I was looking at. Right. This looks good. So snip it a little bit more to expose the wire a little bit more here. Right. Far out. Sorry for that accent. I'm not making fun of anyone. It's just I'm playing the altars, like I said, and there's this guy. There's this one voice accent in it. And we're just broing out together all the time. Okay, here we go, team. This is looking good. Now here comes the hard part. We've built the motor. So what have I done? I have two wires here that are sticking out, and I'm going to connect them to the power supply. We're going to apply about 2 volts. 2 volts is more than enough. There's no resistor in the circuit, so I shouldn't be putting much voltage. And the idea behind this circuit is it spins, it spins, it spins, and then it should connect to these two wires when it spins. As you can see, they're not touching right now. Also, they're too long. Snip. Guy. This guy. Ugh, there we go. Snip, snip, snip. Okay, so the idea behind it is these guys should be connected right now, like this. And then when it spins once, they should reconnect again with no resistance. That's what we need to work on designing our circuit with right now. That's our goal here. Okay. Close, close. We need to get this guy close. Oh, our snip snip is too... a bit more. Ah. Oh. Okay. Don't have... This is going to take a while, chat. This is the hard part. We need to get these wires happy in all conditions. Apply 240 volts. Okay. If I make them too curly, we need to be able to weave them back inside, if that makes sense. So we need them tall enough. I don't know if I have them tall enough at the moment. Oh, and they have to be on the outside. They have to go in on the inside and go out on the outside. That probably doesn't make any sense. It's okay. So we've turned it around, and oh no. I need too long getting caught. It's just a little bit of messing around. We'll find up eventually. A little bit of bendy, a little bit of touchy. We'll get there eventually. And all the students that I assign this to, they eventually get it. Sometimes it takes 20 minutes, but usually it's a 2-hour lab. So by the end, hopefully it works. Okay. Touching. We almost have it, team. And we touch. Ah, we done touch there. And we... Ooh. Guarantee. Okay. Almost. DC motor, yes. We're almost there, team. This is the finale of the great lectures that we've done today. By great, I mean long. And I know a lot of it was difficult sometimes, and I apologize for that. But hopefully, we learned a lot of things. We learned amazing things. Okay. Connection. Oh, so close. So close. Okay. I have a close connection here. Connection 1. Connection 2. Ah, okay. So sometimes it doesn't get through. Let me just get a bit longer of a wire here. Don't have enough closed. Have 1 here. Nice. 2. Nice. Yes. All right. It works. I think we have a close connection each time. Okay. So let's hope it works. This stuff doesn't tend to work a lot, chat. So I'm going to decrease the voltage. The current limiter, I'm going to have to increase. Current limiter has to be increased. A lot of current. Okay. Still nothing too crazy and unsafe for us. Set it to 2 volts now. Bit off camera, but just trust me, I've set it to 2 volts. Right here. Let me turn off the fan so for physics, exactly. Let's hope this works. I really hope this works. But it might take a lot of playing. See now? The power supply is off. Okay, I've moved things. Ah! Bulge in a bit. Damn it. Okay, we'll start again. Because we'll increase the resistance occasionally in that way. It'll get caught, unfortunately. Yeah, my gain is a little bit low. You might not want me at normal volume usually though, guys. I can be a bit loud sometimes. So it's okay if the mic cuts out a little bit occasionally. It's probably better for health and safety. So other than electrical health and safety, we probably have also some aspects of sound safety here. Ah, damn it. It was working so well. Almost. We do have a connection. It's just one is slightly more than the other. Possibly there could be. So hard to straighten it now that I've bent it so much. Magnet. Ah, damn it, I've ruined it again. It's going so well. Be here forever. How do you know which way it will spin? Good question. We could figure it out using the right-hand rule, but the way I like to do things is YOLO and hope for the best. If it spins this way, like you kind of are hinting or mentioning, we could have enough momentum to transfer it. If it goes this way, it'll get caught. So if we wanted to spin the other direction in case we do mess anything up, all we have to do is just switch the polarity of our power supply. Okay, this looks good. Maybe. Let's test it. Look, if it doesn't work, it doesn't work. Here we go. Oh. Current limit. Just quickly mess. Current limit. There is a lot of current in the system. It's actually kind of annoying a little bit because of the connection happening and unhappening again. It might be very, very sensitive. The power supply, I would say. Disconnecting, connecting. So the current might be shutting it down a lot. It's jumping. Was working there for a second, I think. I didn't see it, but when I looked back, I saw that this thing. So it must have moved. It's not working. Sorry, my power supply is a bit finicky today. So what's happening is, because we have a quick connection and a quick disconnection, quick connection, quick disconnection, the problem is sometimes my power limit for a minute might reach the limit and it'll just shut it down, you know? And I don't know if I can even shut off the current limiter. I kind of don't want to, just for safety reasons. But that could be an issue for sure. Poltergeist moved it. Is it AC? No, no, DC. We're doing, it's DC, it's a DC motor we're working with. A little bit of resistance here as well. Feel resistance. They say resistance is futile. Yes. Good connection. Good connect. Okay. Oh, why is my power supply doing this again? This was the same problem with the LEDs last time. It definitely is working, as in there is a connection occasionally at the very least. The problem is, yes. There is definitely a connection there. Is there resistance? I don't feel a resistance. Okay, there's definitely a connection. Let me mess around with the power supply. By doing this. Happened last time. Why does it do it to me? Volts supposedly. I just want at 2 volts. That's all I want from you. Volts. No, 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 don't stop decreasing. Stop. Oh. Bad voltage source. If you give it a manual torque, won't it work? No, no, that's the thing. It's not. That's the unfortunate part. I think my power supply is being rude. Volts should be more than enough. Force it. Just something is happening to my power supply. Sorry. Your battery would be a better thing. On. Okay, it's trying to move. It's definitely trying to move, chat. It's working, but it's stuck. There's too much resistance. Adjust. Feel any resistance? I do feel resistance. Why is it stuck there? The wires are kind of getting caught. Magnet. Okay, that worked. I cheated. Okay, half a turn. We're getting there. We're getting half a turn. So this is a good connection. Then a bit too much distance here. Not moving. At least we got half a turn. All right. Thank you, Jay, for that. I was about to ban as well. Some people are a bit of oddballs, as we can see. Okay. Maybe my voltage is too... Maybe I need to give it more oomph. Maybe overcome. I hate to admit it, chat, but I feel like this wire isn't wrapped tight enough and it's actually like creating problems. Oh? Almost there. We have half a turn done. Somewhere around here. Better. When I'm messing around with the wires, the power supply is off, in case anyone's wondering. That is definitely happening. The magnet is touching the wires. I think it's because I don't have the wires tightly enough. Problem. Fortunately. I'ma just put a little just do it in here. Okay, chat, you're gonna hate me. This is gonna be awful. I hate this. I hate that I'm doing this, chat. But you know what we have to do? I know it's awful. But we have to do this. We have to do this. We're on the front page. I'm not quitting until this motor works live on Twitch front page. It's the last thing I do today. Not more coils, just tighter coils. We're going to make these curls, these coils so tightly packed. There's no excuse for them. Is this Fallout New Vegas? No, it is Witcher Velen music. We want them tightly packed so they take up very little space. Hope I don't snap it. Wait, there's music? Yeah, it's very quiet in the background. Very soft Witcher music. I am under performance anxiety now. I must perform here. Okay, very good, very good. Wires here. Nice, nice. I get another wrapping done. Where the extra wrapping might be a problem. Go. Very nice, very nice. Let's go. Little weave here. Let's go. Nicely done, team. Nicely done. Okay, and then I'm going to weave this in here. It's okay to weave it criss and crossy. Like I said, we're not really caring about the wraps of a coil, you know, like with inductors and transformers and all of that. We're not too worried about that kind of thing. Wow, we actually have so much excess to work with because I wrapped it so much better this time. Hopefully this will help. Get this guy out, sticking out like this. I'll snip him here. You'll probably need more snipping. There we go. Okay. Pierce this guy through. I'll be very sad if this doesn't work. This is like the grand finale of my lecture today. It'd be nice to get it on the 8-hour mark. I only have 5 minutes left, chat. Only 5 minutes left until the 8-hour mark on my stream. 8 hours of physics. Oh my days. I don't think I've even done that in my lecturing job. Okay. Okay. A few things first. We might need to snip this guy a bit more. Also a little built here. Ooh, thing's broken. Okay. Feels better anyway. And here. Oh, too long. It's getting stuck. Go. Guy a bit more. Oh, guy bent over. And we're just messing around with the connections on the either side again, very similarly as last time. Here almost. A bit closer. Prettier. Ugh. Everybody knows uni lectures only work a couple of days. Oh. No. So it's moving smoothly. We've definitely fixed the friction problem. Now we just need to play around with these wires. Come on, Tofu. Come on, Tofu. You can do it. I believe in you. Yes, you. Potential. There is potential. Oh. We are building a DC motor. So I spent a little while explaining what magnetism is. And what I've basically done is I have a bunch of wires wrapped around here, which will produce a magnetic field. And right here, we have two other magnets as well. And so hopefully what will happen is that once I put on the power supply, we'll close a current here and it'll push the motor to one side. And even though it'll be disconnected for about 180 degrees, hopefully, it will be enough to get it through to the other side as well. But so far we're having a bit of connection issues, but this is normal. You know, like I said, when I teach this is like a 2-hour lab. So there's up to 2 hours to make mistakes. If that makes sense. Now we have had the motor work a little bit. We've had it do half a turn. Really easy to get it to turn half. Well, easy is relative speaking. But it's really hard to get it to do a full 360 turn. But the good news is, or the bad news is, whatever way you look at it, is it's really easy to get it to turn once. Really hard to get it to turn the second time. That's the secret in this. And I understand that you guys have tricks. You're talking about hooks. You're talking about bending outwards and inwards. There's different ways of doing it, and that's okay. I just genuinely think that this should work as well. I've built it a good few times. Unfortunately, as many do seem to suffer from this, I'm getting performance anxiety. We can't blame Tofu for that. Ugh. Or the electronics is getting performance anxiety. Sorry, not me. It's electronics. Totally not me. No, there shouldn't be any interference with the desk because everything else is insulated. Oh. Too long. As well. Hook. Almost getting it. I think it turns this way as well. Clarity that I've assigned it. need to mess around with this bit by bit, bit by bit. We also add resistance. If the wires are too like tightly connected, they also add inherent resistance. That's not good either. Don't want that happening either. Oh. Oh, come on. Damn it. There's definitely a little bit of push there. It works a little bit half the time. It's half a push. Working a little bit. Maybe do we need to lick it? Oh, gets behind. Almost there. Come on, Tofu. Only way to be sure, right? There's only one way to be sure. Will it warm up? Get it ready? Will that warm it up? Sorry. Oh, I missed the chat. Apologies. I've been so concentrating on this. For this, well, nothing is getting hot anyway, so that's good. Well, power supply connected. Fine. It definitely is connected because we did get it to work a little bit, you know. We could switch the polarity for argument's sake. Just to kind of see if better suited going the other way. That's another. That's another option. Ah! And then from that happens, then the connection breaks, gets caught. Poopy hands. Yes, I have seen it. Yeah, we saw it work for a half a spin, so it's a bit sad to get it not to see it properly. I'm so sorry. I'm really disappointed that this isn't working. It's such an easy thing to work. I've never seen it not work after messing around. I see a connection though. That's the thing. Only thing I would say is that, you know, oh, oh, almost, okay. It loses connection a little bit here. It's almost there. It's almost there. Let's go! Shit! She's alive! Hey! Let's go! Look at her go! Bzzz. If you look very, very closely, you can see a tiny spark in the connection. I don't know if the camera's picking up. It's moving so, so fast. But there's the tiniest spark of electron current going through. My voltmeter's going crazy. Well done, chat. Oh, thank goodness. It worked. In the last few minutes of the front page, our DC motor worked. Let's go. Oh, thank goodness. Thank goodness. Now, if I increase the voltage, it will go faster. We're not going to do that because I have no resistor in the circuit. There's a lot of current going through. If I'm looking at the thingy right now, it's like 200 milliamps going through, which is a lot. But yes, ta-da! I'm so glad it worked. Well done. Whew. Let me zoom in. Maybe you guys can see the spark a bit. Very, very closely.
Good news, everyone!
Jesus, you scared me, Jay. If you look very, very closely, there is a spark. Do you guys catching it ever so slightly on camera? There is a spark. Nice. Let me turn off the power supply. This will get hot. Absolutely will get hot. But finally, oh yeah, maybe I should turn on the motor, turn off the light. Oh. There we go. Needs a little bit of a push. Let me turn off the light. Maybe you can see the spark a bit better. I see it very clearly. The camera is still not picking up, guys. Yeah, the camera's not picking it up. I can see it very clearly. Okay. But I'm so glad it worked. Really, really cool that it worked. So sorry I spent so long on it. I know technically I was thinking about doing this before I even started stream. I was going to come in with the DC done. And also, although, you know, that would have been nice in terms of cohesiveness, you guys wouldn't have seen me struggle. And honestly, majority of physics, let's be honest, is struggling. Touch this. Is that hot? Oh no, it doesn't feel too warm actually. Oh. I mean, they cool down very quickly, but still, it's pretty interesting that it's not hot at all. Camera. But I'm glad right in the end of our stream, got the DC motor to work. Majority of everything is a struggle, exactly. Especially physics, especially electronics. All about getting stuff to work. And most of the time, stuff doesn't work. That's the beauty of physics. And beauty of science and beauty of electronics. But I'm glad it did work in the end. Did you treat... No, this is actually a school kit. It's a school kit for educational purposes. We teach this... So what we do with this... We have a module for this, but we teach... we bring in kids from high school level, you know, into the university, and we do this as a demo, and we make them do it themselves. Because as you can see, even though the demonstration was very simple, it took forever to get it to go. So, about every 180 degrees that guy spun, there was a disconnect. And he needed enough inertia and needed enough momentum to get it to the next 180 degrees, to get that current, to get that magnetic field, so that the other magnetic field could push it. This is the concept of DC motors. And now, ladies and gents, I would like to express my gratitude, number one. Number two, a kind of highlight moment to say that we spent 8 hours on the front page doing physics education. And everything you learned today was actually more than what you needed for introduction level to physics, introduction level to electricity. We covered a lot more than the base degree would require you. Because everything we did in the first 3 hours, which was resistors, parallel, series, Kirchhoff's laws, Ohm's law, all of that, that's first year level stuff. You've covered first year level physics and electricity. The stuff that I covered on semiconductors is actually a lot more difficult and usually isn't taught at high school level. So you did learn university level knowledge today on semiconductors, on holes, on electrons. That was actually pretty cool solid state physics you guys learned today. So absolutely applaud yourselves in the back for number one, learning something. Number two, if you didn't learn anything, it's okay. It's all right. At least you had a bit of fun. And finally, the last bit, the magnetism and the DC motor aspect, I taught you fluffy stuff, but the fluffy stuff I hope can be a little bit, you know, interesting. There was a little bit more demos in this at least. You've added some moral points to Twitch. Thank you. I was here. Yeah, I really appreciate you being here. I know that maybe physics isn't too interesting to some people, but it was really cool to see you here and cheering on. And obviously it's so cool to see that you guys were here while the DC motor, well, the struggle of the DC motor and the redemption arc of the DC. That was really good. And thank you everyone for the follows. If you guys want more content, I'll be streaming tomorrow. I'm taking a break over the holidays or the weekend, because I don't know where you guys are in the world, but Europe and Ireland and UK and all of those regions are suffering from a heat wave. So I am not going to be streaming next weekend, or this weekend, because, yeah, it'd be too hot, I say, with a fan blowing in my face. It might be too hot tomorrow, but we'll try. Yeah, spam those burn emotes because it's really hot. Thanks for hanging out, Kim Topher. Appreciate it. Build a DC motor fan unit. I need to build a fan for Banzo, Bambi. See if she's into it. She's running around somewhere in the house. Oh, I have the door closed, actually. But it has been an honor meeting so many of you. There's so many people who followed. I hope you enjoyed the physics session. And if you guys obviously have questions, I apologize for not catching a lot of chat. Please bear in mind that there's been a lot of chatter, a lot of movement. And so it was very, very difficult to keep track of everything, hopefully, understandably in this case. Lasers next. Firing my lasers. Maybe we can build, yeah, so there's another DC motor that we can build. I don't know why I didn't think about building it, which is like a battery. You just get a block of a battery. You put a couple of magnets at the bottom.
Gee, Ray, what do you want to do tonight?
The same thing we do every night, Pinky. Try to take over the world.
And you coil a wire, and when it's closed, it moves, and when it's not closed, it doesn't move. It's basically the same concept, and I have a few of those pre-built. I just don't know why I didn't think of it. I wanted to show you this setup. The reason this setup looks a little bit more complicated, it's a little bit more truthful to a real DC motor. Does that make sense? So even though it's a little bit more complicated, what I showed you today live on Twitch stream, it's also more truthful to the real design and output of a DC motor. Good night, Gia. Thank you so much for hanging out. I really appreciate the support. Thank you. Good night. How many magnets to make a light bulb? You could stream and test how to melt big blocks of ice in the most efficient way. Oh yeah? foreseeable future. Solar panels too, please. Yes, that will be a segment that I'll be doing for a charity stream in a couple of weeks. We'll be doing solar panels then, if you guys are interested. Because we're raising money for solar panels and batteries for a Zambian library.
It is possible to commit no mistakes and still lose.
Still lose.
That is not a weakness.
That is life.
That is life.
The card be dropping some encouraging words there.
Commander, set a new course.
There's coffee in
There's
that nebula.
coffee in that nebula.
We won't be doing much more coffee, unfortunately. Like I said, it is 8 p.m., so it is very, very late. Despite how exhausted I am, it is very, very late, and we should go to bed soon. Gotta love Picard, though. Gotta love Picard. I'm just seeing who's nice and sweet and kind right over. I know that we have a lot of viewers from the front page, but those viewers are not going to be moving with the raid. So if you want to make sure to be in the raid, make sure to follow, make sure to click into the stream away from the front page. Otherwise, we will lose you. But generally speaking, you guys have been amazing. There was I think I only banned 2 or 3 people in total today, which, let's be honest, for a front page feature, not bad. You guys are really, really well behaved. I really do appreciate that kindness, that yes, we might not have done hardcore, complex, very difficult physics. And a lot of people, were negative and bringing down people, because that's one of the best things, or one of the pet peeves I have, is that when people say, this is so easy. It's just such a horrible attitude in my eyes, because if it's easy for you, then this content isn't for you, number one. And number two, bringing down people who are interested in learning in any shape, way, or form is just so odd to me. It's like me going to a bunch of kids who are learning algebra for the first time and going, haha, you guys don't know basic algebra, lol. It's just weird behavior to me, and I don't appreciate it because it just discourages people, and I hate it. So I really, really want to say, I really appreciate how amazing it was that, like I said, front page for 8 hours, thousands of viewers, and we only had to ban 3 people tops. So absolutely amazing behavior from all of you. Everyone who followed and was participating in chat, you guys are more than welcome here again, because you're very, very kind and very good, and we appreciate that. And if you guys want to follow me on other socials, I do different content on social media. Yeah, I upload some clips from Twitch, but most of the content I do on Instagram and all of those things.
Call it a mine.
A mine is actually quite different. A little bit more advanced than what I do on Twitch, but still a little bit different and gives you a lot of support. Chaps, thank you so much for your PP. Thank you so much for the contribution and the sub points.